Right, welcome to this day of talks about time and networks. We've got an excellent lineup today. I started learning about this subject in 2000 when I began a PhD on dynamic networks, as it was then called. And at the time, I don't think you could have filled a large office with the people who were studying that topic. So it's brilliant to see so many people here today. Thank you very, very much to Naomi and Matt, who've been doing the lion's share of the organizing, and Ben, wherever he is, who had his company Pometry, who exists to develop the Raphtory software. Here we are, and thank you, Ben. Who has, Pometry has sponsored this meeting. So a lot of the things you are eating and drinking are there because Pometry's here and this is their office space. And I'm not going to bore you with a long talk, so I'm going to instantly hand over to, who is speaking first out of you two? I think it's you. Okay, there we go. So our first speaker, Dr. Ben Steer.
Thank you very much. Hello, I'll just make sure clicker's nice and working. Yeah, so thank you very, very much for all coming along. I hope this is as interesting as it is to you, as it is to me. So I'm here and joined by wonderful Naomi Arnold, talking about Raphtory, which is a platform that I've been building for a very long time now, which is used for the analysis of temporal graphs of scale, which hopefully should be up your street. So before I go into a bit about the tool itself, I thought it'd be interesting to give a little bit of the kind of ecosystem and history. So that's me. I was previously doing my PhD at Queen Mary University in London. Wonderful Richard was my supervisor. And during this time, I built the first version of Raphtory. And our kind of goal of this was to take sort of network analysis and be able to build in this kind of tools for dynamic analysis, temporal analysis, and in a way that's kind of intuitive and useful. When I finished my PhD, I didn't want to go and get a job. It sounds a bit crap. So instead, I founded a company called Pometry with the kind of goal of building the enterprise version of Raphtory so that we could kind of take what we're doing and scale it out. And some of our co-founders and people that work with us are splattered in the audience and are upstairs. Naomi, who should be taking over half of this talk as well, is a researcher at Queen Mary and the Alan Turing Institute and builds really, really cool projects on top of Raphtory and also builds a lot of the features into Raphtory. Which is super handy, which was actually one of the funding bodies behind the tool. And then there's a splattering of other wonderful universities that are involved. So shout outs from Felix, my other advisor, who I believe is online somewhere, Renault, Oxford, and all the other Oxford guys that have been involved in this. It's great to kind of grow out the community. And obviously, if you're interested, the whole point of this talk is to get you to give Raphtory a try. So in this session, normally I try to convince people why temporal graphs are cool. Hopefully this is the first room where I don't have to do that. But obviously I can shout at you in the coffee break about why that's the case. Discuss some of the challenges and kind of why we made Raphtory, why this come along. And then dive into some of the architecture, look at some of the research projects that are built on top and why it'd be kind of useful to analyze some of the data sets that you have with Raphtory. So right, what are the challenges? Why did we bother doing this? So the first is, as most research code gets to, it gets very hacky and messy quite quickly. So if we take something like, oh, I don't know, I want to get the weekly PageRank scores for some social network data that I have from the start to the end, I might do something like this, which is I'll load up Network X and pandas. I'll read my Facebook data into a data frame. I'm then going to create some range. So from the start of my time to the end of time, incrementing by this week. And then I'm going to bung up a for loop where I filter my data down, create a graph, run my algorithm, and then append my results into an array, and then probably do something else later with it. Well, I'm a terrible Python programmer. When I was writing even this segment, I got loads of weird pandas errors. And then there's kind of this question of like, well, if I want to do some other filtering, I want to aggregate maybe monthly, annually, all time, add some extra bits in. I come back a week later. God knows what I've done with this code. I've only put one comment in. I don't remember. So this all becomes a bit of a nightmare. At least that's my experience anyway. The other side of this is once I've actually written this and it actually runs, well, you know, there's kind of good luck running it on anything at scale. I'm making several passes over the data, one for each point in time. I'm reconstructing and discarding many individual graphs. This is like causing horrible problems with memory. So this is not ideal for sort of large networks where I've got lots and lots of data, or if I've got a long period of time when I want to increment, say, every hour for maybe many years. The other question when it comes to this is that I've done that for my sort of Facebook data. Well, what if I have some network snapshots that I want to mix with a stream of updates? What if my nodes and edges have a duration? So they're created at a time, they're updated, they're deleted and created again. So the kind of existing tools that are out there don't really do this. They're not designed with this kind of dynamic elements in mind. And that was the kind of initial goal of Raphtory. So what does Raphtory look like? So it was this kind of first platform built with these ideas in mind, and alongside the kind of analysis, as I was kind of alluding to in the prior slide, one of the things that we're interested in is being able to kind of attach data from anywhere and make it very easy to go from, I've got this random stuff somewhere in the ether and I want to build it into a network. So whether this is, I've got some data on my laptop, it's in a cloud storage, it's on a database, it's in some Kafka stream. All we want to do is say, hey, my data is over there. And I've got this parsing function, which says, given a tuple from that data, these are the nodes in it, this is the time in it, and this is the edges and interactions. And then this can just be pushed into a model where everything is chronologically sorted, can be distributed and analyzed at a kind of wonderful scale. So there's some nice things here that we can get into if you're interested in, which is that you can bung in data from multiple sources, it will ingest it all, push it all together and chronologically sort it, which is quite nice. And then we expose some query endpoints, so you can do things like look at your graph at any point in time, apply a variety of windows, run a plethora of algorithms, and get all the output out in a nice format. There are 30 plus algorithms that are currently implemented in Raphtory, and a variety of other ones that we're hoping to get in soon. These are the sort of traditional ones that you'd imagine. Things like PageRank, some sort of centrality measures, but then there's a wonderful new set of algorithms that, for example, mostly is actually not only working on, which things like temporal motifs, temporal LPA and community detection. So we can have a look at, really embedding the history into the sort of queries that you're running, which hopefully some of the examples that we talk about will cover. The other question, obviously, is once you have an algorithm, we have the question of you're running the what, there's also the when. And then so given a time scale, we can run queries at individual points in your history over a range of times. So incrementing by, say, days or weeks over the course of years. We can apply a variety of windows to say, hey, look back over the last day as we increment through, or a set of windows. So you may say, I want to investigate what's happening on the order of hours as well as the order of years to see what's happening in the short term and the long term. And then the other nice thing that we're exploring is that given you have some, say, update stream, new information coming in, what you may want to do is just continuously requery and compare how your graph is changing, and then feed that downstream to some other systems. So what this looks like in practice is something like this. I don't know if this is probably terribly unreadable from the back, but hopefully it's all right for those online. So the general gist here is we create a new graph. I'm going to open a file. I'm then just going to loop through that file and add edges, specifying here's the time, here's the source and the destination, and that will get my data in. I can then query that at any point in time. In this case here, with this query, we're saying go from the start of the data to the end, walk 1 day at a time. I have a set of windows I've defined, so 1 day, 1 week, 1 month, 1 year. Run a clustering coefficient and return me a data frame. So that comes back like this, which has, I think there's, so there was 9,391 different views of the graph that were run via this query. And then we can plot that out into a nice graph, which shows me over this 6-year period, here's how the clustering coefficient has changed for these different window sizes. So they're kind of, hopefully what this encompasses in comparison to the prior example is that with a small amount of code, you can quickly get your data in, you can run a variety of algorithms over time, and you can do lots of other nice things that we can get into, like composing multiple algorithms together and getting these all out. So hopefully this makes some of the research in this area a little bit easier if this is what you're working on. And with that, I'll hand over quickly to Naomi that can stop me from talking about the fluff of Raphtory and talk about some actual examples of why it's useful.
So in this section of the talk, I'm going to go through some examples of how Raphtory has been used and what kind of analysis you can do with Raphtory. So one of the early ways Raphtory was used was taking this idea of just applying the static graph algorithms and metrics that we know and love, and being able to do that over these different times and timescales, which Ben alluded to. And one example of this from a couple of years ago was some work that Ben did with and the Raphtory project with Mishcon Derea, who are a legal firm interested in this space. And the data that they had was it was 400 years worth of legal documents and the citations that they made. So in our network here, we have each legal document as a node, and the citation where someone's taking a document as a precedence for a current case as an edge. And the interesting part of this data set and study was, as well as the long timescale covering both pen and paper documents in 1600s up to PDFs, is that it also covered documents worldwide, and they were interested in how does this sort of hubs of influence change over time. So it's covering a long history where there's things like colonialism and then independence movements, also forced like globalization. And one of the algorithms that they were quite interested in was looking at the size of the largest connected component of the graph, seeing how connected does this graph become over time, specifically looking at the proportion of nodes in this largest connected component. And so this black dotted line here is what you'd get if you were interested in the size of the largest connected component, just when you consider the graph as a growing aggregate graph, which tells a fairly intuitive story of everything just gets more connected over time. But then when we look into these smaller window sizes, like windows of 5 years or 10 years, it actually starts to capture some dips that are otherwise hidden. Like around the 1960s, there was quite a huge dip in some of the windows around periods of independence movements where people were being emancipated from colonial powers. And then also the rise of the internet in later years in 1980s, where suddenly everything's becoming online. So in this paper, there's quite a few examples of how changing the window size gives you quite different insightful results. Another way that Raphtory can be used is exploring the history of individual entities and things in a complex system. An example for this was some work done with by Rachel Chan at Pometry, who's in the room, and Rachel was interested in studying a company's house, where there was a huge data source available where you have the directors of different companies that are registered at company's house. And you also have a lot of temporal information in there. So when they formed the company, when it was dissolved, how long the different people were directors. And a finding that came straight away was that there was some individuals with huge numbers of companies. I think that the person with the most companies was something like 50,000. Which is not quite usual, but when we dug into looking at how long each of those companies lasted, whilst there were some that lasted around 2 or 3 years, the vast majority of them were formed and then dissolved in less than a week. And then when we looked into the name of some of the individual and the company involved, it turned out they were all operating out of this busy, bustling address over in Finchley, and involved in huge money laundering, gangland stuff. So when we shared about this on Twitter and put it out there, someone suggested why not actually look into some of the recent COVID support schemes and the potential nepotism involved in there, where companies were awarded these huge contracts, and resulting in situations like this where a really poor quality PPE was given out, but paying absolutely through the nose for it. So in this setting, we had the same form of the graph where you've got it's a bipartite graph of directors and the companies they formed, but you also have the weight of what percentage control they have of that company. And we've also got a lot of annotated information about events in the company and these potential change points. And an example we found in here was there was a company called Clandeboy Agencies, who shipped millions of items from Cambodia, like masks and various PPE. And these were originally bought per box for about £1,000, but found to be totally unfit for use, and then were being resold at £5 at auction. And then shortly after this, the company mysteriously changed ownership to some offshore companies with some very suspiciously sounding names like Clady Group and Clady Holdings Limited. But there's a few more examples if you read the blog post in there of these. And then finally, I thought I'd talk about some work that I'm doing at the moment, which is kind of putting these workflows together of being able to explore individual history of entities, as well as moving this through time. And the case study for this is looking at dark markets, and specifically the Alpha Bay market and the transactions people had around that. So Alpha Bay was a website where people could buy drugs, arms, or other illegal services. And there's many similar ones out there. And it was formed in 2014, but then busted in 2017 by a huge Europol investigation. And in this network, we have users sending money to each other. This is all done in Bitcoin. So people can either be buying things from Alpha Bay or making transactions between them. And we have all the people who interacted with Alpha Bay and their transactions as well. And we were looking specifically for temporal motifs. And the type we're looking for is what we mean by motif is a sequence of 3 edges in this case, and we limit those to the ones which complete within 1 hour, so an hour difference between the first and last edge. And the sort of patterns that might be revealing by looking at the motifs is, for example, in this lower bottom corner here, these being all possible motifs of that type. We have ones that might represent pairwise trading between users, so back and forth patterns like that. There's motifs where there's a fanning out, so one node sending money to two different nodes, which could be a user making batch purchases. It could also be something like a mixer service splitting transactions. And the other sort of main class motifs is what you might think of as funneling, where the edges are all incoming to one node, which could be a vendor receiving different orders or a recipient of a split transaction. So when we counted these motifs in the Alpha Bay dataset, we found that by far, by quite a huge order of magnitude, the most common motif was this fan out motif, which could be possibly people buying things in sequence. Going down, I think it was 1 or 2 orders of magnitude is the single direction motif between 2 nodes. So someone sending repeated transactions to another user. And then the next most common is these all incoming motifs. So our next question was, how does this break down over time? So we looked at the motif counts of these different types, like this blue fan out one, to more motifs just on 2 nodes. And these dotted lines are when Alpha Bay was formed and when Alpha Bay was dissolved and busted. And an interesting thing that we found first is that this huge spike in the number of motifs comes down long before alpha bay is shut down. And as far as you know, it's not like people were aware that it was going to be busted. So this is something slightly mysterious. And another interesting part of this was that when you split down the composition of different motifs, so we break those down into the motifs on 2 nodes versus the fan out ones. We start the network in the sort of pre-alpha bay era just with motifs on 2 nodes, these green and blue ones, where it's possible peer-to-peer transactions going on. But then this very sharply changes to motifs that are all like fanning out of money. But rather than returning to that 2-node motif stage, this fan out motif remains present long after alpha bay is shut down. So finally, a little to where this work is going at the moment is whether when you look at individual nodes and the motifs that they participate in, is it possible to find some of these nodes with similar motif patterns, which could be motifs which play a sort of similar role in the network? And it turns out, I won't go too much into this plot, but we applied different clustering methods to the nodes where we look at the motifs that they're part of, and it seems that they do group together in a quite sort of salient way. And our next steps were interested in can you identify different perhaps services in the network using their motif patterns. So I'm going to pass over to Ben, who's going to, I guess,
pinch the clicker.
Who's going to talk about some of the next steps of Raphtory.
Hold on to it. Yeah, so just to finish up, we thought it might be worth just going over some of kind of like what's next for the tool and different ways that you can get involved if the things that we've talked about are somewhat exciting to you. So kind of the first bit is like what's on the roadmap from the, I guess, the kind of technical side, which is that we're currently rewriting a lot of the storage layer and enabling being able to store these graphs nicely on disk so that you can pull back chunks of them. The kind of idea here is that we can get to kind of billions of nodes being able to be worked on your laptop by pulling back individual views of the graph when you do your windowing and so on, which is really, really exciting. And there's a lot of people that are working on this in the background at the moment, so this should be out very, very soon. The other side of things is that we're constantly looking on expanding out the algorithms API. So we're reworking a good chunk at the moment. It's vertex centric for those that have seen some of the bits of Raphtory at the moment, and we're looking to change that so it's much more expressive. And one thing that we're really excited about is this idea of graph projections. So at the moment, you can do things like look at the graph at different points in time. We're also interested in doing things like multi-layer networks so that you can kind of swap back and forth, and doing things like automatic null modeling. So you say, okay, I've got my pipeline of algorithms, now run this with a variety of different null models and tell me if my results are actually important. And so kind of making all of that as easy as possible. So hopefully these are sort of things that are interesting, but what I'd like to get out of today, if anyone has any ideas, is are the sort of features that you find in Raphtory kind of useful to you? Do you think, oh my God, it'd be great if they had this? Very much, I'd love to have that conversation. And on that point, how you can get involved, the first is obviously it's on GitHub, go and have a look. You can pip install it and give it a try. If that's your cup of tea. If you have got some feedback, whether that's positive or negative, you want to just come and shout us, come and join a Slack or drop me an angry email. If you think that the research that Naomi's done is cool and you want to get in on it, I guarantee first tier conferences will accept your papers or your money back. And we're actually just upstairs. So if you're ever around, want to grab a tea or a coffee, talk about graphs, it's what I do all day, every day. Hamza, my co-founder, sitting at the back, trying to hide away, is also very excited about graphs. Would love to chat about them. So please do hit us up. With that, I say thank you very, very much for listening. Thank you very much for coming. And do you have any questions? I don't know if do you want to share this mic and we can run this around?
Amazing to think that 6 or 7 years ago, we were just looking at a whiteboard saying, wouldn't it be great if we had some temporal graph software? Questions from the audience, please.
Hello, thank you very much for the presentation. I was wondering, with respect to what you showed at the very beginning, do do you have an idea of what performance improvements you've had between the way you were doing things before and the way you're doing things now with Raphtory for a similar task, like let's say windowing, the way you were doing in the example?
Yeah, so I think that the ways that we were trying to do it before, it was just it wasn't plausible. It wouldn't run. Even on some sort of that's kind of so it's difficult to know what kind of the order of magnitude difference is when I couldn't even get it to work. I mean, to give you a flavor perhaps of some of the improvements we've been seeing, when we've done a paper on Gab, which was some of the similar analysis to what we was talking about with the legal data, and that would take all night to run on the first version of Raphtory on like a big machine. You can now run that on your laptop in about 5 minutes. So we're like, and then I think some of the newer versions that we're working on are scaling that data up by orders of magnitude, and the time to run these algorithms is coming down by one.
It's also fair to say that when we thought about doing it in Network X, it would take about 30,000 separate graph runs.
Yes, so yeah, I can't remember the exact, I think it was 68,000 different versions of the graph are being generated, which is a lot, but it's kind of like one Raphtory query. So that was very much like that. Yeah, it's we're very proud of how it's going along, and but we're always striving for more. Half our conversations just us shouting at each other that things aren't going fast enough. So that's like yeah, we're trying to do our best there.
Thank you for this talk. I don't work on temporal network myself, so this question might be stupid. So I'm wondering, comparing to other type of temporal data in general, if the temporal network data had something like particularly difficult to deal with, or make it different from other type of temporal data?
I think the problems that well, actually, I don't know, this is a question for yourself as well. We probably have different views on it, but for me, the problem is that the graphs tend to have certain distributions that make them a bit of a pain in the ass to deal with, and I'm sure a lot of people in this room have experienced that a little bit. And when you have this kind of temporal aspect to them, there's you have a lot of questions of, how do you break your data up? Do you look at, your neighbors at certain points in time? Do you look at your neighbors over across whole periods of time? Do you do this based upon, the most recent queries that users have? Do you do it around the sort of algorithms that they have? So there's a lot of those kind of discussions we're trying to work on at the moment of, like, given a variety of different stuff that a user wants to do, what's the best way of storing and applying it, which at the moment I don't really have an answer to. I hopefully will it'll continue to improve. I think that just networks make everything hard, and much easier to deal with tables. But yeah, that's what hopefully we're trying to solve. I don't know if that's a good answer or not, but I don't know if you have a version of that.
So I was thinking that similar lines of graphs in general, especially I think there's the two main challenges, just the large graphs, hard to work with, the hard to distribute, that can be a challenge in itself. But on specifically the temporal networks front, I think the thing that I found was when I was first getting into this, my idea of a temporal graph is just different snapshots of the network through time, but then realizing quickly there's all these different notions of a temporal graph. Of some people might have contact networks where you've got durations on the edges, got people who just have like streams of events going on and things, and finding some sort of common way of dealing with that, and not having to say totally rewrite an algorithm again based on a specific notion of a temporal graph is a challenge. So.
Yeah, so I guess as an example of that, Iman, who's in the chat, was working on some temporal LPA algorithm. We're asking this question of, like, well, I know that my communities look like this at time 1 and my communities look like this at time 2, but kind of, how did they get there? So building out an algorithm where you say, okay, well, I know what I looked like 5 time steps in the past. I know what I look like 5 time steps in the future. And so how can I kind of use the influence of those times to affect now? And so there's a lot of, like, API, or, like, how do I interact with time in a sensible way, which you start scratching away at, and the kind of the whole wall falls away. You're like, oh shit, well, I need to restart again. There's very little kind of research in how you interact with time in a nice way, I guess. Like, I think a lot of people are like, okay, I've got this use case and I need to get this done. So trying to generalize that is a lot of fun, hitting your head against a brick wall.
Of course, there's always, in every graph, there's that one node which has half the neighbors attached to it.
Yeah, I mean,
it's really ruining your.
I think the first version of In the first version of the alphabet motifs, there was one node that had a core running for like 10 minutes longer than everyone else. We're like, okay, we definitely need to fix that. It's like not great.
I guess touching on Naomi's point about about the different the questions open to both of you, but about the different types of networks, whether it's contact or whatever. Does Raphtory want a specific type of network, or can it as in when you feed the data into Raphtory, does it need to be in a specific format, i.e. contact or snapshot, and or can it be any kind of format specifically? Temporal network.
So I think there's one of the things that we're really kind of big on is that given you have data in some format, you might want to model it in a variety of different ways. And that kind of drastically affects the sort of algorithms that you can run on it and the sort of analysis you can get out. So as a kind of example of this, one of the other blogs that we have is on NFT analysis, and we were looking at cycle detections. So what we're finding, normally what most people do is they have a wallet-to-wallet network, and you look at sort of following the money through. Instead, we built a bipartite network where you have all of the NFTs on one side, all the wallets on the other, and the edges were like, this wallet purchased this NFT. And then you could go inside of the NFT and say, okay, well, I'm just going to look through the chronological list of purchases. And then if I see someone twice, I know that there's a cycle. So now all of a sudden I can, with like an O(n) algorithm, find cycles of length 1,000 in like almost instantaneously. So a lot of the time, the kind of modeling side of things, which we've hopefully put a good amount of effort into, actually allows you to do a lot more analysis, and it kind of almost becomes part of the pipeline of like, how do I actually look at my data? But to answer your question, no, you can put it in there however you like.
Can I ask a quick follow-up? Is that okay? Then, okay, specifically, say you have a static network that you want to then feed, you want to kind of reconstruct temporally, or do you need to put it in a specific, like, say you have an edge list and then you need the timestamps, and is that it for Raphtory essentially to build that?
Yeah, pretty much. You just need like a data and kind of when it happened. So you can put things in that kind of one snapshot, or you can maybe have like, one base layer of the network where you say, this is my graph structure, and then I'm going to append a load of events to it, or maybe a load of extra properties. So you can have 5 different data sets, which are all adding kind of their own features to the graph, and then do some analysis on that afterwards. That's the goal anyway. I mean, like, but if you give it a try and you're like, this is dreadful, like we can fix those things. Let us know.
Very quick question. Can I integrate, or is it possible to integrate Raphtory with graph databases such as Neo4j, for example?
Yeah, so you can pull data from it, you can push data back to it.
Is there an integration, or is it like I exported the data from the database?
So for direct interaction at the moment, we have a couple of SQL databases. We're working on a direct Neo connector, but there's no reason why you can either get your data out in like a CSV or JSON format, and effectively all you need to do is say, push it into Neo into these tables. So it won't take long to get you set up for that.
You're not digging into your own talks.
I just have a very quick question. This is related to the motif work. Actually, first, thanks for the nice presentation. Is there a reason why you consider motifs of 3 edges only? Is there an interpretation, or did I miss? Maybe I missed that point. Or...
No, so that we was so 3 edges was, I think, probably the most that we could do in terms of, we were looking for enumerating sort of all different possibilities of a motif of that number of nodes and edges, and I think 3 was the most we could do for that. But I think it could be interesting to look at if you were, say, looking for a specific motif, like if you had a pattern that you knew was associated with some interesting or dodgy behavior, you could probably search for that specific pattern. Yeah, we just went for that so that we could get all different possible types. Yeah.
Oh, sorry, actually.
Yeah, go.
There's a little bit of a combinatorial explosion problem. Like if you look at the 3 node edges, we were measuring literally trillions of them, which is better than other software can do anyway. So if you're getting trillions of 3 nodes, once you get to 4 nodes, I wouldn't even like to think how many, I don't even know what that number's called.
Bigger than a long.
Bigger than long. Yeah, actually, we did run out of memory on the institute type we were using at one point. Yeah, so it's big counts already for 3 nodes.
Yeah, actually, I've worked with cycles as well, so I know how computationally intensive it can be. But I was wondering if there was an interpretation as well. But yeah, thanks.
And now it's time to hand over to you. So, thank you very much, Naomi. So, somewhat awkward handover. Shall I grab that? So, our next speaker, Anastasius, come from the Turing Institute, and I'm looking forward to this one because I'm an old school statistician at heart, and I've done a lot of work on autoregressive models in the past, so love to hear about
That's
it.
interesting. Thank you for having me here today to present. So I'm Anastasia, I'm a postdoc at the Alan Turing Institute, and I'm currently working on a project which is in collaboration with the Office for National Statistics, who are providing us the data. And this is an early stage work with the Office for National Statistics, so it has been highly motivated by the data that we have. And it's a joint work with Gesine Reiner, Mihai Cucuringu, who are from the University of Oxford, Department of Statistics, Victor Mirinhos, who is a lead analyst for the Office of National Statistics, and Francois Lafont, who is also from the University of Oxford. So this is the outline of today's presentation. I'm going to present the data that we have at hand and the problem that we want to deal with for the data. And then in the second section, I'm going to discuss about the way that we're approaching the problem and the modeling framework. Oops, sorry. Then I'm going to briefly present some simulation results and some preliminary results of from applying the model on the real data, and some concluding remarks in the end. So starting with the data and the problem setup. So we have ultimately business-to-business transaction data. These are data that are held from the Office for National Statistics, and they're capturing transaction flows in the UK from January 2015 up to July 2022. So it's ultimately multiple time series of transactions, which transactions are occurring between SIC codes. And for those who are not familiar with what is an SIC code, SIC stands for Standard Industrial Classification. So these are codes that are used by the government in order to classify companies according to the nature of their business. So ultimately, this data can be represented as a directed network with time-varying edge weights. And I'm going to use an illustration to explain that. So just a small illustrative example, we observe this data frame of time series between SIC codes. And the first two columns are comprising an edge list, from which edge list we can then construct a network. And then we have the time series observed on the edges of the network. So under this construction, the key two assumptions that we're making is that the network has a fixed structure through time. So there are no edges emerging or deleting through time. But what is changing over time is the weights on the edges. And the problem that we want to deal with is to analyze this multiple time series utilizing the network structure underlying. And the goal are to perform prediction of future transactions, but also potentially to do change point detection under disruptions. And our approach is inspired by Knight et al. And Zhu et al., who have developed a network autoregressive models for networks with a fixed structure, but the time series would be observed on the nodes rather than the edges, which is in our case. So we're adapting this approach in our problem. And the key assumption of developing the GNAR-edge model is that the values of each edge at some time point t depends not only on past values of the specific edge, but also past values of the neighboring edges. And just to specify here what we mean by neighboring edges, one stage neighbors for some edge ij are all incident nodes to edges to nodes I and j. And this is just an illustrative example of one stage and two stage neighbors. So for edge 1, 2, one stage neighbors are all the incoming and outgoing edges from nodes 1 and 2, and then respectively going further down to higher stage neighbors. Two stage neighbors are the neighbor edges of the first stage neighbors, and so on. So very briefly, some notation. So by XD, we're denoting the time varying adjacency matrix. So it's ultimately, we express that as the element-wise product of a binary adjacency matrix and a weighted matrix, which is changing over time. And the reason why we have that is to make explicit that we have a fixed structure of the network, but we have the time varying edge weights. And by N1 of ij, we're going to denote the neighborhood, the one stage neighbor edges for edge ij, and respectively NR are the NR of ij are the R stage neighbors for edge ij. So the GNAR model for a maximum lag L and the maximum number, maximum neighbor states RL is the following. So the first term is ultimately the autoregressive part. So sorry.
What does GNAR stand for?
G.
Next slide.
Yeah, I'm just, it's a brief, it's a generalized network autoregressive model. Yeah, sorry for skipping that. So we have the autoregressive part as depicted by the first term, and we also have we are regressing also on past values of the neighboring edges to this to edge ij. So they're respectively the parameters alpha are capturing the standard autoregressive parameters, beta are capturing the network effect, and we have the normalizing weights, which is the reciprocal of the number of R states neighbors for edge ij. And we are adding Gaussian noise with mean zero and varying sigma square. So this is ultimately a special case of a vector autoregressive model, and we can use OLS to fit. In this section, I have only included the simulation that is more interesting because it's related to the data. So we have we have simulated data according to the sizes that we have observed in the real data. So we generate a simple Erdős-Rényi graph with 86 nodes and 6,858 edges. And we generate the time series on the edges of the generated graph. And the timestamps that we have are 90, as we have in the real data. And we're specifically generating the time series from the GNAR model under two alternative simulation regimes that I present here. The first case is where we have the GNAR model with maximum lag of 4 and one stage neighbors as depicted by the arguments in the GNAR model that I have put down in the table. And then the second case, we consider.
Just remind me for the beta parameters, which is the lag and which is the.
How I have as arguments. Yeah, so ultimately this is corresponding to the maximum lag, and here we're denoting the stage neighbors. So alpha is the autoregressive.
I can't remember on the indices of the beta parameter whether the first one is lag or the first one is your R.
Yes. So it's indexed first by lag.
All right.
And yeah, and no worries. Yeah, please interrupt me when you have questions. It's so yes, the table on the top is showing the parameters that we're using, the true parameters, in order to generate the time series. And these are some results from these two alternative cases. The table on the right, on the left, is showing the estimated coefficients and then 95 confidence intervals for the first case. So we can see that it's quite close to the truth, and also the 95% confidence intervals are enclosing the true values that we use to generate the data. And similarly, for the second case, we had a similar performance, overall performance with estimation pretty close to the true values. Now some preliminary results on the real data. The data size is as similar as I explained for the simulations that we had in mind, the real data when generating them. So we have 86 nodes, 6,858 edges, 90 timestamps for the edges varying over time. The manipulation that we do before fitting the GNAR edge model is that we do first order differencing, and also we divide by the standard deviation of the training sample. And we then fit the GNAR edge model, what I have included in this presentation, at least today. We fit the GNAR edge model for data up to June 2022. and predict the next timestamp, which is the last timestamp that we have so far, which is July 2022. And I'm presenting two alternative cases here. In the first case, we have a fixed one-stage neighbors assumed, and we have varying sizes of lag. And then for the second case, we have a fixed lag of size of 4, and we're exploring various neighborhood stages. And this is to evaluate the performance in predicting the future values. And we're using the RMSE here for that as an evaluation. So the figure on the left is showing how the RMSE scales for when we increase the lag size. So we can see that there is a downward trend when we showing a better performance when we're including more lag sizes. But what is most interesting is the second case, I believe, because it's showing how the changing R-stage neighbors are having a better, showing a better performance in the modeling predicting when including the neighbors rather than when not including. So on the x-axis, you can see that there is a case where we have a 0, so we have no network effect encoded in the model in that case. And we can see for 2 or greater stage neighbors, we can have a better prediction performance when including them. Also, this slide is to illustrate the fitting of the narrowed model. Yes?
Why we include the one step, it goes up, but then it shoots down. Why does that happen? One stage step neighbor, and then it goes up, and then it shoots down.
Yeah, this because we have to make two decisions for this model. First is the lag size, and second is the stage neighbors here. So it can be, so finding the optimal between the two might be the case. So in this case that I'm presenting here, I have the lag of 4. So it might be that, because I could see that when increasing the lag, I would have a better performance. But yeah, overall, it's at least good that we're seeing that there is a downward trend when we include more and more stage neighbors. Yes?
Why did you select July 2022? Is there anything special about the month of July 2022 that you selected?
It was the last timestamp that we had in the time series. And also this is the very first result. So we have in mind considering other periods as well, because we have the COVID situation as well in there. So this disruption might be a disruption, which would be interesting.
Could you offer a comment of the size of the error improvements? The magnitude?
Yeah, so here, as you can see, the scale, you mean the scale of the RMSE here. So it's not very, we cannot see a drastic change in the size of the RMSE. And a reason why where my intuition for that is because we have an almost complete graph in that case where we consider 2-digit codes. So the network effect is not very clear for this case at least. But just to clarify again, for the SAC codes, we can have 2, 3, up to 5-digit level SAC codes. So the higher that we go, the lower the aggregation is. So we observe a graph with more nodes and less edges. So a clear structure might be there. So this is why I believe that we see this scale.
I'm really liking this work, but I'm really surprised by that going up at the first stage, because you've got more parameters. Technically, it would be the same model if you set all of your betas to 0. So you see what I mean? If you're including the one stage neighbors, if you just set every single beta to 0, it should be the same answer as predicting the 0 stage neighbors.
So for the case where there is a jump,
case where R equals 1, as far as I can see, if you set every single beta to 0, it would be exactly the 0 stage model.
Yes.
So it should be an identical RMSE if you optimize everything correctly.
Yeah, I'm not sure that I get it fully now.
Do you want to talk? If you want to move on, you can, and I can ask this again.
Yeah, we can have a conversation.
All right,
maybe.
let's go back to the All right. So if you pop back to your equation, this one, that one. If you set every single beta to 0,
yes, it would be
exactly the same as the 0 lag model, right?
Yes.
And that's an option for your optimization.
Mm-hmm.
So if your optimization of stage 1 is getting a higher error,
Mm-hmm.
it's not perfectly optimized. There's better parameter values available, because it can always,
Yeah.
at the very least, achieve the value of the lag before it.
Mm-hmm.
So I don't know whether that just means your optimization hasn't converged completely, because I
Yeah.
didn't quite get how you were fitting these, because I guess the standard whole limited approach isn't going to work, right?
Yeah.
So
It might. Yeah.
it seems that you're not quite getting the exact optimization when you've got
Yes.
a lot of
Yes.
parameters.
Yes. It can be something that could, I don't know, from your experience as well, it could be something that can be attributed to the lag size, also specification maybe, I guess. But there are definitely more things to explore in terms of the application on the real data. And
I hope
yeah.
you don't interpret that as a hostile question. I'm just, very interested.
No, I'm very, actually, this is why I'm presenting today. I wanted to have your feedback. It's an early stage work, so it's good to have suggestions and ideas at this point. Yeah. So, and this slide is just to illustrate the fitting of the GNAREDS model. So here I have picked 2 edges because there are 6,000 of them. And in the black lines are the real time series, and the red line is showing the fit of the model, of the GNAREDS model on the real time series. The reason why I have picked this particular 2 edges are also because we're seeing this change in the size of the transactions after here. It's after September and December, respectively, 2019. So this is, I'm just illustrating now this because in order to also explain why we're motivated in looking into a change point detection framework furthermore, because it might be the COVID effect that we are seeing this change. And as some exploration, we have considered a sliding window of K of length equal to 55 months with lag size of 4 and 1-stage neighbors. And this is in order to explore how the estimated coefficients change over when considering these different sliding subdata frames with a sliding window. And here are the alpha parameters, where we can see a change after April 2020. But what is most interesting are the beta parameters that are capturing the network effect, where we can see that there is a change in the scale of the parameters as well, which is not very prominent here in the alpha parameters. So this is why we are motivated in order to go further and look into a modeling framework for the change point detection. And just to conclude, the findings so far, we have an overall good fit of the model with good prediction performance. Some simulations validate the model. Sorry, the simulations validate the model performance, and investigation shows that there is possible presence of change points. And as future work, we want to perform more extensive simulation studies. And the second point refers to the SAC codes that I mentioned earlier. We want to explore the bigger size networks and how the different structure of the network affects the results in the GNAREDS model. And finally, we want to also develop a formal framework for change point detection. And thank you very much.
Thank you very much, Anastasia. Questions from the audience, please. Ben.
So I just pick up really on Richard's point, I guess. So I think you said you did the estimation by ordinary least squares.
Yes.
So I mean, my feeling would be maybe some of the points, such as Richard pointed out, which I agree with, could be solved if you fitted a different method of fitting. So like OLS is terrible for anything that's not linear. It's not going to be the unbiased. It's not going to be minimum variance. So I wondered if you might consider doing a sort of holdout estimations, sort of test train might work, or doing some kind of maximum likelihood type thing. But I think that would probably make your estimators more, I don't want to say consistent, but make them more evidently usable.
Mhm.
I guess. I just don't think OS works. I think that might be a problem.
Mhm.
But
Thanks for the suggestion.
I love
yeah.
the idea in the model and the work. It looks
Yeah.
really good.
Okay,
Yeah, it
thanks.
looks really good.
Yeah, it's highly motivated by the data that we observe. So
Yeah.
yeah, it's. Thank you for the suggestion.
More question.
Yeah, thank you very much for the wonderful talk. I was just wondering, when it comes to kind of increasing the number of sort of hops away that you're getting, the number of neighbors and so on, what's the kind of like performance or like runtime that you get for increasing? And do you think there's kind of like a, obviously if you're saying say at 2 nodes, it seems very similar to sort of 3 and onwards. Is there kind of a point where you're like, actually, you know what, there's no point of adding any more information because it takes 10 times as longer, but it's giving us like a 1-point improvement?
Yeah, I haven't done. Yeah, that's a very good question. Actually, it's quite computationally intensive as we increase the stage of neighbors, and especially when we have large networks, as we have in that case. I haven't done an exploration, like a formal exploration of the time, what is the burden that we have to deal with in terms of the time as we increase. But definitely, yeah, we need to find this optimal case where we have also done some exploratory preliminary analysis, which we hope that will inform the modeling part in terms of specifying the number of neighbors to consider, states of neighborhoods to consider, and lag size. But yeah, as you say, we don't want to increase complexity and also computational time when to implement the model. Yeah.
No, lovely. Thank you very much.
Thank you.
Oh, great. Oh, goodness.
Thank you for the presentation and for the model. I think in the direction of simplifying the number of parameters, I think we have explored other 2 dimensions in this kind of autoregressive models for networks in dynamic networks, which is one is kind of selecting nodes and edges based on the features of the nodes, so that you have some kind of selection in the space of the topology of the networks. So I don't know, the degree of the node could be a method to like simplify the number of neighbors of a given time series. And the other one is a discrete autoregressive model where you have like not whole potential time in the past, and you can select some time in the past to actually choose the next steps. So these are other kind of papers in the literature that you might consider.
Yeah,
for
thanks.
yeah
For that. You can let me know after the.
Yeah. So it wasn't much of a question, I guess. I guess the question is, have you considered this?
No, we
option?
haven't.
Yeah.
We haven't considered that far. Yeah.
Thank you.
Hey, thanks for the presentation. I just wanted to ask a follow-up about, I was curious why the performance on the error doesn't improve when you include like the network structure as well. And like you said, one of the reasons could be because it's highly connected. But I was also wondering if, and that could be fixed if you disaggregate more, perhaps, right, at a higher length of code. But is it also the case that most of the transactions or most of the edge weight is in certain parts of the network, or is the edge weight sort of distributed evenly across all the nodes?
Yeah, I haven't looked into that.
So when you do the edge weights, do you divide by the standard deviation of all the edge weights, or just along the edge, the time series standard deviations?
No, for the training sample.
Yeah.
Yeah.
So it's for all the edges overall, right? Or I don't.
It's edge specific, not for all the edges. No, it's for each edge, the standard deviation for each edge.
Okay. So then at the end of the day, so then the data that you have in the training at the end of the day should be fairly evenly distributed, right?
Yes.
Okay.
Yeah.
All right, cool. Thanks.
So I think one of the baked-in assumptions here is the correlations as to lag will all go in the same direction. There's a lot of research nowadays on signed networks, whether a relationship represented by a link is an antagonistic or a friendly relation. I wonder if you've considered that, like if you could just annotate links as positive or negative links, it might, without unduly increasing the number of parameters, if there was some way of knowing whether a link was a positive directed or negative directed.
What would be the interpretation for this? Because I'm not aware of this.
So in a social network, it would represent whether you are friendly or hostile to each other. In a trade network, it might represent whether my production going up helps you or hinders you. Because we can also see situations in a trade network where I do better, therefore you do worse because we're rivals.
Yeah, sounds interesting. I haven't thought of that. So this would require prior knowledge on that in terms of the
perhaps prior knowledge, or perhaps you could look at the history between pairs of nodes across a link and say, in general, is there a positive or negative correlation between them? And therefore we could assign them positive or negative.
Yeah.
Obviously, you greatly increase your parameterization there, but
yeah, I see.
It could be.
So it would be ad specific.
You just say this is a positive link, this is a negative link.
Yeah.
And then you can flip signs and maybe things will come out better.
Yeah, it's an interesting. Sounds a very interesting direction. I will.
A lovely piece of work. Any final questions before we hand over to the next person? Last questions. Okay, well, I can see our next speaker. Thank you. Thank you very much.
Thank you.
Are you R&D, Joshua?
Handle this a little bit here.
Yeah.
Hello.
Yep. So Joshua's from UCL, and you're going to talk about networks of innovation.
Yes.
I believe.
So my name is Joshua Becker. I'm from the School of Management at UCL, which I have to spell out because I just realized I didn't put my name anywhere in these talks. So if you ever want to find me later, just do Joshua Becker UCL into Google. There's also a very famous Joshua Becker who has like a minimalist podcast, which I think is cool, but not me. Okay. So I'm a little self-conscious because I'm not really going to talk about time today. I'm going to talk about networks and talk about things that happen over time in networks. I'm not a methodologist, so I'm a social scientist. So this will all be fairly high-level stuff. There's no math on these slides. And this project, most of my research, I am a researcher in collective intelligence, which is a very kind of broad term that means whatever you think it means. And I specifically study particularly how communication in groups impacts belief accuracy, things like forecasts and estimates. I'm not going to talk about that today. This is actually a side project that I started when I was a grad student doing some work with Andrea Baron-Kelly, who's going to be here in the afternoon. I was really hoping it's going to be here now. And it sat on the shelf for a long time. So I'm dusting it off now and trying to get it published. So I'd love to hear any comments you have on it. And being from, well, not originally, but now working at a business school, somebody already would have interrupted me with a question by now. So please feel free to ask questions throughout. And I'll just repeat the question back into the mic so that people on Zoom can hear it. And we don't have to pass around the mic until the end. Okay, so I'm going to talk about the diffusion of innovation. And one important research question on the diffusion of innovation is why suboptimal strategies spread at the expense of superior alternatives. So for example, in the competition of technology. And this is particularly important because when adopters don't only care about the thing that they're adopting, but also care about what their peers adopt. So I'll talk through some examples there, like this clicker. There we go. Okay, so imagine you're a railroad firm in America in the 19th century, and you're trying to decide what kind of rail gauge to use. And there are various different technical benefits to different rail gauges. Don't ask me what they are, but there are. But what's also very important for these countries as the network grows more national is being compatible with their peers, right? So they're balancing this need for compatibility with peers with whatever technical advantages one particular design or another might have. Or imagine you are someone who uses software on occasion and needs to code your own stuff. Maybe some people here in the room are doing some coding and you have a preference because obviously R is better than Python. But maybe you also care about sharing code with friends and peers and collaborators, and you're spending all day trying to get this code, and eventually you just give up and start using Python because it's what everybody else is using. So it's another case of balancing, your preference and maybe some objective technical benefits against the need for compatibility with peers. And today I'm going to be talking entirely about objective benefits, but you can ask me to speculate on subjective preferences at the end. Okay, so one of the things that Andrea's work, as well as others, has shown is that when people are doing this, trying to just make this decision over time, wake up in the morning, what coding software am I going to use today, or what new Rails are we going to install today? Over time, I'm making this decision, balancing between the objective preferences or the objective benefits and the need to coordinate with peers. Over time, the population will spontaneously emerge on a shared strategy, and that strategy is just simply termed a convention, right? So when we call it a convention when everybody just spontaneously starts doing the same thing, driven by this need for compatibility. And we see this, of course, in things like language as well. It's just all over social life, but in the case of technology, it really matters which one we end up using. Yes? So the question, the comment really is that the same could also apply to science as in Kuhn's paradigm. I think, yes, I think this concept can apply very broadly in a lot of different social contexts. Conventions is a very generic behavior. The more complicated the behavior gets, the more factors are going to impact a person's adoption decision. So I'm going to stick today with some fairly simple examples, such as the railroad and the coding. Even coding starts to get complicated. Something like scientific paradigms is going to introduce a whole lot of other incentives. Yeah. Dragos.
In the example of either railroad or coding, could there be either potentially or empirically cases where you have multiple optimal or optimized societies? So one group would be dedicated to Python coders, another group dedicated to R coders, and never the two shall meet.
Yeah, so you could imagine a case where you emerge not on one single convention, but on two different separate conventions. I'm not going to look at that today. It's certainly an interesting question. But so for my purposes, I would just pick one of those sub-communities and say, okay, I'm modeling this, the emergence in this particular sub-community. So I'm just going to kind of break that down and isolate it. But that's an important question. And if the reviewers do ask me about this paper just went under review, I'll run some models to test that. I think that should end up producing the same results as what I'm going to show today. Okay, so we have these conventions, and we want to know, why does one strategy emerge and not another? Okay, so why does one strategy win and not another? So the answer is historic chance or path dependence, right? Essentially, some strategy just by luck gets an early advantage, and that strategy becomes more popular over time. Now, that's sort of the generic result when there's no payoff benefits. So let's say we're talking about it's not just the compatibility, but we care about the payoff benefits, and we want to ask, will the best one win? So one answer, very optimistic answer coming from economists who really want to argue for efficient markets. They study ergodic models of this, which is giving infinite time. In infinite time, eventually, the population will converge on the best solution. But empirically, that we have examples of that not happening. And then if you look more carefully at those economic models, you see that eventually, infinitely, you get to the best solution, but it's not necessarily the first solution to emerge. And the first convention to emerge can stay the convention for a very practically long time. So we actually really care about what is the first convention to emerge. So then this question is, okay, so why then still we have to ask this question of, why do some things spread and not another? Historic chance isn't really a super satisfying answer. So of course, in advertising and marketing, there's a ton of research on why some innovations or technologies are very successful at spreading. Like maybe they have a really good marketing campaign, right? Maybe they have a really good advertising campaign. But all of these things can apply equally to the best solutions as well as the suboptimal solutions, right? And one
effect that is really commonly shown in a lot of different research is that when a central node promotes some innovation, they can spread it faster and farther, right? So central nodes are upheld as these like heroes in marketing and innovation diffusion. It's like, oh, look at how good they are at spreading solutions, right? But this still can apply just as equally to the good solutions as the bad solutions. So I'm still left wondering, because I am a collective intelligence researcher, I want to know how to design systems that are going to, reliably spread the best technologies and behaviors. I want to know what at the structural level in the system is going to make it more or less likely for the best solution to emerge. So that is the question that I'm going to ask today. What structural factors impact the likelihood that a network or a market or an industry will converge on the optimal convention? And because central nodes have turned out to be such an important feature in the diffusion of innovation, and they're something that has a big impact on network structures, we all know, I don't have to sell you on that. I'm going to look particularly at the effect of central nodes. And we can operationalize that by looking at network centralization. So you have either networks that are characterized by the presence of disproportionately central nodes, like one person who's way more popular than everybody else. We're going to call that a centralized network. Or you can have a network where everybody's got the same centrality, the same degree centrality, same number of friends or connections or peers. We're going to call that a decentralized network. And we can just kind of, continuously go between the two so that we can range centralization from, low to the highest possible value. So that's what I'm going to look at. I'm going to look at whether centralization helps or harms the optimality of emerging conventions. Now, intuitively, it could go both ways. So central nodes, well, they're often very helpful for the spread of innovation. So, and they also have a lot of exposure to the network. So they may be able to kind of learn about the good ideas and then spread them. But on the other hand, they're just really influential, and they tend to kind of live in these echo chambers where everybody around them is being influenced by them. So their central nodes may end up inadvertently spreading their own solutions and making those really popular before they even get a chance to learn about the more optimal solutions. Okay, so how am I going to study this question? How am I going to test how network centralization impacts the optimality of the diffusion of innovation? So what I'm going to do is I'm just going to take a fairly standard formal model, so game theoretic model of diffusion with coordination. So coordination is the term for just wanting to match my peers, right? We're trying to coordinate in the sense that we want to coordinate the same railroad gauge, or we want to coordinate the same coding language. And then I'm going to take that model, I'm going to simulate it in networks with varying centralization, partially because I'm not particularly good at math, so I'm going to run these in simulation, and also because the mathematical solutions are the ones that are those ergodic models. So I'm going to basically run the simulation until it reaches an absorbing state, and then I'm going to say, all right, which solution won? So it's a computational experiment. Okay, so I just want to talk briefly about the model. This is just a pure coordination game in game theoretic terms. So if you're to set it up as a 2x2 game theoretic matrix, you can imagine the columns represent, what player 1 is choosing, and the rows represent what player 2 is choosing. We've got strategy 1, strategy 2, strategy 3, so on down to strategy n. And what I'm studying is a game where if you don't match, so I choose strategy 1 and you choose strategy 2, we both, I guess it doesn't like my talk. If I choose strategy 1 and you choose strategy 2, try something different this time, not keep doing the same thing over. If I choose strategy 1 and you choose strategy 2, we get 0 payoff. This is just a very, very kind of simple version of this scenario to try to study the underlying dynamics. Okay, so examples of this kind of behavior are technological standards, communication protocol, right? If I have a telephone of a certain type and it can only communicate with that same type of telephone and nobody else has it, that telephone is useless to me because I have nobody to call, right? Or if I'm using a messaging app that I really like WhatsApp, but I go back to America, nobody uses WhatsApp, so it's useless there, right? Screw threads, metric systems, railroad gauge, I already mentioned. So I'm really interested in these technological standards because that's where, we talk about objective value, things like cost or price or efficiency, or with messaging apps, maybe, security or other concerns, but also behavioral norms are going to fall under this kind of model, right? Potentially scientific norms. I think that gets into pretty complicated territory. linguistic conventions. Not really an example where maybe we wouldn't say English is better than French, but it's an example of this type of coordination behavior, just to sort of illustrate what's going on there. Okay, so the model that I'm running based on this game, very simply, I've got a network. I'm just randomly creating a network with, in this particular case, I'm running it in R, which is very slow. So I think I'm using something like 1,000 nodes, but that really doesn't matter for the outcomes. So each node, and that's reasonable if you're looking at like a market or an organization anyway, 1,000 nodes is a reasonable size. Each node starts with a randomly selected solution. And today I'm going to show you results on basically an infinitely large possibility space of solutions. So essentially every node starts with a unique solution, but you get the same effects even if you just do 2 solutions. They just get a little bit smaller. Nodes update, choosing the best response to peer choices. And then you just kind of keep running this line 2 until it reaches an absorbing state. And best response is just the payoff of a solution multiplied by the probability of a success with that solution, which is equal to the proportion of my neighbors that use that solution. So just very simple expected value. Okay, so that's the setup. I'm going to jump into the results now. So the first thing I want to look at, this says centrality, but it should say centralization. The first thing I want to look at is the effect of centralization. And what I find is that centralization reduces optimality, but decreases speeds. Was there a question or did you just want the figures? Okay. Yes, so I am quantifying centralization by the Gini coefficient. You can quantify it by any number of things. It's, I don't have the results here, but I've played around with it. It produces similar effects. I like the Gini coefficient. And I'm running 2 different versions of centralized networks just because they don't get necessarily the full range of centralization. And I just wanted to make sure it's robust. So one of these is just using a graph degree sequence where I'm basically generating my own degree sequence and using a random network generator to just generate an arbitrary degree sequence. That's the gray one, gives me a nice range because I can give it whatever Gini coefficient I want. And then I'm also using the Barabashi, Albert, the growth network, cumulative attachment, preferential attachment. So that one, that's what I started with. It only kind of got me a shorter range, and that's why I went to the longer range. So you get pretty much the same thing. So when you're fully decentralized networks, they're not perfect, but you're converging on the optimal solution about 70% of the time. And the more centralized the network gets, the less and less likely it is to converge on the optimal solution until over here, this particular network is converging on a suboptimal solution, let's say 90% of the time. Yes. Richard.
How are you getting different degrees of Gini out of the Barabashi algorithm?
By changing the strength of the preference for attachment. So there's a parameter that determines how much I'm attracted to people of high degree, and the stronger that is, the more centralized it gets. No. Yeah, this is I should call it a Barabashi-Albert inspired preferential attachment algorithm. It's a power power law type network. Power law type network. Yeah. I have not, and here's why it never would have occurred to me to do that, because I don't know what my rank 2 neighbors are doing. If I know what they're doing, or if I care about matching with them, which is kind of one and the same, then they're my rank 1 neighbors. But I would imagine we're going to get to the end. It's basically be a super simple, intuitive explanation for all of this, and it'll suggest that it's robust to all these various different considerations, but I haven't actually run that, so I don't know. That's the disadvantage of not doing the math, is you don't really get general results. Was there another? Oh, yeah, in the back. How many choices are they picking between? How many choices are they picking between? For these figures, they're picking between, well, they only know, this is a good question. So they only learn about choices by observing them from peers. So when I start off with a randomly selected choice, I know my choice and I know all of y'all's choices, but I have no idea what people are doing, over in Oxford or back at Penn, right? Because this is a diffusion thing. So I'm learning about solutions by encountering them in the network. Yeah. So they're choosing between whatever they know about, which is, and then of course, even if they knew about something circulating elsewhere in the network, because none of their peers are using it, it's not really a choice, because again, if none of my peers are using this technology, this railroad gauge, then it's useless to me, because as much as I might like it, it offers no value if it's not compatible, because if I have a telephone and I can't call anybody, it's no good. Now, okay, so we see that they're getting less optimal as they get more centralized. They're also getting faster, so this is kind of cool. We like when diffusion is fast. So we see that centralization decreases optimality, but also increases speed. So this may imply a speed optimality trade-off. I'm going to give you a preview. It doesn't. I'm going to get to that in a couple slides, but that's an important piece of this. I want to unpack a little bit some of the mechanisms behind the centralization. It's more or less what you'd expect. So first, we're just going to look and check to see that, in fact, central nodes are more likely to introduce the winning solution. So what we do is we just take all the possible degrees that exist in the network. So there are nodes of degree 10, there are nodes of degree 20, there are nodes of degree 30, and basically we're going to generate a likelihood ratio between the actual degree distribution, which is what you'd get if people were all equally likely to introduce the winning solution, which they are if they're starting randomly, right? Central node is no more likely than a peripheral node to have the best solution. But if that likelihood ratio is above 1, it means they're more likely than chance to introduce. And as we see, very peripheral nodes, this is very low degree, so the lowest possible is 10, and this is just one snapshot network, a centralized network. They're much less likely than chance, and as you get more central, you are more likely to introduce the winning solution. Not particularly surprising, but just letting us know that under the hood, it's behaving the way we would expect it to. Now, here's a little bit, I'm going to dig a little further into the mechanisms now, and I'm going to say not just is the central node more likely to introduce the winning solution, but then I'm going to look at the quality of the solution under different regimes. So what I'm doing now here is I'm plotting by centralization the average payoff of the eventual convention under 2 regimes. One, under the case where there's suboptimal coordination, and another under the less likely case, the increasingly less likely case of optimal coordination. So in the case of suboptimal coordination, the more centralized the network gets, the worse the winning solution gets, pretty much as we'd expect, right? Because it's less and less and less likely to converge on the best solution. But under the case of optimal coordination, so it's in the event that it converges on the best solution, that solution offers a higher payoff. And it's basically showing us that in highly centralized networks, it has to offer that much more of an advantage to overcome that influential effect of the central nodes. So it's showing both that central nodes are more likely to introduce the winning solution, and that as a result, it's making it harder and harder for good solutions to spread because they're just so loud, everybody starts doing what the central node did. And then finally, I just want to look at just by the degree of the node introducing the eventual convention, the more popular was the person who invented it, the lower quality it is. So there you go. And that's in the, remember, I say invented, but this is because of that coordination effect, right? The coordination effect introduces all of these network effects. If we're diffusing innovations where I don't care what my peers are doing, it's a completely different story. And that's a lot of innovation. I'm looking at kind of a niche case here, a niche but very important case that drives a lot of our world. Okay, so now I promised I'd look into whether there was a speed optimality trade-off. So we might think that because central nodes make things fast, but they also make things worse, we have to choose between a very slow emergence of convention. And remember, lack of coordination is inefficient in those stages before we have a convention. I have a hard time matching my friends with the messaging. So we really want to get to that state of being able to easily use this technology or this communication protocol. But we also want to make sure it's the best when we get there. So in order to test that, I look at some other networks. Now I'm forgetting about centralization. I'm just looking at network density in decentralized networks. And as network density increases, so a dense network is one where everybody knows everybody. A sparse network is where everybody only knows a few people. as networks become more dense, they become both more likely to converge on the optimal solution until a perfectly dense network is always going to converge on the optimal solution very trivially, because in a perfectly dense network, everybody can see everybody. So the first person to update is going to adopt the best solution, because in my initial conditions, everybody starts with a unique solution. So nothing has an early advantage yet. That goes lower than 100% as you reduce the number of solutions, but density always increases the probability of optimal coordination and vastly decreases the speed. This is just the average number of updates per agent. So that's something like, you know, a 45% decrease in speed, although it's hard to interpret magnitude in simulations. Okay, so that's the model, that's the question, that's the results. Let me tell you now why I personally am interested in this. So I do care a lot about innovations. I do care a lot about market efficiency. I do care a lot about network centralization because, as you probably know, networks tend to be very centralized. There are really, I've never seen a decentralized network. There's always some people who are more popular than others or more influential than others or who talk more than others. So this, and there's a reason I say that, because this result is actually consistent with other research on collective intelligence showing that in general, centralization undermines all sorts of collective decisions. So I call this a collective decision because we have a population that is essentially doing a kind of equilibrium selection. There are all these different innovations circulating. Any one of them could be the dominant convention. We don't all have all of the information. We only really know what we learned through the network from our peers. So it's distributed, it's decentralized. It's not a decision in the sense that somebody's saying, oh, let's make this decision, but it's an emergent collective decision in the sense that initially they didn't have a convention and then it selected a convention, and it is or is not the best solution. So we see here that centralization undermines the optimality of collective decisions when it comes to equilibrium selection for emergent conventions. It also undermines the optimality of other collective behaviors. So I started off by talking about how I studied belief accuracy forecasting. When you have a group of people talking, network centralization in various forms reduces the accuracy of the eventual average belief. This is in the wisdom of crowd space. And that centralization can come out literally by who's communicating with whom, as I was doing in this case, but we also see in discussion groups, if we map centralization as how much you talk, that produces similar effects when we use the same underlying models. So this to me is really a kind of joins a broader set of research showing that network centralization is not so great for collective intelligence. Any questions or discussion? Yeah. Oh, thank you.
Absolutely excellent presentation. I suggest this effect where the person with the loudest voice in the network produces a terrible solution. Surely it's the Elon Musk effect.
You can call it that. You could, yeah, I suppose so.
Right, loads of questions.
Oh, and it's not by virtue of being central. Central nodes can also produce good solutions. Remember, this is a statistical effect, not something about, you know, individual human nature. It's really collective. Yeah, not because they're popular. Yeah.
A question I have on the slide you had where you this one, yeah, the next one, this one here. You say centralization doesn't necessarily lead to the optimal solution, right? Is there almost like a two variable kind of game or kind of exploration where you have payoff, but you also have efficiency? Because the more centralized, the more typically the more efficient you get to some kind of solution, right?
That right, more let's say more quickly.
Quickly, yeah.
Say more quickly. Centralization is fast but suboptimal.
So is there almost kind of like I guess in economics, if you say supply and demand, you have this kind of trade-off of efficiency but optimal.
So I guess the point of this is that I would argue it's a false trade-off. It's only a trade-off if you think we must live in a world with centralized networks. What this kind of suggests to me is in something like diffusion of innovation, we should be trying to either decentralize the networks, which is not necessarily possible, or think about ways that we can counteract these effects. So
do you not say, I guess, do you not want to balance between the two, speed and
well,
optimal?
I mean, I guess if I were, could rule the world, I would say, no, we don't need to balance between them. I'm just going to get rid of the Elon Musks, and I'm going to put everyone kind of in a decentralized network and make it really dense. And then we have fast and optimal. Now this, I'm being a little bit cheeky with this because that's not super practical. And one of the challenges with this is that you can't actually go manipulate a network. So I'm really more identifying a problem than I am identifying solutions here. But at least I think it's important to, in thinking through the theory, it's just important to keep in mind that trade-off is not an inherent feature of coordination. It's more an inherent feature of our networks since we tend towards the centralized networks.
But would that not be an inherent feature of human coordination?
I suppose so. Yes, I suppose. Yeah. And in which case I would still say, I don't have the answers yet, but there, you can imagine policies or centralized bodies who are going to try to aggregate information and make it easier for people to learn about alternatives. I'm not really sure what the solutions are, but I am an optimist, so I'm not going to settle just yet for that trade-off as inevitable, even if it is common. Yeah.
Thank you.
Hi, thanks. So obviously centralization can be done with any centrality measure.
Yes.
So the other one that would seem obvious here when talking about innovation would be something like betweenness centrality, which presumably would look very, very different. So do you have any intuition if you were looking at centralization of betweenness centrality, what the patterns would be that you would find here?
Does betweenness centrality correlate with eigenvector centrality?
No, I mean, eigenvector or PageRank, those are all going to be refinements of degree, but betweenness is potentially very different. The fact that you're using a preferential attachment model here might mean that you wouldn't actually see too much variation in that because you probably don't have clusters.
There's really no,
Yeah, so you don't have clusters. So if you have something that has clusters, then betweenness centrality would potentially be doing something very different. And then
even if you don't have clusters, it can be quite different.
Right. But presumably with the generative model that you have here, you may not see too much variation.
No, I think you're right. I think I'm going to hesitantly say yes. Intuitively, you'd expect similar effects. And here's the really simple intuitive underlying model. Anything that can systematically give some things an early advantage and is going to introduce this kind of effect because it's basically making it from the get-go less likely. It's basically, if it's random, if it's not correlated with quality or optimality, it's basically saying something has a chance for early advantage. It's not correlated with quality, which gives the chance that something gets lost peripherally in the network or whatever the system is that gives advantage. And if betweenness centrality could do that, but I'm not really.
The issue, I think, with betweenness centrality is that would be a person or a node that's torn between potentially different coordination, right? They're being pulled in different directions.
Well, because you talked about two clusters with that would I can say two clusters will emerge on two different conventions.
Right. So then nodes with high betweenness are going to be the ones that bridge across those clusters. Right. So if you have clusters and high betweenness nodes are going to be torn. And then
the question is whether they're more likely to introduce one of the nodes into or one of the solutions
which
into
is where it comes to innovation.
Which I would think,
right.
yes,
So that's
I would think
yes. And stuff like that. Right.
I would think yes, but I want to say hesitantly because sometimes intuitions can lead us wrong. Yeah.
Thanks.
I think I'm out of time. Yeah.
Have to do the experiments.
Right. The computational experiments. No, not at all. No. Yeah. And all my R code is on GitHub if you want to rewrite it in Python and run it. Yeah. Do we have time or?
I think we've just run out of time.
Okay.
So the question was really, I like the work. I'm not sure I like the model. Do networks not form because of innovation?
Sorry, did they not what?
Do networks not form because of innovation? So your formation, your network growth model is totally independent of.
That's true. I'm treating the networks as fixed and static.
If I'm France, I'm going to build a railway because I'm next to Switzerland or whatever. Whereas I'm Spain, I might say, well, I don't like France, so I'm gonna buy a different gauge, which is what happened. They built a different gauge railway.
Well,
So could you incorporate your Yeah, so I think the independence assumption here is going to be quite critical to sort of real world results. I think was my comment.
Right, and the question is, so the question for any potential complicating factor is whether it will lead the results to go in a different direction, whether it can somehow restore optimality. Intuitively, I would not expect so, and unless it's somehow correlated with quality, right? They can bring that back in. But yeah, I mean, I would say that's an example. If you go to American railroad networks, that's going to be an example where the network is fixed because they're operating in different states, and it's just a spatial network. They can't really change who their neighbors are over time. So I could see something like communication protocol gradually changing over time. But for me, in terms of choosing Facebook Messenger or WhatsApp, that's going a lot faster than my friendship network is changing. So I think it depends on the speed of the innovation versus the speed of the relationships. But again, the real question comes down to whether anything can restore optimality. So yeah, thank you. Good question.
I think we are out of time for questions. Thank you again.
Thank you all so much.
So our final speaker session is from Mary. Is this supposed to work with them? So
yes,
so this is an absolutely brilliant talk. I won't spoil it by saying what's going to happen. I really like this work. No pressure.
Yeah. So let's start with the easy thing.
Oh.
Totally failed. Yay.
There we go.
Thank you. All right. Okay. Hi, everyone. Yes, I'm Sylvia, and today I will talk a bit about characterizing color patterns on real spatial network through random walk. Okay. So, yes. So, why is it interesting to study patterns using random walk? So, I want to talk to you about a research story, because last year, two biologists come to us saying, okay, we have this very, very nice data set on plants, on root plant cells. So these are real cell networks where we have that the red cells are the more important, or they have a very important functional role because they are related with the production of root hairs. Okay, so they are very important for the plant, while the blue cells are not so important for the production of these roots. The gray ones are not interesting for this study. Okay, so they gave us these networks, and they asked us, okay, can you use these patterns, these special colored patterns, to give us some information, some like grouping the species, find relationship between species, which is not from something related with phylogenetic history, with evolutionary history, because tons of like papers in biology on this topic is related with study on DNA, study on evolution. And this is the very first step into like trying to work with networks and plants. So they gave us these very nice data sets, and they asked us to study the patterns. And we started very easy. So we started looking into red and blue cases separately, and we obtained some results. We were able to like ranking the species, finding some interesting correlations between them, and blah, blah, blah. But then they asked us, okay, really nice, but we are to convey this message to biologists. So could you do it with one measure? And we say, okay, yes, maybe we can. We can use in random walks. So during this presentation, I will talk about static networks, spatial networks, but using the power of random walks to explore these patterns. So the idea is that we shift from a local pattern analysis, so a structural pattern analysis, into something that is the study of through random walks permits us to have like this overall view of the pattern. So we can capture heterogeneities, correlations of colors, looking at only one measure. So what are the networks I'm working on? Spatial colored networks. So spatial colored networks are networks that are embedded in space. So the nodes are located in the space. So we have that adjacency are obtained from geographical adjacency of the nodes. And then we have labels, and the labels represent physical quantities that are interesting for us. For example, here we have the bottom maps of United States, and we have that red and blue represent something that we want maybe to measure, okay? And we can obtain the network from the real data set, and we have this, the fact that the distance are important, we have some stuff that are different from more general networks. So we have to keep in mind this. And then we have connected components of the same color that could be interesting for us. For example, this cluster here, or the very big red cluster, right? So we want to find a way to characterize this kind of patterns. And for this presentation, I will define this kind of connected component of the same color, clusters. Okay, so clusters is a connected subgraph of nodes where all the nodes share the same color. For example, here we have a big cluster, black cluster, but also, if you want, a white cluster that surround the cluster, the black cluster. Okay. So what is the time in my presentation is the interclass passage time. So the interclass passage time is defined as the expected number of steps a random walk needs to hit the color alpha starting from the color beta. And in this figure is like the expected time. This random walk needs to jump to the color orange. So any node is okay, it's fine. You only need to hit the orange, starting from a node of color blue, for example. Okay. So, and another, and we can use the interclass passage time to look at the distribution of interclass passage time to understand some of the structural properties of the clusters. But another measure that we can do is the mean first passage time, which is the average of the interclass passage time, but normalized with the same measure, but over a null model. And for my study, I only use a very easy null model, which is obtained maintaining the structure of the network fixed and only reshuffle the color over the nodes. Okay, really easy. And if you do this, if this is your real network, okay, with your real colors, you can see that this indicator has to be very similar to one when you have a very random pattern of color. Instead, if you have a more heterogeneous situation, more like correlated, spatially correlated distribution of colors, then your indicator diverge from one. Okay, so it's really easy. And this is, you can think on this like a matrix, because you will have all your, if you have, for example, only two colors, alpha and beta, you will have alpha alpha, alpha beta, beta alpha, and beta beta. Okay, so if all the four entrants of this matrix has to be similar to one, you can say, okay, we are very similar to a random case. So this pattern that I'm looking into is not very complex. It's not very heterogeneous. Okay. So applications. Let's start with the first one. This is a paper we are writing with the two biologists I mentioned before. It's a part of the study, and is about the resilience of these plant species under a parasite attack, so a random attack. So the original network is the one with the red and blue colors, and then we remove a percentage of nodes at random, and we obtain the attacked network. And then we measure the mean first passage time in this case and this case, and then we look at the difference between these two, and we put in the top position of this figure the plants that are more resilient, which means the plants that have not so many difference between the two mean first passage time. While in the bottom position, we have the plants that are like the more affected by this attack. And what we found is that some of the top positions are occupied by plants that are more recent in the phylogenetic history, which is not really straightforward when in the case of biology, in the sense that there is this idea that the more the ancient a plant is, the more has to be resilient because it's here from like a long time. But we found this, and this is like saying, okay, but maybe there are some like patterns, some roots that are like specially organized, as they can also be very resilient, also if they are very recent in the history. So this is a new, if you want, idea. And it's really interesting to use this in biology. Okay, the second case of study is always in the field of biology, but it's studying bacterial colonies on plants. These are two colonies of bacteria over a root of plants. This is one modified in lab, and this is what we can find in nature, okay? So the biologists ask us, can you please, these are the two real networks, spatial networks, like a slice, okay? Can you please help us characterizing these two? Because, okay, you can see with your own eyes that these two images are different, but it's not so easy to formally define that they are different, okay? So the first thing I did is produce the null model, okay? So I reshuffle the color. And then I look at the distribution of the interclass passage time. You can see two, this is the colony A and this is the colony B. And this is a snapshot of the network. And what you can see studying the distribution is that in this case, we have this very more probable peak with blue to white. What means blue to white? That means that the time a random walk needs to go out from a blue cluster to the white color, okay? And you can see that this means that the time is very low. So for a, like, I think it's 2. So you need like 2 steps to go outside, and then you have this very probable situation. And this is talking about the stripes. You can see here you have tons of stripes. So very they are from the model. They are residual, like something that they expect to have. But this is measuring this. And here instead you have that this peak is lower. So this is capturing the image. And then you can see also that the white to blue, so the time you need to jump from the white cluster to the blue is similar in the two situations. And this means that the important stuff is in the blue to white, okay? And this is true because the blue are the bacteria and the white is only the plate, okay? Okay, and then we can study the mean first passage time matrix, and we can obtain some information also from this, because if we look at these two entries, these are saying that the colony A is more similar to the null model than colony B, because look at this. You have this that are 1, and these that are more similar to 1 than these two, which means that if you remember, if you have that all the entrants of the mean first passage time matrix are equal to 1, you are totally in the null model. And this is something that we can recognize like with our own eyes if you want, because this is more similar to this than this. We see more heterogeneity here, okay? And last one is, I think the more interesting is that the mean first passage time here is very large, which means the time you need to escape from a blue cluster to the white is very large. And this is a structural, here we are using random walks, so time measure, to have a structural measure of the network, because we are able to capture in the fact that these blue clusters are very large. Here is smaller because we are not so many blue clusters. Okay, and the last case of study is about cities. Here we have a different network. We have street patterns. We can obtain polygons from these street patterns. They are our nodes. And then we have that each polygon is a node of the network, and adjacent polygons correspond to an edge. Okay, so for example, these two are connected and these two are connected. Then we we label the nodes according to their area, but we can do it for whatever you want. Income, I don't know, whatever you want, okay? So we study only geometrical stuff because it was easier in that case. Then we obtain the null model, as I mentioned you before, reshuffling the colors, and then we measure the mean first passage time and perform a hierarchical clustering. And here you can see the result for this hierarchical clustering for New York, Chicago, and Cleveland. And what we found is that these are only the counties. You have to imagine that we study for each county, each polygons, and then we do the hierarchical clustering. And the study of the mean first passage time helps us to detect the center of the city. So detect what is not the border of the city, because it's quite not a problem, but it's an open question in the study of cities. Try to understand what is the center of the city, not the one decided by the humans, but the ones that emerge from the growth of a city. So thank you for your attention. This is me, and this is my series of seminars, NetPlace. We are like PhD that runs seminars for PhD in network science and complexity. So if you are a PhD and you want to give a talk in our seminar, we're very happy to invite you, and thank you very much.
Thank you very much indeed. I'm going to take the chair's privilege and ask the first question here.
Yep.
So I really like the work. Can you pop up the slide with the bacteria colonies and that structure there? So if I'm understanding your procedure correctly, you're creating your, the one a little bit to the right, maybe that one, yeah. If I understand correctly, what you're doing here is you're like superimposing a grid to get your network.
No, it's not super. Yeah. Okay. It's kind of. There is a grid. Yes.
Yeah.
It's a lattice.
Your neighbors are north.
Yes,
south, east.
Exactly.
But that implies scale. And when we look at this, the first thing I'd say is that's got bigger blobs.
Yes.
Would you recover a similar distribution if you just made the grid on that one bigger than the grid on that one?
I have to try this. I have to start, because this is a very early result on this work. But the next step is to look like changing the scale of the and try to find if this kind of. I expect that, for example, this peak, I'm very sensible to this peak now because I can spot the presence of a stripe because it's like I can see this. But if I enlarge a bit the scale, I think yes. Mm-hmm. But at the same time, I think I could recover again the fact that here I have less blue clusters than there. So I think.
Also, I was really struck by this dip in the blue here. It's like there's almost.
There are some stripes also here. You can see this.
Yeah, but it seems like there's a passage time.
Yeah.
There's nearly
I don't.
No way. I don't know. That. It seems real unlikely.
I don't know.
Okay, I've hogged the questions.
Sorry, you know, with the cities.
Yep.
I mean, in the case of like the bacterial,
No.
As in, what my question is, in the case of the bacterial,
Oh, sorry.
no, go to the cities. But in the
Okay.
case of the bacterial, it's obvious what you're going to color. It's going to be species, right? In the case of the cities, what do your colors represent? Is my question.
Okay, we study only like structural quantities, so area, angle, and shape factor of the polygons, because okay, we obtain our network through the street patterns. So if like 3 streets form a polygon, a triangle, that becomes our node. So if you want buildings inside the city, and then we measure the area of these nodes, because we have the street patterns of all the cities, then we assign a color. But we also decided to have 3 major classes. So area larger than these are assigned with color green. Area with polygons with area between this and this with this color, and area smaller than this with this color. So 3 colors. We do like a distributions of the area. We look at the distribution of the area, and then we decided to divide it into 3 classes. And then we color the network. So you have to imagine this network, the city, colored with 3 colors. And then we look at the same measure for the bacteria, if you want, for the bacteria and for the plants. So we look at the pattern of color, which looks like segregated because the center of the city present, if I remember correctly, like smaller area than in the border. Okay, because in the border you have very long streets, very industrial factory and stuff like that. So you have plenty of space, but in the center you are more segregated, and you have the presence of this cluster, colored cluster of small area in the center. And when you do the null model, and then you compare the 2 ones, the presence of correlation emerges. Okay, so you can do the clustering, and you can find this. I just ran for 50 cities, and it continued to work, but let's see, I have more cities to.
Thanks.
Thank you for the question.
So then your nodes are blocks? That's
nodes are
like a block, like a section of
let's
land totally surrounded
look
by a
at this.
street. Yeah.
For example, in white you have streets,
yeah,
and in blue you have what is confined by the streets.
Sure.
So maybe it could be also a park,
sure,
or could be a series of buildings, right? Because maybe you don't have streets between.
And then you're measuring the mean passage time.
These are nodes, for
Right,
example.
right.
This is one node. For example, this is colored with color 1, if you want. This is colored with color 2 because it's a medium area, and this is colored with color 3. Okay. So
and then you're measuring the mean passage time, yes, on counties. Is that right?
No, I studied on polygons. Okay. So a smaller scale, and then I group the result by counties. So for each county, I study the mean first passage time, and then I look at the hierarchical clustering.
So for each county, you're measuring your
yes,
time. Okay,
yes. Because when we did for cities was a mess, in the sense that we lost a lot of information looking only at the large scale. So we decided to go to the counties.
But counties are bigger than cities.
No. Counties in American cities.
Chicago is part of Cook County.
I don't know. It's not the
census tracts. Oh, okay.
Sorry. Yes. Sorry. Yes.
Okay. Thank you.
Yeah.
That is clarified.
The neighbor.
Okay. Thank you.
I think the question back was first.
Thanks for the talk. Quick question about when you go from geography to these nodes and then color them. how sensitive do you think your results are to two things? One, how many divisions you make and how many colors you put, and where you put those borders? Because I must imagine it's fairly...
This is a very good question. And I think to make the work more robust, the study, I have to like change this number of color and show that the information remains similar. But it's pointless to have too many colors, right? Because it depends on what you want to, it depends on what you, okay. It depends on what you want to measure, okay? But you have to create like a discrete distribution of colors if you want to color in a, because otherwise you will have like a very diffusive, the presence of a very diffusive distribution of colors, so you cannot measure like anything because everything is different. So you have to, yes, it's a bit difficult to make this decision. So how many colors I use? So I didn't show you the work behind because I don't have the time. But we, for example, we decided to look at the distribution of the area, and then we found that there are some peaks, and we decided to put the colors at that point.
Okay. And just to make sure that I understand what center.
Yeah, because you can say, okay, but it's totally arbitrary, and you find something because you force the.
Sure, makes sense that you would have to pick something, and the center is essentially a bunch of small area nodes, right?
Yes, exactly.
All right, thanks.
Question. Hello.
It's about NetPlace. Is another organizer.
No.
Joking.
So thank you for this talk. It's very interesting, particularly interesting to me because it's somehow related to what I'm working on for now. I'm quite interested in this measure itself. So do you think this measure is kind of related to some other, for example, the average cluster size or even the average diameter of the cluster? Or, I mean,
yes.
Is there any particular use for, or why do you choose this as a measure of the difference between these patterns of the other ones?
The fact is that I think this is strongly related to the presence of cycle inside of a cluster. Because if a cluster is large, that means that it has to have cycles inside him.
Like a ring?
Yes, not a, yes, a ring also, but if you look, for example, okay, wait. If you look at blah, 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 this, okay? So this is a bigger cluster than this in the sense, bigger, I mean, deeper, because you need 2 steps to go outside, right?
Okay.
Because you have more and more neighbors of the same color as you nearby. So I think that to answer your question, I think that mean first passage time is related to structural properties of the clusters. So for example, the dimension, the size, the shape, because if it's a circle cluster, you need a ton of time to go outside. If it's a stripe, you go outside very easily. So the sense is that you can capture these structural properties using random diffusion. So you can run your random walks and you're done.
That's very nice and somehow related to my talk in the
nice
session.
Cool.
Thank you. Any last question?
Thanks for the great talk.
Thank you.
I was wondering if you had thought about any information theoretic alternative. It doesn't seem like you need it because your time-based measure is working, but I'm just asking because your work reminds me a lot of the approach taken for random walk-based community detection, like in InfoMap.
InfoMap, yes.
And so I was just wondering if you had thought about an information theoretic version, or if you think it wouldn't be as good, or if you just don't need it.
I use, for example, InfoMap. I at the beginning, I used InfoMap to try to find community detection here, but the problem was that, I don't know if it's a problem or not, but when I cluster the mean first passage time, for example, look at this, you want to look at the mean first passage time of this against this, and this. So you have to produce the hierarchical clustering, you need a distance, a distance matrix, right? Or a similarity matrix. But when I give this to InfoMap, then I always find like a only big community because of the intrinsic nature of the similarity matrix. So I'd like to use InfoMap, but in this specific case, wasn't the right direction. So I prefer to go for dendrograms and then try to capture something from that.
Makes
but
sense.
Yeah, I tried InfoMap, but yeah, I think in other situations or in other, for example, if you choose only one cluster of one color, then maybe you can use InfoMap to like explore the network as well. I never tried that, but it's a good point. Thank you. Okay.
Thank you.
Thank you.
Well, I've got to say that was, for me, that was an absolutely excellent start for brilliant presentations. The pressure is very much on people presenting in the next session to keep up this high standards. Naomi is telling me we do have food upstairs. Brilliant. So lunch will be served upstairs, and we're coming back at 1:30 for the start of the next session.
Let's start the after lunch session. So our first speaker is Hanli Son from Queen Mary. Hanli.
All right, thank you very much. And we're happy to have this opportunity to give this talk here. Since this morning, people basically talking about the data and the application. So I'm trying to, I don't know, either frustrate you or stimulate you by talking about some theory. So today I'm going to introduce our recent work called Triadic interactions induce blinking and chaos in connectivity of high order networks. So clearly there are several keywords I will need to introduce. What is triadic interaction? What is high order network? And later, like what is blinking? And this was a great collaboration with Filippo Radicchi, Eugene Kuth, and my supervisor, Dinitra Bianconi. So first, let's talk about high order network. So as everyone have already known, I mean, in this workshop, well, agree that a network is becoming a new paradigm to studying the interacting system, like in either in nature or in society. And traditionally, the network is consisted of nodes and links. Links, which means they only encode the pairwise interactions. But in recent years, people have noticed that the pairwise interaction is sometimes insufficient to capture many real-world behaviors. So many new models, which is called high-order network model, which consider the interaction beyond pairwise interactions, has been proposed. And there are several of them. For example, the hypergraph, simplicial complexes, and the one we're going to mainly talk about today, called network with triadic interactions. Actually, in the recent study, the high order network has been used in many scenarios. Sorry. And for example, in epidemic spreading, people have considered the high order interaction among these individuals, and many new phenomena has been discovered, like a discontinuous transition or bistable regime, etc. And the high order network has also been used to model the brain network, and the synchronization on network has also been extended, generalized to high order networks. And also you observe this new phenomena like explosive transition. So these are usually the hypergraph or simplicial complexes model. And the following two is in some sense a different type. For example, the synaptic interaction and the interaction in an ecological network that includes the triadic interaction that I will introduce in detail afterwards.
And if you want to know more about higher order network, there's a recent review, not review article, but the article published on Nature Physics talking about the physics of a higher order interaction in complex system. And this is a new book of Janice Strabianconi on higher order networks. So if you're interested in this topic, you can check this out. So apart from this general introduction, let's move on to the network with triadic interaction. So what is triadic interaction? These are two examples. For example, in this synaptic interaction, like in a brain network, you have this situation, like on the right-hand side, there are two neurons. They're communicating or transmitting some signal via the neurotransmitters. And there's a third cell, it's called glia, is able to manipulate this interaction between the two neurons. It can either enhance interaction or it can suppress the interaction between these neurons and like enhance the neurotransmission or cut the neurotransmission. And this is in a brain network, in a neural system. And in ecological network, you can have something similar. For example, in panel B, this figure, there is a three-way interaction, means that 1, 2, 3, 4 are for a different species in the ecological system. And the connection between those are some sort of interaction between these two species. And you see in the panel B, the third species could interact with the could change or could affect the interaction between species 1 and 2. It can either have a positive impact on their relation, or it can have a negative impact on the relation. So these are two examples of triadic interaction. So actually, the triadic interactions are a general type of interaction in nature, but they have been only studied in a small ecological system in this paper on the right-hand side mentioned. So here, we propose a higher order network model to study the role of the triadic interaction in shaping the macroscopic network properties. So now let me introduce some details of some features of this triadic interaction network model. So first of all, this is a triadic percolation model. And later we will introduce more what is the percolation and why we want to include this. So first of all, there are several features of this proposed model. So first of all, this model is a higher order network formed by structural interactions and triadic regulatory interactions. So first of all, higher order networks is higher order interaction because the interaction involves at least 3 nodes. You have 2 structural nodes that interact with each other, and there's a third node could affect the interaction between the 2 nodes. And so you can consider this network is formed by structural interactions, like these blue nodes and the red structural links, and also the triadic interaction that a node can act on the links. The second feature is that the triadic regulation or interaction can be positive or negative, means that it can both either enhance the interaction between 2 nodes or suppress this interaction. And here we make it clear that what is the role of the like a suppression or enhancing. So an active link requires at least 1 active positive regulator and no active negative regulator. So basically it must receive at least 1 positive message and receive no negative message. And the third feature is we consider bound percolation on in this framework, which means the links are deactivated with a probability Q. And the last feature is the regulatory interaction takes place on a lower timescale than the structural interactions. And this kind of motivated by some real-world observation, which means that the regulatory interaction determines which links are active based on this rule. And this is a slow dynamic. And the structural interaction determines which nodes are active via the percolation process. We will explain in detail afterwards. It's a fast dynamic. And with all these features, in the end, I will show you that the triadic percolation, a triadic interaction, turn percolation into a fully dynamical process. So let's move away a little bit from the triadic interaction, and I'd like to introduce you, or explain to you what is percolation theory, if you're not familiar with this area. So the percolation theory is in general used to evaluate the robustness of a network against random failure. So here we have a network like the red nodes are in the giant component and the green nodes are not in the giant component. I mean, this is a simple illustration of the idea of the percolation theory, let's say. And next step, we randomly damage some links with a certain probability, and it will change the connectivity of the network, and it will change the macroscopic topology of this network. And then next step, the size of the giant component changes. Right. So why this model can, the percolation theory, can use to evaluate the robustness? Because it is like sort of a common belief, or everyone believes that, and also have a lot of evidence for that. The existence of a giant component in a real system is a requisite, as a necessity for a dynamic process to happen on a network. So you can imagine if you have a road network or have a flight network, that if everyone is almost interconnected and you can, sorry? So this network can be functioning, but if a large amount of nodes or links are damaged, making most parts of the network are isolated to each other, and it will make this network not functioning anymore. So the percolation theory wants to predict when this network fails or when the giant component disappears. So the previous description is just like a user natural language. And here we can try to exploit it mathematically. So mathematically speaking, the links are removed with the probability Q equals 1 minus P. Also, it's equivalent to the links of the network are retained with the probability P. And we are looking at the order parameter, we call order parameter R, which means a fraction of node in the giant component. And we observe a phase transition. Of course, this is on the infinite network limit. You have a phase transition, and there were two phases. We call it percolating phase and non-percolating phase. So in percolating phase, you have a non-zero value of R, which means there exists a non-zero giant component. And in the non-percolating phase, the R equals 0, which means you only have an infinitesimal. The largest component is the size of it is infinitesimal comparing to the whole network size. And there will be a critical P or critical Q equivalently, that where the phase transition happens. And on the right-hand side, I show you a phase diagram of this percolation process. So you see that in this case, when P average K equals 1, above 1, the R becomes non-zero, and below 1, the R is 0. So that means P equals 1 over K average is a percolation threshold for this model. And this is a simple auto-shriening network with every degree K. So in general, how do we calculate the critical threshold PC where this percolation transition happens? And we can develop some simple theory for that. I'm not going to explain all the details in this theory, but I'll show some results. So first of all, we can introduce a new variable S called the following a link, we reach a node in the giant component with a probability S. And you can write a self-consistent equation for S. And after you calculate S, you can use S calculates the R, which is the quantity we're interested in. And it's just like a standard procedure. So if you look at the first equation about S, you will see, well, S equals 0 is always a solution. And when you move to the percolating space, means you have a non-zero solution for S, and that's a non-zero solution for R. You just want to know when this non-zero solution emerges. So you see the first equation on the left-hand side is S, on the right-hand side is a function of S. So you can plot them together in one figure. You can obtain the 3 following figures. So when P smaller than PC, you only have the solution 0, which means in the end, the R will equal 0. And above PC, you will have another non-zero solution. And at criticality, that is when this non-zero solution emerges. And you'll see in this case, just the right-hand side function is tangent to the linear function at 0. So you use this, you obtain the critical threshold equals 1 over K average. This is for the auto-shriening network. And we find this transition is continuous which means when you increase P, the other solution emerges continuously from 0, not suddenly emerge somewhere else. So this is about the theory of percolation and how do we calculate the critical threshold. And so this is a percolation theory on a simple network, simple pairwise network. And there are also the development of percolation theory on high order networks. And there are some new interesting phenomena, like you have discontinuous hybrid transition, or you have multiple transition, or you have bistable regions. So this is about the crash course about percolation theory, and we're coming back to the Triadic percolation. So after introducing the percolation, you may understand better of this model. So basically, you can determine the status of the network using this following iterative algorithm, actually 2 rules. So first of all, we find the giant component, and only nodes in the giant component are active. This is a percolation process. And the second step is we deactivate the links based on the rules we introduced previously, like it must receive at least 1 positive message and no negative message. So the second step will be the regulation procedure. And you can see on the right-hand side, it's a simple diagram showing this procedure on a very simple network. So I need to point at these. So these blue dots are nodes, and these black squares are links. So first of all, and the green arrows are positive regulation, and red arrows are negative regulation. So first step, this is the initial condition of this network. And next step, you will see these 2 links are deactivated because they are negatively regulated by these 2 nodes, right? And next step, these 2 nodes will be deactivated because when you do the percolation, you will see these 2 nodes are not in the giant component anymore, so they are deactivated. And which will cause the deactivation of this link, because this link is positively regulated by this node. So he failed and he failed. And when he failed, this node failed, and this node failed, and this link failed again. So basically, you have this dynamical procedure. By the way, this diagram is a deterministic case, and in general, after the regulation, the remaining links will be deactivated with probability P because we are considering a percolation model. But in any case, the important observation is that if you see the status at t equals to 2 and t equals to 4, you will see the status of network are exactly the same, which means as the dynamic goes on and on, the status of the network will oscillate between a finite states. And that is why we call blinking the title of this paper, because the size of largest component will change periodically or chaotically. And we also developed the theory of this triadic percolation. So actually, this theory is quite easy to understand. So you may remember that first 2 equations are almost the same as a standard percolation on simple network I've introduced before. And the only difference, major difference, is the last equation of PL. And the PL is actually the regulation procedure. It determines what is the probability you retain a link in the end. And of course, we included time index in this percolation equation because it is a dynamic process. So in the end, we can simplify this equation in the right-hand side form. The order parameter at time t is a function of PL at time t minus 1, and PL at time t is a function of the order parameter R at time t. So you can play with this dynamic by iterating again and again and see what dynamic goes. So the property of this map can be studied using cobweb plot. And this equation can predict the phase diagram of this triadic percolation. And theoretically, this critical point of this phase diagram can be analyzed by calculating the Jacobian at these critical points. So this is a simple illustration of the cobweb plot. So you see we have 2 equations on the right-hand side. And if we want to iterate it, we just give it an initial condition. We give PL at time 0 and use this. We can calculate R at time 1 and use R at time 1. We can calculate PL at time 1 and then R2, PL2, etc. So we can graphically show this in this so-called cobweb plot. So we start from here with the initial condition PL0, and we got R1 and PL1, R2, PL2, R3, PL3, etc. And in the end, in this cobweb plot, you will see, in the end, the value of R will only oscillate between these two values, right? Which indicate this end up at a period 2 oscillation. The R will oscillate between two values. So we can compare this cobweb plot with the actual time trajectory, or you can call it time series. So we plot the R as a function of time. So on the left-hand side, you see this is a period 2 oscillation, and on the right-hand side, it is indeed a period 2 oscillation. But if you change the parameter, you can have something different. On the left side, there's no periodic behavior anymore, but it becomes chaotic. And on the right-hand side, the actual time trajectory, it indeed shows a chaotic behavior, chaotic oscillation. So here we try to plot this result in a different form. So we plot it in a phase diagram, or you can call it orbit diagram. So when you change the parameter, you can see a very fruitful phenomena, including, for example, here is a discontinuous transition at this point. And here you have period 2 oscillation, and this is also period 2 oscillation. And here you have period 2, period 4, period 8, etc. And in the end, chaotic oscillation. So this is like a route to chaos. So with this mechanism, it will turn percolation into a fully dynamic process, which display a period doubling and the route to chaos. So we want to compare. We also compared this oscillation, this triadic percolation, with a standard percolation on this scale-free network. So on the standard percolation, you simply have a continuous phase transition on the left-hand side. And on the right-hand side, if you consider this triadic interaction in the percolation process, you have a very interesting orbit diagram, display this period doubling and route to chaos. So the red plot is a theoretical result, and the blue one is the simulation. So you see that this triadic, this route to chaos, or this chaos, is not only something that exists only theoretically, but you can actually observe this in the simulation. And also we play with this model on some real networks. So this is a mouse brain network with a little bit more than 1,000 nodes. And we can also observe this periodic and chaotic oscillation of the order parameter. So in the end, there's another scenario which, if we only consider the positive regulation, not the negative regulation, and we find that the dynamic will always converge to a steady state, and it display a discontinuous transition. Sorry, how much time do I have? 3? Okay. So, so in the remaining part is basically about the discussion of this dynamic mathematically, that's why we have chaos, why we have periodic oscillation, why in the case without negative regulation, we only have steady states. It's an analysis about that. So I try to quickly go through this. So basically, it's not a very, mathematically not a very difficult thing, because we can write the equation in this kind of iterative form, and we can further simplify this in this form, like R at time t is a function of R at t minus 1. And this is basically a one-dimensional map that has been quite extensively studied in the dynamic system. And we can have a fixed point solution, a stationary solution can be written in this way. And we want to see if the stationary solution is stable or not. So we can do this linear stability analysis. So the idea is around the fixed point, I give the value a small perturbation, and I want to see if it goes away from the fixed point or it goes back to the fixed point after iterations. And turns out that this stability highly depends on this derivative or Jacobian of this map at that point. So when the absolute value of the Jacobian is greater than 1, then the fixed point loses stability. And so clearly when j equals 1, this is a critical condition. And for j equals to positive 1, it represent the discontinuous transition, and when J equals to -1, it indicates the emergence of period 2 oscillation. And it's in the book of dynamic system is always called flip bifurcation. So you use this result, or use this theorem, we can analyze the sign of J by explicitly writing the expression for the Jacobian. So in this case, if we don't have the negative regulations, we will see that J is always positive. So which means I can only reach the criticality at J equals 1, which corresponds to the emergence of discontinuity. And when we include both positive and negative regulations, you can have either positive or negative Jacobian, which can bring you either discontinuous transition or the periodic oscillation. All right, so in conclusion, in this work, we review the microscopic effect of the triadic interaction on high order networks. And there are actually two separate results, not separate, but two results. First is if the high order network contains both positive and negative regulations, it will turn percolation into a fully dynamic process, and the order parameter undergoes period doubling and the root to chaos. And if you only consider the positive regulations and no negative regulations, then the percolation process always converges to a steady state, and the phase diagram will display a discontinuous phase transition. In the end, this framework can be easily generalized to analyze other structures such as hypergraphs or multiplex networks. And in the end, these other references I've mentioned in this talk. And that's all. And thank you for your attention. I'm happy to take any questions.
Thank you, Hanley. Any questions? I'll start with a close one.
Thank you. So I like the way you've managed to recapture the classical Feigenbaum diagram and period 3 implies chaos time results, but I kind of didn't quite get it a little bit early where you describe the transitions you were using. Could you give me some kind of physical intuition for the rules you're using for your changes?
I mean, the percolation transition?
When you were changing the network by crossing out the negatives and
the blinking.
Yeah.
Blinking is not clear.
Yeah, it was not clear to me why you'd picked those particular rules for change.
Okay, can I go back to the, I guess.
Please go back to those.
That doesn't work, I think.
Matt, can you help him out with the?
Click on that. Yeah,
it should work, but
yeah.
There we go.
So coming back to the feature of this.
It was the rules you had for the changes here. I didn't quite get where these rules had come from.
So there are actually several rules.
Yeah.
The second and third and the main one. The regulation can be positive or negative. This is like, of course, you have many options for these rules. Like you can have defined different rules for when this link is active or when it is not. So this is basically a very simple, maybe the most simple one. Like I'm activated, at least I receive one positive thing, and I don't want to receive any negative thing, because like a negative thing will be a poison, can damage this interaction. So at this stage we just pick a very simple rule. And this percolation thing, this is quite general. So in percolation, it's commonly regarded that only nodes in the giant component are active, and the other nodes are not active, or like fails or damaged or whatever. So this is comes to the rule when we looking at this dynamic. And the last rule is actually the time difference or time scale of these two processes, because we actually have two processes. One is percolation process, the other one is a regulation process. And in this case, we assume, we reckon these two processes are happening in different time scale, like one after the other one. It have some, let's say, motivation from the reality, because, for example, in the neuron transmission, because it's a chemical reaction, so the effect of the So if you have the transmitter in this environment, it will take some time to like totally remove it or remove the effect of this. So which means the regulation process can be a slower process than the percolation. So the percolation can happen very fast, and then the regulation can happen in a slower time scale. So we can separate this. We have percolation first and regulation, then percolation and then regulation. So this dynamic can go on.
Thank you. What's the question? Question on the chat as well. Okay.
Thank you, Anand, for the talk. I was wondering in the simulations that you showed, so I think you had a maybe preferential attachment network and then a mouse brain network. How do you add the regulations? Did you have actual regulations for the mouse brain, or do you just have some random process to add them?
This network itself, the structure network is a real one, but the regulation is here mentioned is a Poisson regulators. Clearly, because we will not have the actual information of the regulator in the network. So basically, we just want to show this regulative, the static percolation or the period doubling thing is not only happened on the synthetic network, but it can also happen on real network with this real structures. So that's the main purpose of showing this.
Thanks.
We are running out of time.
Yeah. Okay. And a hypergraph, what are the practical applications of this algorithm potential? Okay. Yeah.
In the hypergraph context, what are the practical applications of this algorithm and potential results it reveals?
So I guess you're mentioning this like potential extension of this theory on hypergraph and multiplex network. So indeed, if we want to capture some real world scenario, because for example, this triadic interaction could happen in a biochemical network of biochemical reaction. You may have enzyme, you may have this chemical reactors. And in this case, the structure of the network is not pairwise, but you have a higher order interaction. For example, you can consider a hyperedge that involves one type of enzyme and many other chemical reactors that it is in this whole environment, which gives you a hypergraph, not a hyperedge, not a link, because it's not a pairwise interaction, but it involves more than two agents. So this is a potential reason that we want to generalize it to hypergraphs. And first of all, this is a theoretical work, so we're not intended to directly apply this to some real world application, but we want to, we could potentially provide some insight to the, for example, the brain network study or the biochemical reaction network study. So this theory is designed to, like, we can analytically study what's happened. And in the future, it may be generalized to the real application, but so far at this stage, it's only a theoretical one, and it may provide insight, but not the direct application. That is.
So let's thank the speaker again, please. Okay, so our next speaker is Max Falkenberg from Citi. When you're ready, Max.
When I good. So, hello, my name's Max Falkenberg. It's lovely to be here. Thank you for the invitation. I'm currently a postdoc at City University with Andrea, who's at the back. But today I'm going to talk about some of my older work. So a lot of this is theoretical network science. But essentially what I'm going to talk about for roughly the next 40 minutes is I'm just going to moan and complain. And if you like my moans and complaints, please do come to me and talk about it afterwards, because I'm kind of stuck with where to go with these things next. Okay, so what am I roughly going to talk about? So the reality is we're in a room full of people talking about temporal networks, but it's still far and wide the norm that most people study static networks. And a lot of our understanding of static networks comes from theoretical models of network growth. So the absolute classic one is something like Price model, Barabasi-Albert model, which is the undirected equivalent. And when we build these networks, as physicists, as mathematicians, we love things to be tractable. So we make certain assumptions that make the maths behind these models tractable. The problem is those assumptions don't work in the real world many times. So one of the things I've been interested in for many years is understanding how the assumptions you make when you're constructing a network model, how those influence your thinking about the real world. And one thing I'm particularly interested in is how we think about the data that is missing in a network. So we can always go to more and more complicated models. I'm a physicist. I would like to, as far as possible, keep things simple. But what I'm interested in is if we don't observe, oh no, I thought there was a laser pointer, but there's not. If we don't see certain parts of the network structure when we're thinking about how a network evolves, well, how is this going to change our thinking about the mechanisms which construct this network? Okay, so that's roughly the general premise. Okay, so the talk will go sort of in 3 parts. The first part is basically a very simple example to try to illustrate to you where my thinking is coming from. And then there's going to be 2 separate parts. They will at first seem relatively unrelated, and certainly this first part, it's not clear at all what this has to do with hidden data. But what I'll try to do is show how these 2 ideas are related. The first about non-stationarity and preferential attachment, the second about symmetry breaking in node copying. I'll try to show how these are related and, use this to construct my, complaint, let's say. Okay, an example. Suppose we have a network. It's a wonderful little network, and we want to think about how this network is going to evolve. So when a physicist looks at something like this, we say, okay, there's certain symmetries in this system. We see that the structure between ACD and BCD is symmetric. So we make this kind of assumption. And then we say, okay, so if we watch this evolve, if we think about what's going to happen if new relationships form, let's say this is, a Facebook network, friends on Facebook, and we're interested which of these nodes are most likely to become friends. When we see symmetries, we make some assumption about those symmetries. For instance, that the probability of these 2 triangles closing is equal. The reality is, though, that many of the data sets we have about social networks, they are just projections from the real world. So I have certain friends who are very privacy obsessed and where the idea of being on Facebook is, completely anathema to them. So if I'm person D, I might actually know person A through some third party who's not on Facebook. There is already some relationship in this system, but it's not captured in your social network. The problem with this is that there's some hidden structure in this network, in the real data. When it appears in a social network, you can't see it. But the influence of this hidden data is it creates an asymmetry in your system. It means that the probability of one triangle closing is no longer the same as the probability of the other triangle closing. Now, obviously, if this data is missing, we can't systematically account for this. I'm not proposing a new set of methods to suddenly work out which bits of data are missing. But what I would like to do is think about, well, what would happen if we are missing bits of information? I want to see what are the systematic issues with making these assumptions in our networks. So that's roughly the example I want to give. And to start off with, I'm going to talk about an example which seems initially unrelated. And it is to think about completely standard models of preferential attachment. So that is, you have some network, you have some new node joins the network, and then Barabasi-Albert style, this is going to attach to a node in the network proportional to its degree. So that's the number of neighbors that are one step away from it. Now, for completely random reasons, I was working with some people in Tokyo Tech a few years ago, and they were particularly interested in second neighbor interactions. there was some data they had based on companies that showed that second neighbor interactions was very predictive of certain roles within a company. Okay, so for standard reasons, you know, someone has a data set and you start thinking about modeling it. And one of the things we looked at is essentially the BA model, Barabasi-Albert model, exact same model, but instead of attaching to proportionally to the number of first degree neighbors, you do it proportionally to the number of second degree neighbors. So all nodes within 2 steps of some target. It is a completely arbitrary model. It has no real world significance. It's a toy, yeah? But it's a toy that the purpose of which is to illustrate something. So the BA model, you know, one of the nice things about it is it's very analytically tractable. And the reason it's so analytically tractable is that the form of the rule, the probability of attachment, follows a very typical assumption. So this is that there's some function, which is a function of the degree's intrinsic property only, and that all the time dependence in this function is captured in the denominator, so in some kind of normalization. The consequences is if you look at 2 different nodes and you look at their relative attractiveness, then the time dependence cancels out. So essentially the rule itself in relative terms is stationary. There is nothing realistic about this rule in the real world, but this rule makes mathematical models tractable. In this second model, what you'll see is that this rule doesn't apply, and it has certain consequences for how we think about time in networks. Okay, so we were playing around with this, and as I say, you know, this is roughly what I've just said. In the classic BA model, you have this, you know, stationary growth rule. The consequences, you get this nice scale-free network, and this grows along the predicted scaling. So if you look at the network at one time and at some later time, the only sort of statistical differences you'll see is in some finite effect in the tail. Apart from that, for smaller degree nodes, everything looks the same. And the consequence that this has had on, in my view at least, the consequence this has had in our interpretation of real world models is there's a huge amount of work that looks at the network structure, the degree distributions of real networks. All sorts of papers at various levels of statistical rigor that try to work out, is this distribution scale-free or not? Very nice statistics, yeah? None of them talk about time, ever, yeah? I say ever, I'm lying. I mean, this paper mentioned time. It did like 2 snapshots and said the numbers are relatively close. That's good enough. But the problem is that if you make these assumptions about that time is not important, you're trying to understand the structure of a network based on a single snapshot in time, you get a skewed idea of the mechanisms that can plausibly construct your network. So these are all great in systems where the growth of the network itself is stationary. It follows the stationary rule. But there's pretty good evidence that this is not the case. And actually, if you look at something like the model I was just talking about, so this preferential attachment to second neighbors, what you see is actually, instead of converging to a limiting scaling, you basically have increasingly large fluctuations away from what would be the predicted scaling.
Maybe I'm being too much. Just clarify for me the second neighbor preferential attachment.
Oh, it's literally here you're proportional to 3 over a normalization. Yep. And here you count the number of nodes that are 2 steps away from a target. All right. And again, normalize. All right, brilliant. So, I mean, the model is not important. It's a completely trivial toy. But the point is in the BA model, it follows this nice, well-behaved rule that's stationary. This model doesn't do that. And the consequence is that you basically get fluctuations away from some steady state that grow over time. It's not simply captured in this finite tail. So what is very common when people complain about statistical methods for measuring degree distributions and about scale-free networks is they say, well, you shouldn't worry about the degree distribution. You should actually try to accurately measure the function that determines the preference of each node. Okay, many papers do that. And this is for the BA model. Again, you basically have predicted scaling that once you take 2 time steps and take the ratio of those 2 time steps, you should basically have a flat line. So if this is a flat line, it is a stationary growth rule. And what you always have is some finite tail effect. So you can ignore that. But in the case of this second neighbor attachment, there you basically have fluctuations in this growth rule. If you look at one point in time compared to a later point in time, it doesn't appear to be stationary. So these are just, toy network models. The reality is, though, if you look at all sorts of real networks, you find that the growth rule, if you measure it, is not stationary. And the other problem is that the only methods we have for measuring these functions assume that the function is stationary. So this is already calculating these functions, making a false assumption. Okay, so that's sort of roughly the point about non-stationary networks. You wanted to ask a question?
Is this just because the math doesn't work out?
Yeah, essentially. So basically, the reason it's a complaint and not a whole lot of new methods is because lots of these things cannot be solved if you don't make the assumption of stationarity. That does not give you an excuse, though, to forget it might be an issue. So it means that when you're using data, you should make reasonable efforts to look how stationary is my data. Are things changing if I take different snapshots over time? I don't have a toolbox that fixes these problems, but my agenda, in a sense, with this work is to encourage people to at least check their assumptions and think about, if these assumptions are wrong, how might our results change? That's where I get interested in this work. Okay, so in a lot of this, I've not really spoken about hidden data yet. But when I was doing this work, it was pointed out to me by a colleague that this second neighbor attachment model can actually be thought of as a copying model. So basically what you do is you take this initial network and you construct a surrogate where, instead of counting neighbors that are 1 step or 2 steps away, you just look for all 2-step connections and create an edge between them. So this is kind of a surrogate network I construct. And when you do that, you can think about, well, how does this surrogate evolve? And this surrogate basically evolves by a copying mechanism. So you attach to a node, and then you look at the neighbors, and then edges are formed to the neighbors of that target. The problem with trying to study this copying model is that the maths goes crazy. Yeah. So one of the things I was interested in is taking this copying framework for thinking about time and networks, and going as low as I can, as simple as I can, to get something mathematically understandable out of it. And what I came to is this very, very simple copying model by Renaud in Oxford and colleagues. I mean, he wasn't in Oxford at the time. And the idea in this model is, it's almost trivially simple. You get a new node alpha. It randomly connects to some node in the existing network, in this case, beta. It looks at the 3 neighbors, so gamma 1, gamma 2, gamma 3, and each neighbor is independently copied with probability p. So this is what I was talking about right at the start, the example I gave about asymmetries in copying. This is the symmetric example. You pick a neighbor, you look at them, you copy them with probability p. Now, this model is nice. It has all sorts of interesting properties to do with clique scaling and non-ergodicity. I really recommend reading this if you're interested in those things. But one thing I was interested in with this idea of hidden data is whether we can basically break this copying symmetry and construct some bias in this model. But I wanted to do it in a way where I could still do some maths on it and understand what was going on. So I'd like to break this symmetry somehow. And you might wonder, well, what's the point in this? But this is kind of what I was saying earlier about, you may have closer friends or less good friends. So, if you think of something like Facebook, you might have like 300, 400 friends. But not all friends are equal. There's 15 people who I'm actually good friends with. And what I want to do is I want to have some surrogate model in which the edges in a surrogate model represent your close friends, But this is not observed. Yeah, this is some underlying structure that you will not observe. And all you actually study is some observed network, which evolves by itself and as a function of some underlying surrogate. And what will happen is the exact same as in the original model. You'll have a node, it attaches at random to some target, but now we will copy close friends. So those are friends that exist in this surrogate network with some probability pH, and we'll copy other connections, but ones which are not close friends in this surrogate network with probability PO. And the nice thing in this case is that if you take the extreme case where pH is 1 and P naught is 0, then all of this becomes analytically tractable. And as you might expect, one of the consequences is that the symmetric model and this asymmetric model, where you've broken the symmetry between neighbors, they behave very differently. So this symmetric copying model gives you nice power laws. And if you use the exact same copying probability in this asymmetric model, you basically end up with something that looks like a stretched exponential with extremely high clustering. And then if you vary these copying probabilities, so you can have a copying probability for your close friends, you can have a copying probability for your distant friends, you get a whole sort of taxonomy of different structures that emerge from, completely trivial exponential decay to stretch exponentials. Of course, if your copying probability is 1, you end up with complete graphs. The original model basically lies along this diagonal where the copying probabilities for close friends and distant friends is equal. And here you have power laws. But the point is, within this taxonomy, there's all sorts of different structures that can emerge based on the bias that is present in your model. There's other interesting things that happen. So I just show this because from the 4 years of my PhD, this is my single favorite result. I am yet to find someone who cares about it, but I really enjoy it, which is that in this asymmetric model, you have a very weird clique scaling. So a clique is a set of n nodes where all those n nodes are connected to each other. And what you find is that the number of cliques of size n scales equally for all n, independent of n. That means you have an equal number of cliques of size 3 and 4 and 5 and 6. That sounds weird because that's impossible. It's impossible because every clique of size 5 has multiple cliques of size 4 in it. And every clique of size 4 has multiple cliques of size 3 in it, etc. But the reason this works is basically because it only works on aggregate. If you average over a large number of networks, everything cancels out. But the sort of message I'm trying to give here is that in any individual network, you're going to have large fluctuations away from this, very convenient, well-behaved scaling. Yeah, so this is just the clique scaling to show you. I mean, we're talking about networks that are, 100,000 nodes. This takes, about 100,000 iterations to average over, and you only start seeing the scaling for very, very small clique sizes. So, in practice, these things only exist in the absolute limit. But mathematically, these things look, very, very nice. Anyway, that's a tangent. I just really like this result. So that's this kind of asymmetric copying model. But one of the things we did in this model is choose this initial link at random. And we can think about, well, what will happen if you do it preferentially? And if you do it preferentially, you basically recover the model I was talking about at the start of this talk, which is this second neighbor preferential attachment. I won't go into details how you can see that, but essentially it's the same. And basically, suddenly everything becomes not tractable. And one thing I want to highlight is that the difference in this model to the case where you initially attach randomly is that now you essentially have coupling both between the surrogate model and between the model, the network you observe. So there's a difference in the causal direction in which, information results in changes in the network structure. In this, nicely behaved asymmetric copying model, you only have information going from this hidden surrogate layer to this observed layer. There is no influence of the structure of this observed layer on the hidden surrogate. But when you choose this initial link preferentially, that asymmetry between the layers is lost. And as long as I've been looking for it, every time I get a model with this coupling, I can't solve it. So I can only ever solve the models in which the coupling is only in one direction. And those are the kind of things that interest me. So I'm really interested in trying to generalize these ideas. I have no idea how to do it. So if you have ideas on how to think about these things, for instance, I've been thinking about trying to use dynamical systems ideas to do this, but if that interests you, please do speak to me afterwards. Cool. I mean, just to emphasize this thing about the non-tractability, one of the things you see a lot is non-ergodicity in growth. And basically what you end up with is, two instances of the same network with very, very large fluctuations from each other. And one of the other common features you see is an extremely strong dependence on initial conditions. So you get like gelation to a single node, which forms a community, and then that community has gelation onto it, and you get this sort of cascade of all sorts of things going wrong. So these are the kind of things we start seeing in the non-tractable models. Cool. So this is roughly what I've just said. I'm interested in trying to find some way of, generalizing this as much as possible. But in general, the kind of grander message I'm trying to give across is that I would like people as much as possible to think about the assumptions that go into their modeling and also how those assumptions impact the way they think about networks. As I mentioned, whenever these models stop being well behaved, I don't have a good solution for how to solve them. But the point is trying to think about how our analysis of networks will change if we think about these assumptions more. If you're interested in these things, there's these two papers. You can check them out. Thank you to my various colleagues who work with me on this stuff. And apart from that, thank you. And I'd love some questions.
Any questions?
So I'd really like this observation that there's network models where the different realizations are moving very, very far from each other. Do you have any, that's quite vague, but do you have any idea what sort of properties in a network model trigger different realizations to look similar, and what properties in a network model trigger them to look very, very different in the different realizations?
So my impression from looking at these kind of models is that the models in which you have, where the maths is well behaved. So essentially where individual instances are ergodic, they follow the expected scaling. Those are typically models where you can do a lot of the maths, where you can treat an individual node almost in isolation from the rest of the network. So you can mathematically think about it in the abstract without thinking about second layer structure. You can think about the immediate neighbors, but you don't think about feedback mechanisms. You don't think about, well, if this node changes, that'll alter another node, and then that will cascade back. So node A affects node B, and then the change in node B will affect node A.
So
these
we might think of it as some kind of tightness of coupling.
Yeah, exactly. So in the case where there's some kind of feedback mechanism, so node A affects B, B affects A, things tend to go wrong. In the systems where that coupling is, has no significant influence on the evolution, then you tend to have more well-behaved structures. But as I say, I really don't know a lot of, the requirements, and that's kind of some of the stuff I'm interested in better understanding.
Thanks for the talk. To carry on the next point, would that be related to how many cycle structures are present then?
Well, I mean, network scientists will tell you that almost all models only are solvable if they're trees anyway. So the maths behind networks is, you usually assume it's a tree. And the reason the reason you can solve this this copying model, which is not a tree, is because the surrogate is a tree. If the surrogate wasn't a tree, then I again couldn't solve it. Whether it's because of cycles or not, I don't know, but certainly mathematically, you almost always assume tree structures to avoid these issues.
Thanks for the talk. I have kind of a high level and maybe a bit vague question.
That's good.
Do you think there's any hope for more statistical growth models? And I'm thinking specifically.
No, I don't.
I'm thinking specifically of a paper by Austin Benson and some co-authors from a few years ago on, I think they called it choosing to grow a graph, where they basically recast a lot of these models in terms of logit functions. And so I don't know if this is where it's vague of like, do you think there's hope of using that kind of approach to alleviate these issues? Also fine if you're not familiar enough with the.
No, I actually vaguely do know that paper. My gut reaction always to approaches like that, with all respect to the authors, is that when you have too many mechanisms, you're probably going to be able to fit anything you try to fit. I think, you know, from a physicist's background, the reason we like simple models is because it gives simple explanations that are, you know, easy to understand when you make very deliberate changes to that mechanism. And I think that kind of interpretability is lost when we start going to these very complex models. I don't particularly see much hope for, you know, we will perfectly know what mechanism this network came from post hoc, unless we were involved in constructing it. Except in those cases, I don't see it much. But I do think, you know, there's thinking that can go into you know, understanding general principles of network growth. So, you know, how does triadic closure affect networks? How do long distance relationships affect network growth? What happens in superlinear preferential attachment as opposed to sublinear preferential? These kind of, you know, tools, and thinking about them in a broader context. Thanks.
I'll give you a half-formed thought.
Okay.
So if you don't have networks, then people still make assumptions about models. And you then want to, so I don't know why you're doing this. Okay, so I guess you're trying to say, is this network different from that network? Or is something we can measure on that network different from that? You know, you're trying to identify some. So it's quite easy if you're measuring something without connection, you know, are men taller than the women, for example. Okay. And what people think about the way you do that is you assume some model, and you know, maybe you assume everyone's normal and you do some Z test or whatever. But what you're actually doing is you're appealing to some kind of randomization argument. Right. So in the sort of deep magic underneath, you're sort of saying, well, you know, this person could have been a man or a woman, but he tends to be taller than she does. So I wonder if there's mileage in doing the same thing with networks. So instead of thinking, okay, we must rigorously think about what these models are and how they grow, you're thinking, well, we've got two different things. What is the possible space of random seeds that they came from? And I think mathematically, that's probably not going to be possible to do. But sort of simulation-based approaches, maybe, I don't know if you come across ABC, which is like approximate Bayesian computation. So you start with some priors on what your generation rules could have been, and you see what type of networks you've done, and your network is 12% likely to be in that. So I wonder if that's the way to go, because I can't see a nice mathematical result here.
Yeah, so I mean, part of this, and I didn't talk about it a long time, part of this is a response to the obsession of fitting models. I mean, my personal preference is to stop stressing constantly about, is it exactly this model? Because I don't actually think that is helpful. I think you pigeonhole yourself into thinking about networks or models or, you know, real structures in a very limited way if you say it has to be this or that. in terms of using approaches where you use some Bayesian approach and think about where could it sit within some family, I would certainly be intrigued by such an approach, but the things that concern me is similar things have been tried with network structures, and the family of distributions they try are all ones that are well behaved. They use distributions that are known to come from a network model that already makes one of these assumptions. The point with these non-ergodic models is they don't come from some family. They just, or at least they don't come from some very easy to understand, well-behaved family. They sit outside, you know, stretched exponentials, power laws. So I don't really know how to move forward, but a lot of this is, you know, me complaining about people being too rigorous, and yeah.
Thank you very much for the presentation, Max. Could you go back to the one where you showed, I think it was YouTube and Facebook, like real life networks, whether they were flat or not? There we go. That's the one. To the best of your knowledge, are there any results that try to measure this error rate in a sort of systematic way? The rate of misexpectation. You expect it to be flat, but in real life it's
no, precisely. I wanted to do that and I got sidetracked.
You got what? Sorry?
I got sidetracked, as people always do in research. Yeah, I mean, everything I've spoken about is like from 2-3 years ago.
Okay.
And these days I'm mainly working, you know, polarization in social networks, completely different stuff. So no, that's something that's interested me for a long time, trying to systematically look at, you know, deviations from good behavior. But I'm not aware of anyone who's done that systematically now. Cool. I should.
Just one comment, Max. Now, why don't you try? I mean, this has been tried, so it's a comment. You start from the way that you know the structure, and then you remove things. That's what you get. Statistical mechanics have done by Collington and Ivan in Keynes to show that when you remove nodes or links blindly, the distribution changes. So that's the other way to do it. So don't go from the growth model, go from the statisticals, from what you know, from what you think you should get. And from then there are results for that.
Yeah, no, so that's definitely an interesting approach. I have looked into that at one point. It's I guess it's just a different way of thinking, and I've not gotten around to thinking that way yet. But yeah, no, it's definitely an interesting way of looking at it.
Okay.
Yeah. Thank you.
Thanks again.
I think Reddit is linked to something. Are these links going to get shared after?
No. Maybe as you say, indeed. So Renaud has a comment there. Okay, so Renaud, I just saw it. ABC has been used in this context, so that's an answer to the comment from Ben. So if anyone can see that, the link on there.
I think you said something. You go play out loud. Yeah, I'm just gonna go there.
Thanks. I think so. Yeah.
Okay, so let me introduce now our next two speakers. Is Eleanor and John, and we'll do it already.
Great. Thank you very much. So this is a project we've had some earlier presentations where people have said basically the scientists brought us this question. I'm the scientist bringing the question here, and you can see I've asked it of many too many people, including here John as well. So this is gratefully funded by an ESRC grant, which is probably none of you even know that there's a different corner of the UKRI for this sort of stuff. In any case, here's the entirety of the team here. So we're a mix of social scientists, including anthropologists, psychologists, social statisticians, Bayesian statisticians, and also, of course, some statistical physicists and things like that in the mix as well. And this is really the work here should be credited to Katerina, Martina, John especially, and of course the entire team, but there's a reason I'm at least at the end here. And yet you get to hear from me talking because I'm going to be giving the motivation, and then we'll hand it over to John to actually show you the hard bit of it. So the motivation comes for this from an entirely different project, which we call by the acronym ENDOW. ENDOW stands for Economic Networks and the Dynamics of Wealth Inequality. This is a large collaborative project funded by the US National Science Foundation, which is gathering in the end some 50 different or over 50 anthropologists and researchers working in over 30 countries around the world to gather social and economic data, so social network data and also demographic data, household wealth information and things of that nature across 2 points in time. So we do have time here to look at basically changes in households and individuals' livelihoods and to understand how the position of individuals, or really the positions of households within a community network, is influencing their ability to better themselves over time. And at the community level, how the structure of that network seems to be associated with wealth inequality in that community as well. So these are trying to get at some fundamental questions about how individuals and communities better themselves and how the social relations that they have facilitate or constrain their ability to do that over time. Like I said, involving all sorts of different people. So here is not even all of the researchers involved in this. This is from a meeting at SFI some number of years ago. And this is all of the different places around the world where we are gathering data. So broadly in the global south, in relatively rural, small communities where we can actually go out and gather the data. So this is definitely not big data. This is data gathered with pen and paper surveys on the basis of longstanding relationships of the anthropologists and other researchers who are working in these communities. So for example, those 2 little dots right there are where the data that I'm gathering in South India, and that I've been working in these 2 villages for about 10 years. So there are some constraints that we needed to work with for the ENDOW data that are going to then influence the questions that we brought to people like you here. Broadly, the data that we have at hand in terms of the network data, at least, we're doing a standard set of name generators. Well, I should say some of them are standard and asked consistently across sites, and other ones are specific in that a sort of domain was set, but the specific phrasing of the question is appropriate to different communities. It doesn't make sense to ask the same questions in an agricultural setting in India and a fishing community in Vanuatu, or a horticultural community in Bolivia, or whatever else it might be, right? So we've got some standard, some varied. A number of the questions that we asked are what's called double sampled. So we actually ask about the relationship in 2 different ways. We'd ask basically, who would you go to for advice? And then we similarly ask, who comes to you for advice? And if both the giver and the receiver are asked that same set of questions, that means we should be getting we should be double sampling that relationship. We should be getting information on it from both the giver and the receiver, because we're asking about the questions in both ways. That'll become important in a minute. For the realities of the complicated nature of fieldwork, our sampling strategy is very different between sites. So in some places, so we can't even speak about households here. That might be the term that we would like to think of, but what does a household mean in different communities around the world? If you have a polygynous setting, where you might have a man and multiple wives, what even is the household unit there, right? So what that means is harder for us to work with. So we think more generically of a sharing unit, which is basically the unit to which economic resources are shared, where there's pooling of resources and where people are then sort of entangled with one another's and their livelihoods. So at least one person had to be sampled from each sharing unit. But that was a minimum. So a lot of people spoke with a male and female household head or something like that. I was masochistic and asked all of the adult residents in the communities. We have a range of reporters speaking about not just really their own personal relationships, but more generally speaking on behalf of that larger unit, that sharing unit. And the coverage that we have of sharing units, at least, is very, very high. So in this case, we're basically everyone is getting over 90% coverage of those networks. These differences in the questions that were asked, the phrasing of those questions, but more specifically in these sampling decisions are important for us to consider, because fundamentally this is a comparative project, and we want those comparisons to speak to actual differences in the nature of sociality in these settings and not differences in how we chose to measure them in the first place. So hence all of the rest of this talk then, talking about the consequences of different decisions on measurement and representation of those relationships for us to consider at the start. So to set the scene then for what we might otherwise typically have done here, I'm going to punch up a little bit and punch up all the way to the Nobel laureates. This is Abhijit Banerjee, Esther Duflo, and Matt Jackson would also be on these pieces for people, for the sort of relevant person for networks. They gathered data in as part of of course, it was a randomized control trial where they were looking at the adoption of microfinance. And they gathered data in 75 different villages in Karnataka. And here's roughly what they did. So in ways very similar to the data that we're gathering for Endow. They had 12 different name generators. A good number of those, again, were double sampled, just like ours. They're asking about both who you give loans to and who you receive loans from, for example. They asked multiple reporters in each of the different households, though their sampling coverage of households was actually not great. And they did this across 2 waves in time. So how did they take the raw survey responses that they had to then generate a network that they then worked with? Well, they combined all reports from the household. So whether you had 2 reporters or 5 reporters or just 1, they're all combined. So you get one sort of meta node, which represents the household's responses. They take the union of all of those together. They then also collapse, and this includes the ones where they're asking about relationships in both ways. They then also collapse all of the different name generators. So they're dealing with one network across all of the different prompts that were given. And they only consider those households who consistently appear across both waves of data collection. So they drop all of those that were only there in wave 1 and not there in wave 2 effectively. And actually, in the end, it's even worse than that. They consider only, they remove edge weight, or sorry, tie directionality, and they don't consider edge weight as well. So they end up with one undirected, unweighted household to household network, which is what they then perform all of their analyses with. Yeah.
Just a quick question. These 8 questions are different on what they're asking about?
Yes, exactly. And we'll actually show this later on. So they double sampled an advice question, a household sort of food sharing, like who do you borrow and receive kerosene and rice from, a visitation network, and
so at the end of the day, the edges are essentially this social contact.
Yes, any sort of relationship reported by anyone, whether giver or receiver, and anyone from those households. Yeah. And the consequences of this can be pretty substantial, as we will try to demonstrate. So this results in a variety of different measurement issues that we're trying to grapple with here, and which are shared by these Nobel laureates, but also basically loads of social scientists who are gathering social network data through surveys. So this is exceedingly common. So the first issue is when we have multiple reporters or multiple reports on what should be the same relationship. And so there's a fundamental question there as to what do we do, particularly when those reports conflict, where I say that I'm friends with John and he does not agree with that statement. So that's actually largely what we're going to be talking about here today, because this is what we've actually really done. So we have a model for this, which is in press at JRSSA. And you can see the archive link for that. We'll talk about that more, but there are further issues. So there's then the further issue of we have survey responses which are given to us by individuals, but we want to infer some higher order, well, not higher order, that's going to be different for the people here in this audience, higher level network that's not individual to individual, but rather household to household. And so first of all, there's a question as to the extent to which this actually exists
in any real sense, but often we would like to think that something like this does sort of kind of maybe exist, and then how do we go from individual responses to something that's representing those higher level units. This then becomes even more complicated. So this is what we're working on right now, and we're leaving for the end the actual time thing, which I will gesture to at the end, which is basically these, as we go, this step of aggregation, individuals, I think we can all agree, are relatively stable in how they exist and move in the world. Households, though, are potentially not. So when we're considering households over time, we may have people from one observation to the next, joining or leaving. What that household is when there's divorce, when there's a new child there, when those individuals have themselves changed in any number of ways, complicates things. And specifically, it means that the nodes that we would want to actually work with here are themselves unstable across time. So how do we talk about a temporal network when we have unstable nodes? And that is what we haven't even broached yet, because it is obviously exceedingly hard. Okay, so first we're going to be talking about multiple imperfect reports and how we might be able to aggregate those. So when we have asymmetric relationships, or more generally directed relationships, we can double sample those relationships. So we could find out about the existence from I to J, either by asking I about their relationship with J, or by asking J about their relationship with I. There are, of course, other ways that you could get multiple reports into we could also ask a different person M about the existence of relationship between I and J. But our focus here is going to be in the case where you can imagine, again, you're asking something like this. So in the event of an urgent need, from whom could you borrow the equivalent of a week's wages? And also in the event of an urgent need, to whom would you lend the equivalent of 1 week's wages? And if we're asking those two questions, both I and J, we should be getting both of their reflections on that relationship from I to J, as well as the relationship, obviously, from J to I. So in some cases, they will nicely agree. They will, for example, both say that that relationship exists, or they will both say that that relationship doesn't exist. Those would be concordant reports there. But we're also going to potentially have discordant situations where one of them reports that the tie exists and one of them does not, and the corollary of that. And the question effectively is, how do we integrate these potentially discordant relationships? And this is exceedingly common. So in that network data set of Banerjee et al. From Karnataka, only about 10% of the ties are actually concordant. So we primarily disagree about the existence of those relationships. And the consequences of this are huge when we look at, so here now we've got our different, I focus here on the left panel. So these are the 4 double sampled relationships that they have. One about money, advice, about borrowing and lending household items, and about visitations. If we consider the two, so we have the 2 different name generators. If we look at them individually and look at a simple measure of the extent to which there's reciprocity in those networks, so each point here is representing one of the 75 villages and one of the different relationships types, we can see reciprocity in that is around, let's say, 20%. But if we take very simple deterministic rules of aggregation, like the union, as is often done, so that's basically saying if anybody reports a tie, I'm going to say that it exists. The intersection would be saying if people don't agree that a tie exists, it does not exist. So this is the most maximal and the most minimal. Either way, actually, you're dramatically increasing the observed reciprocity value there. So that seems like pretty fundamental decisions as to how you choose to construct the network are impacting pretty fundamental measures that you might want to make some conclusions about for example, the extent to which relationships are reciprocal. So this means that there are potentially a few different issues going on here. One of the reasons for this massive jump is what we call mutuality, which is basically the extent to which we desire to be in balanced reciprocal relationships. And we see this all the time in the reports, where basically, if I am asked, who would I go to, who do I enjoy spending time talking with? And I say John, and then I'm asked who enjoys talking with me,
I very much want to think that John also enjoys spending time talking with me, right? And so you see these basically repeat nominations. These questions are typically asked in order, one after the next. And so people will often say basically, yes, those people that I just said I go to, they also come to me. So you get this massive desire for mutual relationships, for balanced relationships. And because of that double sampling, that then inflates the values that we see. Though the extent to which that should happen should vary by relationship. So in relationships that we expect to be more hierarchical, for example, we may not expect this to the same extent. I might go to Richard for advice. I do not expect that Richard comes to me for advice, for example. So I'm less likely to name him twice across those two prompts. Then we may be thinking more generally that there are some reporters who are just more or less reliable, or more generally that they may be responding to the questions in different sorts of ways. So some people might have a different idea of what it means to be a friend, and might have a lower bar to saying, somebody might just name many, many people, and somebody else might have a different idea and maybe be more circumspect and not name as many individuals. So we might have differences in the extent we can sort of trust the responses that are given by different individuals. So this idea of mutuality is going to be sort of common to a relationship, probably normatively formed in a particular community, whereas the sort of reliability of particular individuals is going to be particular to individuals. So with this set of observations, we then attempted to define a model that would do something to help us figure out those different measures of reliability and mutuality and the actual sort of true underlying latent network, which John can now speak to.
Yeah, I can talk a little bit about that, but we had a question beforehand, right?
Oh, sorry. Yeah.
Imperfect question. People can interpret a friend in different way, whereas
the
question is, who do you go to for advice? That's a bit more of a clear question instead of friend.
Yeah, of course. So this is why we spend a silly amount of time deliberating over the exact phrasing of the questions. But of course, this is assuming that the question is being asked in consistent ways across individuals. And yes, this is why you would probably want to avoid prompts that leave a lot of space for interpretability. But take the question as given. There might still be different. Actually, this even picks up to what Max was talking about before with missing data. If basically people just have, somebody's maybe more comfortable, giving responses as compared to someone else, you could effectively see that almost as sort of missing data, in that somebody might have relationships which a recipient might be willing to give, but the giver may just, maybe that name is forgotten, or there's sort of a different bar for their expectation of giving it. So we can see, for example, that one of the common features of this is that there are often sort of stars. So a few individuals who many people name, but who themselves do not then name many individuals. So, it could be the guy who's giving loans to everybody. He's not going to remember everybody that he's given a loan to unless he has his ledger in front of him, but the people who have a loan with him probably remember him, right? So it's there's yes, it's a messy situation, let's put it that way. And we're trying to deal with the mess. Yeah.
Yeah, so just to reinforce that is, even if you consider that the questions are well framed and everything, like, we would still have problems of, they might not agree on the reports. So I'm going to talk to you, describe briefly how we're modeling this problem. So we posit this expected value. So we have our data X, which is the actual report. So M is a reporter, and they're reporting on a type. It's directed, right? I to J. I goes to J for advice. And that is a question. And then we posit that what is the expected value for that report, given that the true. So we have this idea that there is an underlying true network there, right? Linking I to J, and it has a degree K. So how do we measure that? Like, so we that's just like restating what I just said, how we're representing that. And the expected value, I think, is kind of straightforward. Like, how we solve it is a bit complicated, but what we state here is that, first of all, just what Ellie just said. So we have this idea, we have the assumption of mutuality embedded in this expected value. So if reporter M reporter a tie from I to J, we would expect to a certain degree that they would do the opposite, like they would nominate that J would go to I as well when prompted on the other side. So that means that the tie on the other direction would inform our expected value for I to J, for example. And that is modeled as it's captured by this parameter called mutuality, which is a positive number that is inferred by our model. And then we have also, apart from the mutuality aspect, we also encode the reliability of the reporter. And that is another thing that Ali just mentioned. So are these reporters, are they over-reporting? Are they under-reporting? And that model would, this is also inferred by our model. So what is the expected value for how much does the value of Y, the true network, would spill over to the true data that we observe? So we have this, aspects of the data that refers to the reporter and aspects of the actual reporting itself, and we use that data to encode. We posit this likelihood, and we solve it using variational inference. So it's a Bayesian approach. We solve it with variational inference, which means this, as opposed to MCMC or these other Bayesian approaches, is very efficient. So we get to explore and do some simulations with our data. And that is what I show here. So the first thing we did before we applied it to real data, and essentially this is what we will inform when we move it to the sharing units and to the temporal network aspect. We wanted to see how did this model capture the true network. We planted the true network, and then we generated some noisy reports from that. And we added a few a number of these people in this network was 100, simulated 100 nodes. How many of them would be over-reporters? That's the simulation on the left. And how many of them, what is the ratio of under-reporters that you would have? And we also planted some scenarios of mutuality. So if the mutuality, remember from here, it's it's something that is inferred for the whole network. So it's a property of the network. It's a group thing. So what we see from our model, and here we are comparing to those two baseline assumptions of the union and the intersection, is that even when we have a higher ratio of unreliable reporters, whether they are under-reporters or over-reporters, our model still encodes, it still captures the true network more, better than if you were to just aggregate simply by taking the union or the intersection. So that was a good sign. So that meant that, in the simulation, we fared well. And then we started applying it to real networks. So one of these networks is Nicaragua. One of our collaborators, Professor Jeremy Koster, gathered this data. And here in this particular network, we have each one of these represents a node, and the concentric, the shares of this pie, they represent, how many people confirmed that tie, and when they were prompted, how many other people actually confirmed, or, yes, I agree. It's how many of them were concordant on reciprocals. So this, the one on the left is one where they are under-reporters. They do not tend to report pretty much anyone, and people will nominate that person in their ties. Whereas this one here is, it's a huge over-reporter, and in fact, I think I remember Jeremy telling us about it. So that was a guy when they asked, who do you go to when you need rice? And then he would point, it was an iPad, right? Yeah. So he would point in everyone, he selected every single person. And then he would come to you, select every single person. So it was good. It was a good sign. It matches the evidence in the field that this person was actually an over-reporter. What you would have if you were to run this model. So this here is a comparison of those two baseline approaches from Banerjee that you would use, and take the union. This is one of the networks from the Carnatic.
This isn't even quite what Banerjee does, because they're also aggregating to households, but this is
still the individual. The individual level before we move on to sharing units at the households. If you were to take the union, that's the one on the left. The one in the middle you get the intersection, you very, very, very sparse network, and then you get rid of a lot of reports. And when we run our model, we actually have a weighted network, and these are, you know, there's room for interpretation. How do we interpret these actual ties? So we have probabilities attached with those. So what is the probability that this tie exists? So one thing you can do after we have that is sample from a posterior and do multiple sampling until you get, a better description of the network. What is the reciprocity, or you get a point estimate, which is what we did in some of these cases. So for the same Karnataka networks that we were talking about, they are about, how many networks do we have? 75 networks. So we looked at all of these 4 different layers of the network. So the prompt questions were on advice, money, visit, and household items. And we can see from here that, let's focus first on the box plots. And we're trying to look at reciprocity, right? The tendency that people that go to someone would actually come back to them later. Not so much in the report, but actual, in truth, when we infer the true network, they would return back. So we see that reciprocity is inflated on those cases from the household items. And the visit, maybe Ali would be better suited to comment on those.
Sure, yeah. So overall, with our model, Demure, our estimates for reciprocity are lower, and we have the ADAs here, our estimate of the mutuality, and you can see again that lines up with our expectations. So for the money and advice, well, really, especially for the advice network, our estimate for mutuality is lowest. So people have the lowest propensity to sort of double nominate individuals. And it's highest, so people have that greatest desire for being in balanced relationships for who they would go and visit, so effectively a friendship network, and who they would give and receive household items from. So we're getting both a better measure of the reciprocity, but then we're also learning more about people's sort of perception of these relationships as well.
And also you have to remember that we now have a more nuanced view of the network as well that we can explore.
Yeah. So where we're going effectively, and we will wrap very quickly here, are the next steps. First, that step of aggregating individual reports up to the household. So we have some number of individuals, and we see at any particular point in time that they exist in something that we could define as a sharing unit or something like that. Those individuals could be nodes about whom we know information about the relationships between them, but often we want to then understand not the individual to individual relationships, but the household to household relationship. And again, here the question is how we do that aggregation and whether or not we even think that this exists in some particular way. To reinforce again, looking at the Karnataka network data, the consequence of this here too, we can see that if we aggregate individuals to households, we see boosts, jumps again in the reciprocity values. And that's going to be particularly for relationships which likely are between households. So we see that, when people are going for advice, they might be asking their spouse or their partner, their parents for advice. So that aggregation from individuals to households doesn't make too much of a difference, but it does much more so if we're thinking about the exchange of household items, things like that. So again, how we do this work, this is again here just taking a simple union. How we do that is going to have consequences for what we see at the other end. A further complication is we might have across those different sites where we're gathering data for Endow, households or sharing units that look very different in terms of their size, but then also in who we speak to across those different units. And these, when we do that very simple aggregation of just combining them all and taking the union of all reports, is going to result in substantial differences across those, some of which might represent differences in measurement approach and sampling, and not so much differences in the actual substance of relationships between those different units. So again, here with aggregation, we need to do this with care. So we're working on that right now and trying to tell our query how real the household network actually is. There is some comparable work in this space, but most of it is quite different. So Lazega, for example, is looking at interorganizational relationships and interindividual relationships and how they relate to one another, but we're trying to just infer that household to household network. So we're working on that right now. And then finally, time here, yes, in some cases, at time step 1 and time step 2 that a unit might be stable, and that's all well and lovely, but we're also going to have cases where households combine, households split, new members arrive, and any combination thereof. And so how you even consider the evolution of a network over time when the fundamental unit that you're trying to grapple with is not stable is exceedingly difficult.
And it might also interesting to think about the timing of the snapshots we take, right? That would take what, 5 years from one snapshot to another. So how many other differences and changes in dynamics might have occurred between one time step and another? So,
and even that then is not really the same.
Exactly.
That's a 5-year-old to a 10-year-old. That's a very different sort of thing. So we're working on all these things right now. The foundational model with the multiple reporters is in press. We have put together a lovely Python and R package. So we're agnostic on that front. And you can go to our site to learn more about that and install it and all the rest. Right now, we've had so many deliberations on the aggregation to households, or how to deal with individuals in households, the sort of multi-level question, that we have 2 different versions of that we're pursuing simultaneously. One more statistical physics and one more sort of standard boring stats, social statistics sort of things. And the extension to that dynamic case is still on the horizon. We'd be very happy for any ideas that you might have. So thank you again to you and to all of the people who've worked on the project.
Any questions?
Brilliant presentation. I loved it. It's sort of the phrase that comes to mind is seeing how sausages are made.
Yeah, and
so.
it's very messy and kind of ugly. I mean, and this is it's very simple to take that the network data set as given, and I would encourage extreme caution, especially if it's based on survey data sets or really any sort of social system.
Probably a high proportion of the people in the room have worked with the Zachary Karate Club and just gone, yeah, those are the links. Yeah, I must be right.
Yeah.
That's not my question. I was looking at the model you gave for the expectations and the parameters. It seems like the number of parameters in that model is coming within a pretty high factor of the number of data points you have. Is that correct? Can you pop up this slide just so I can understand it? It's the one.
the reportings.
The one where you had the parameters with the mutual. Yeah. But the one after that, I think the one after it. That one. So I think you have a parameter for every individual you ask.
For every reporter, yes.
For every reporter, but you're not asking them a huge number of questions.
Yeah. So to make that efficient in the code, what we did was that's a very sparse tensor that we actually encoded that way. So especially in the Karnataka, just to illustrate your point, in the Karnataka, every reporter can only nominate up to 4 people.
I think it was 5.
4 to 5 people.
Yeah.
There's also there's that limitation, and you're not asking them about every single. We take so that's why like the different service setup. That's more about the code itself. So we set all those those lines to 0 because they are not there, and we only solve, and that's what makes it efficient. We only solve the equation to those which we do find a report. And if you think about it, if there's no report on a particular time, then that's 0. That's a good, an easy case to solve. That's just a 0. And if there is a 1, and it depends on how they are connected, then we infer. So that I think has to do with this partition.
Okay.
Question.
Thank you very much. I think it's on the next slide, the figure with the or maybe the figure with the performance when you did the oversharers and the undersharers. Yeah, there we go. So it kind of struck me that the performance is relatively better when there are over-reporters. Right?
These can't be directly compared because the mutuality parameters are different.
Right, okay, well, I guess regardless, how much are the over-reporters over-reporting, how much are the under-reporters under-reporting, and can that influence the performance of the models on this, and who are they over-reporting and under-reporting as well? Is it random? Is it secondary neighbors, all that sort of stuff?
I can tell you about the setup for the simulation. So we had 100 nodes, and the theta here means the reliability of reporters was set to 1. In all of them, it was deterministic. It was not randomly assigned. But in the underreported case, we set this to 0.5, so half of the report. That we tend to do half the report. And the overreported was set it to 50. So it was a lot more. So that might explain what you're explaining about. Like, so the overreported, we exaggerated it before.
Yeah.
But the effect, because of the scale, it's quite similar actually, in terms of the ratio of two.
Okay. And so, yeah, with the overreporters, what extra links are you adding to the network? Like, how are you adding those?
So with the overreporters, so for every tie, let's say for money, who do you go to and ask for money? So they would actually nominate people that would not, if it was a real scenario or if it was the exaggerated, like the case we have in Nicaragua, they would name everyone. So it's essentially people that are not connected to them at all in the network. Like it could be people that are completely far aside in the network, in the periphery of the network, but they're still naming them as if they were. So,
but it sounds like your question is if there's a pattern to their overreporting. Are they only nominating the popular guy? Is there
or the people who like
or two steps removed.
Next most likely to be overreported.
Yeah, I don't think we fiddled with that.
No, I don't remember I really don't remember how we did that. I see, like how they were in the network, inside the network.
Because I guess the underreporters, you'd always remove real ties.
Yeah.
Whereas overreporters, you're not necessarily adding nearly real ties, I guess.
I don't remember how exactly we did that, but it was definitely not just like random anyone.
Okay.
The network does have an impact, like how they are, but I don't remember how we.
No.
Yeah.
Cool. Thank you.
Thank you. That was a fantastic presentation. I was wondering, possibly on the similar lines, in the real data, whereabouts in the network the over and under reporters are. For example, I think you gave me an example of potentially if there's someone who's regularly giving out loans, they might not remember all the I wanted to if you could.
Yeah, so we've played with this a little bit to see what's happening. That is the most consistent finding and the most frequent occurrence is basically you have people who receive many nominations but don't give so many themselves. In, for example, the Karnataka data, that's because they're actually prohibited from giving more than 5 nominations, right? So we necessarily are going to see many more underreporters in that scenario. There has been other work by other people looking to see what drives agreement, disagreement, and sort of accuracy in recall. I think we really do need to be using scare quotes and all these points because, like, is that relationship really salient for the guy who gives loans out to 100 people? Maybe not, right? So it's nice to be staying in a Bayesian space here. But that's in terms of like looking to see what are the demographics or other information that we have about individuals in order to be able to predict the reliability of those, again, with definite scare quotes. We haven't done that to a full extent yet, beyond the point about the sort of degree and the degree of those individuals. So high degree individuals, are often underreporters.
Hey, thanks. This was really fascinating. If you could just quickly go back to where you're defining the expectation of, this one.
Sorry, it's coming.
No worries. No, the one before that.
Yeah.
This one. So here, the lambda here is a sort of, you're trying to fit how the true network influences your, what you see. And this is the same for every village, for every person. This is like a system level property, right?
We weren't taking a multi-level approach in that way. So we're fitting each village separately, each village and each relationship separately. So we're looking at like village 1 and its money relationship.
So there's a lambda K for every village and every type of relationship.
K here is actually the degree. So it's just like discrete degrees. So the strength of this tie is 0, 1, 2, 3, or 4. So that's not an index on the village. So it's just like indicating the strength of that.
Right. So I was just generally curious how does lambda vary with K? Because is it like a quick spike or does it? I don't know. Do you?
Our priors for this, for example, are 0.01 on the 0 and one for the one. So if that means if there is in the true network, if the generative network here that we have, if there is a type 1, so that means that we want to infer a 1 here, right? And if there's a 0 here, we want to be close to 0 on this side. But we didn't play as far because we didn't need that for the network we have. We didn't play more than 0, 1, k equals 0, k equals 1. So you could go as far and yeah, you can set the priors and let the convergence define it for you, and then you can export that as posterior.
So the true network is just 0, 1. There's no strength.
For the empirical data sets that we are using here, yes.
Oh,
For the
cool.
for the model, no. The model is more general.
Cool.
And the model is also not limited to double sampling. You could anybody could be an M. M could be every node in the network, for example. And so, in fact, in the Karnataka data, or sorry, the Nicaragua data, that's a different approach where each person in the village reported on the entirety of the network.
Okay. Yeah.
Which is sometimes called cognitive social structure as a sampling approach from the 90s.
Thanks.
Thank you. It was a really nice presentation. I was wondering, have you viewed the problem as a multiple network data problem? So having ultimately for its report, for its reporter, a network, and then reconstruct the network from the true network from the multiple reporters? Is that the way? Because I'm not sure if I have misunderstood or.
Are you asking if we're treating this as a multi-layer approach? Or
yes, a multiple network dataset problem where each observation is independent, or a multi-layer, yeah, even a multi-layer where there might be across the networks that they are sharing the same nodes and each individual is reporting something different.
It's close to the idea of the multiplex network, I guess. But one important thing here is that we don't model any coupling between these layers. So we treat them as independent and multiple. So we thought about it. We thought about implementing because there might be some coupling. And if you go to someone for money, you might go to them also for advice or some other things. But we didn't we didn't put it into the foundational model.
But the model can do it. We just chose not to implement it that way for the empirical explorations that we're doing. It effectively already is multi-layer, or it could be.
Thanks.
Any other question? No? Shall we thank the speakers again, please?
Okay, thank you very much to everyone in the session. We now have a coffee break, which lasts until 3:40, and then we've got our final session of the day.
Okay, everybody. Thanks again all for coming. I'm really excited to chair our last set of talks. First up, we have Johannes Lummer from the Alan Turing Institute, and I shall hand over to you.
Yes. Oh, I don't need a mic, right? I just need it. Thank you. Okay, so, well, hello, everyone. It's great to see you, and let me also thank the organizers for putting together such a lovely workshop. It's been a real pleasure so far. So I'm going to talk about some ongoing work, and I think the title is a bit grandiose in the sense that I will probably disappoint you. But yeah, it's some ongoing work that I started when I was employed at École Polytechnique, and it's a joint work with Jean-Philippe Bouchot. Okay, so let me maybe get started by just giving you kind of the key goals of this talk in case you want to, I don't know, in case you're a bit sleepy after the break. So I will introduce a non-perturbative tool that is already pretty established in statistical physics to describe a system of dynamical network economies. And to do so, I will obviously introduce what network economies are, give a bit of a background, and then introduce this tool, so dynamical mean field theory, as a way to study dynamical networks in economics in this case. All right, so the big goal is to kind of understand this kind of plot. So what you can see here is the yearly GDP growth of the US, well, over a period of 70 years. And on on average, GDP is growing, but as you can see, the standard deviation is quite high. And this phenomenon is called the business cycle. So essentially it's the cause or the origin, or describes macroeconomic fluctuations. And one big goal in economics is to understand the origin of these macroeconomic fluctuations. So why does GDP grow? And typically what is done is you assume some kind of external shock. So this could be, for instance, an extreme weather event will obviously affect the economy, or climate change also. And you assume economic equilibrium, and then you study your system and try to, try to see whether what you get makes sense. But what I would like to propose is an alternative idea where these kind of shocks, these kind of fluctuations are not caused by external shocks, or not necessarily by external shocks, but can be caused by the internal dynamics of your system or of the economy, the way kind of the network is set up. And moreover, I will kind of depart a bit from the idea of economic equilibrium, and will assume that, you can have some kind of out of equilibrium dynamics. I will come to that in a second to introduce what is meant, or what I mean by economic equilibrium. Okay, so what are network economies? Because this will be kind of the framework within which we would like to study business cycles and macroeconomic fluctuations. So fluctuations in productivity, for instance. So network economies are essentially a system of firms or industries that are related by their input-output relationships. So for instance, if F1 buys from Fn, then there will be a link, and essentially this creates a directed network where you have n firms that are equipped with the so-called production function. So the production function in economics, it's essentially just a way to model how a firm produces and how much a firm produces. And furthermore, you can actually, you can assume or introduce different things, but in a very simple version, you can also introduce a generic household sector, which provides labor while maximizing a so-called utility function. So the way the household makes decisions is by, sounds maybe a bit materialistic in this crowd, but is by maximizing its own utility. And typically you assume some kind of function for that is then maximized. But it's not that important how that function looks like exactly. As the talk goes on, I will assume a so-called Leontief production function. What it means is essentially that production is limited by the scarcest good. So do I have a laser actually, or I don't? Okay. So essentially what you can see here is a variable Zi, which is called the productivity. Then you have the variable Jij, which essentially denotes the units of J that are needed to make 1 unit of I. So let's say I produce bikes, then I would probably need two wheels. So Jij would be 2. And Qij is essentially the number of units of J that firm I buys. That firm I buys. And as you can see, so the moment that J is no longer available, so it's 0, production stops. And so that's why the Leontief production means essentially that production is limited by the scarcest good. So this is something that, or these kind of setups have been studied in economics for a while already. So I've cited these 2 papers, but in these kind of scenarios, what people do is they always assume economic equilibrium. So they assume that supply is equal to demand at all times, and that profits are zero. And well, if you think like a physicist, you could say, well, maybe that's not always the case. I mean, it could be, right, that the economy is out of equilibrium and somehow relaxes to an equilibrium state over time. And then you could try to study the system and see what kind of economic phenomena you can get. The natural question then, of course, is, well, how would you model the dynamics of such a system where you say, well, I no longer assume economic equilibrium, because you need some kind of way to describe how your system will evolve. I should say that this kind of toy model that I introduced to you here is described by two variables for each firm, namely the prices it sets for its products and the production. So in order to introduce some kind of dynamics, one can introduce rules of thumb. So these are intuitive rules. They're not, they're not fundamental, so they're just assumed. But essentially what you can see here is that, to begin with, there are two key functions, namely excess production and profits and losses. And for instance, and there are 4 different time scales. So these are the parameters alpha, alpha prime, beta, and beta prime, which will dictate how fast the economy equilibrates. And so what you can intuitively see from these equations, I mean, you don't have to, what's important is that essentially, if there's too much, lots of profits, will drive prices down over time, because actually it will attract more firms, more competition. And hence, in order to stay competitive, each firm has to lower their prices for their goods. Exactly, then excess production will also lower prices for goods. If I'm producing too much, I need to lower the price of my good in order to sell it. So this is essentially what is described by this first equation. And what the second equation describes is essentially that on the one hand, excess production obviously leads to lower production over time, and profits increases production. So if I'm making lots of money with my product, I might maybe increase production. So you can introduce these kind of rules to introduce a time component, let's say, into your system. And these rules can be rearranged or rewritten in order to take into account the network structure. Again, the equations don't matter. What you can see here is that the evolution of prices and production of each firm, which are the two key variables, depend on the network structure and depend on a number of other variables, such as labor, the consumption preferences of different households, et cetera, et cetera. The main key point here is that if we're considering n firms, we will have 2n ordinary nonlinear differential equations. So of course you can simulate it, but well, I was spending some time in France, and in France they really like analytical stuff. So our goal is to also introduce some kind of analytical tool to study these kind of problems. Okay, so I mean, just some simulation results here about the different phases that you can get. Yes.
Sorry, but what's the network that you're considering? What are the edges? What are the edges there? Do you have weights? What's happening?
Okay, so essentially this is your adjacency matrix, and this is your network essentially. And ultimately, the network structure should be dictated by data. So you look at the actual economy. It tells you what kind of input-output relationships we have. But I will come to this later in order to study this analytically.
Link represents a firm sending goods to another firm.
Yes, yes. Oh, sorry, I should have made it clearer. Does it answer your question? Yeah. I have one generic representative household and different nodes for the different firms. Yeah. Okay. Exactly. So you can simulate it, and you will have different phases, ranging from competitive equilibrium, which is the standard economic equilibrium that you can recover naturally, as you would expect. So in this case, supply is equal to demand, and profits are zero. You also find so-called deflationary equilibria, which is where supply does not equal to demand, and profits are not necessarily zero, but you still have a equilibrium state. And then you have well, some kind of crisis states and also oscillatory dynamics where prices fluctuate over time. So this is just to give you a bit of insight about the kind of phases or different behaviors that you can get from this very simple toy model. Now I would like to introduce the method that one can use to study such phenomena more analytically. And this is so-called dynamical mean field theory. So it's originated in condensed matter physics, in statistical physics, and it has been applied to spin glasses. So, or aging in spin glasses, essentially what it means is that you have a system with a different disordered system, essentially, with different magnetic moments that interact. And the system will go through different equilibria, and the transition time between one metastable state to another will increase over time. But okay, let's maybe not come to physics here. Where it has also been applied actually is in theoretical ecology, which is also very interesting. So for instance, in predator-prey models, where it's kind of like a, well, I think you mentioned it early in the morning, like cooperation and non-cooperation. So you have these kind of interesting dynamics where you have a number of species that either work together, or, I mean, since it's called predator-prey, get eaten or are the predators. So this is some interesting work that has been done, for instance, by these people. And okay, what is dynamic mean field theory, maybe in a bit more technical terms? So it's a way to map these n interacting degrees of freedom, or these n coupled differential equations, onto just one self-consistent stochastic one-body problem. And the reason that this works is because of the central limit theorem. So you assume that the adjacency matrix of your network is random, and that it is Gaussian, or at least that the two first moments are Gaussian. And the main assumptions are, well, that fluctuations are modeled by white noise, and that the complex behavior of the random interactions, so the interactions are essentially the links, that they are Gaussian and given as such. And then you can do that again, forget about the equation, but there are two main things to take away. One is that you get a stochastic, just one stochastic equation. The stochasticity is captured by these noise terms that you get, and you get an n dependence, n being, in this case, the number of firms. And since you want to take the n to infinity limit, you have to rescale certain quantities. And in order to get something reasonable, and this is maybe also where I would like to discuss with you guys. So you can, typically what is done is, for instance, if you apply this to predator-prey models, the interactions, well, can be smaller, larger than zero. So you can just assume a Gaussian distribution. In this case, however, since the links represent the goods that are bought from one firm to another, we have this additional constraint that the interaction between different degrees of freedom, in this case, different firms, have to be larger to 0. And this, of course, constrains a bit the nature. I mean, since Gaussian distributions by nature also have negative components, it constrains a bit how you scale. In any case, what we find, or a scaling regime that can be identified, is one of a so-called homogeneous economy, where essentially the relationships, the average interaction strengths between the different firms are peaked around some constant value, and the variance, yeah, exactly, are peaked according to some delta distribution. Okay, so in any case, enough with the technicalities. You can then take this stochastic equation that you obtained by your map, and you can, well, study it. And what you find is that you're able to recover a so-called the so-called Hawkins-Simons condition, which is a result in economics, which is that for a certain for a certain parameter in the structure of your network, the price, the economy becomes unstable. And this you can see by the fact that, so what I've plotted here is the probability that prices of goods are larger than 0. And obviously, if the probability is 0, it means that there are prices that are negative, which doesn't make much sense. So this kind of transition between a, let's say, sensical economy where prices are positive to a nonsensical economy where some prices are negative is the so-called Hawkins-Simons condition, and it's something that well, you're able to also recover with this so-called DMFT. So how much time do I have actually?
Yeah, 10 minutes left.
Oh, 10 minutes. Okay. Exactly. So what we see, I mean, and this is of course compared then to our simulation results where we ran it for different firms. Exactly. Let me also maybe conclude with some open questions that I'm still exploring, or as it's still an ongoing project. So we've introduced DMFT as an analytical tool to essentially study systems where you have different interacting degrees of freedom. We found that it reproduces the correct probability distribution of price and productions. We also found that the Hawkins-Simons transitions were produced. What we would like to do, of course, is because this method heavily relies on the fact that you take the n to infinity limit, so you assume infinite number of firms. What would be interesting is to also see how well it performs when you assume well, finitely connected graphs or just finite number of firms. And we would also like to explore other potential scaling regimes for more realistic economic applications, because so far it's a bit, it's towards economic applications. Yes, so thanks a lot for your time, and I'm happy to discuss and get input.
Thank you for the talk. Is there any questions from the audience?
Yeah, I was quite intrigued. It seemed a little surprising that you got your periodic shocks without any exogenous input. Do you have any insight into how that? Oh dear, that's how that periodic shocks result comes about.
So I should say that for these periodic shocks, there were also a number of additional. Oops.
Oh, Matt, can you zap that for us? Yeah, you're good at one equation too many. There we go. Right, yeah, it should be controllable now. You know the graph with the periodic shocks.
Yeah, I'm doing something which I shouldn't, I guess. It doesn't want to see you there. Oops.
Oh dear. Oh yeah. Oh, well, anyway, we saw what the exogenous shocks. We saw what the model looked like. But it still managed to get those features just for the differential equation.
So there are two things. First of all, the simulations that I showed here assume some additional parameters, but also, for instance, if you think about like I don't know if you know the Lotka-Volterra equations. It's like a predator-prey equation. So
don't ask me to write them down.
Okay, so you kind of have like what is called a limit cycle. So I think in like these predator-prey equations is quite intuitive because say I don't know, like you're a wolf and I'm a rabbit, or we are like there's a wolf population there and there's a rabbit population there. Then, you know, the wolves would maybe start eating the rabbits. The population decreases. As the population decreases, the wolves are losing food. So also the wolf population decreases. As the wolf population decreases, the rabbit population goes up, and you have these like
you can pull
and it's something similar is going on here.
Does that similar intuition apply to the one that had what seems to be long periods of nice flat equilibrium and then these sharp spikes?
Yeah, that's a bit different. That's the additional parameters that I did introduce that make it. So that's a different.
Could you give us an intuition of why it seems so stable, and then what is internally happening that pushes it out?
So there is a technical explanation for it, which is that, but
you could start with the technical explanation.
So usually when you study like systems close to equilibrium, you do it by introducing a so-called stability matrix, or looking at the stability matrix around it and studying the eigenvalues. In this case, actually, it's a bit funny because it's like there's a switch between the stability matrices. So yeah.
Thank you.
Thank you very much for the presentation. Actually, it's a very related question to this. Had you looked at how this compares to the work by Didier Sornet with endogenous shocks from within systems right before crisis points?
Yes, I mean, I haven't compared to it. I'm aware of his work, and it's kind of a similar phenomenon in the sense that what people usually do is they have some kind of dynamical system, and then they kind of study the equilibrium properties around it and how the system approaches equilibrium. And I think he does something similar in some sense, but I haven't. Yeah.
Thank you.
Any more questions? If not, I might ask another question. It's on, I think, a similar line to Richard's question about how you get similar effects to an exogenous shock over time. I wondered if you might be able to comment on how you might distinguish if you're looking at real data, how you might distinguish these exogenous shocks from something that could be more caused by something like this out of equilibrium.
Yeah, well, we're talking to this. Yeah, I think that's a very good question. It's also a bit the aim in some sense. For that, of course, first you need data.
Yeah.
Then you need a good model to calibrate. And then you also need to study your exogenous shocks within the data compared to the model. So it's more of a long-term thing, I would say. I hope it answers the question.
Yeah, no, definitely, yeah. Well, if there are no more questions, then let's thank Johannes again. Oh, so, what goes to none.
I'll just put this down.
Oh. Got these in lectures at work.
Oh yeah. I use a handheld mic. I don't have any pockets.
Oh really? When you're lecturing?
Today I don't have any pockets, so
okay.
So yeah, for our next talk, I'm happy to introduce Mario Bazic from the University of Warwick, speaking about mesoscale structures in temporal networks. I shall hand over to you.
Thank you very much.
Go there for the
Thanks.
slide.
I might use this every now and then, and I can keep it on here for the next speaker if you want a pointer. Does it work? It does not work.
I suspect laser pointers don't work.
Was it? Did you see a little red light?
It only works on the wall, not the
well,
sides.
that's useful.
With the LCD displays.
Okay, cool. Well, thanks. Except the slides. Convenient. Good. So thanks a lot for inviting me to this workshop. I wanted to come sooner, but I was lecturing today in Warwick and I got here just in time, which is tough luck for me, but at least I made it. Okay, so it was suggested that communities and temporal networks might be a good theme for this workshop. So instead of talking about just communities, I thought I would just speak of mesoscale structure, which is a slightly broader lens. And most of this work is kind of 2 years old, so in these two papers. And one of them is actually with a collaborator, Lucas Joib, who's currently at Raphtory Pometry, but obviously a lot of collaborators were involved. And in the end, I'll talk about some ongoing work as well. Okay. So I'll start with a bit of an intro where I'll define some of the terms and try to set the scene. And then in the second part, I'll talk about a generative model for mesoscale structure. So we won't be so much concerned with detecting it in this talk, but rather suggesting a model that can generate mesoscale structure in temporal networks. In the third part, I'll talk about a type of mesoscale structure, which is known as core periphery. So different to communities, but both can be viewed as mesoscale structure. And then I'll make some concluding remarks. Okay, so what is mesoscale structure? One way to motivate why it might be interesting is if you're working with a network, it can sometimes be quite useful to zoom out of structure that lies at the micro scale, so nodes and edges, and structure that lies at the macro scale, say total degree distribution, and to kind of coarse grain the network in some way. And there's different types of mesoscale structure that exists. By far, the most studied is community structure, but there are others. One example is core periphery. I'm assuming everyone knows what communities are, so I don't need to define that. So core periphery, where you've got two sets, a core and a periphery, dense connections within the core, dense connections between core and periphery. So up, we've got the adjacency matrices and down the network, and sparse connections within the periphery. And what these two structures have in common is that they yield a partition of a network. So the object that you end up with is a partition where you've got sets and nodes and sets. In core periphery, you'll have two sets, unless we have multiple cores, multiple peripheries. And in communities, I guess the maximum is the number of nodes. If every node is a singleton. All right. So I'll be mentioning these two in today's talk, but I'll also mention another type of mesoscale structure in the very end. Yeah. Oh. So what I'll mean by temporal network here is basically a sequence of adjacency matrices where every adjacency matrix corresponds to a time window, say. There are other representations that exist. So you could think of events maybe happening at different points in time that you could aggregate over an interval to get this. But in this talk, we'll be working with sequences of adjacency matrices. And this is just a toy example. You'll be seeing a lot of toy examples. I hope that's okay. Where we've got two snapshots, 3 nodes in each snapshots, and no weights here. So an edge is not there and then appears. LinkedIn is a little bit random. This could be anything. But this is what we'll mean by a temporal network. And I included one from real world data on the next slide, because it's important to remember that we are interested in empirical networks as well. And it kind of shows nicely that structure can vary non-trivially. So this is an example from so Pearson correlations between price time series of financial assets over time. And it might be interesting to see what this looks like today, but I don't have it on this slide. And this is a project that I did many years ago with HSBC. And I think there were about 100 nodes in the data set, so 100 different assets, and 238, I think, snapshots. That's too specific to be wrong. And here, it was a long project. I remember it well. Here we've got 6 of them, pre-Lehman and then kind of post-Lehman. And the blocks on the diagonal are assets in the same asset class. And on the off diagonal, you've got Pearson correlation between time series assets in different asset classes. And you can see that government bonds kind of stay tightly connected, equities to an extent, and correlations between these asset classes vary over time. And
sorry,
yeah.
E is the first post-crisis one.
Say that again?
You said post-Lehman with E, which is the first E?
F. Yeah. And interestingly, I mean, this might be a feature of how things were constructed. We never quite cracked it, but this bimodal structure, so you see the tight correlations at the top, tight correlations at the bottom, seems to emerge earlier for some reason. But yes, maybe something to investigate at some point. But I think one thing to highlight here is that when we think of temporal networks, we can think of structure changing gradually and abruptly. And so this might be an example of what some call a change point. Yeah.
What's the
good question. So here I guess 1 year is one. So the time points were weekly closing price, yeah, of every stock. And then we aggregated, so we computed the Pearson for every time series 1 year, and then we rolled. Yeah. Okay, so this is just to show empirical data, and it's kind of a nice visual to keep in mind when we think of temporal networks. So going back to when I mentioned communities and core periphery, I said what these two have in common is that they yield a partition of a network. So nodes fall into sets. If I'm speaking of a partition in a static network, so a usual network, this is just a toy example on the left where circles are nodes, colors are sets. I'll use the term mesoset just to kind of emphasize that communities are not the only type, but if you forget what that means, think of communities. So on the left, we've got two mesosets and 3 in one, 2 in the other. And when we speak of mesoscale structure in temporal partitions, we'll be thinking of a partition on NL nodes, where L is the number of snapshots and N is the number of nodes in every snapshot. And if we just represent it as column is a snapshot, and here we've got 5 nodes in every snapshot, it's something that looks like this. Yeah. No. So what you see on the right here is that sets can kind of extend over time, right? They might appear, they might disappear. And one of the key differences between the object on the right and the one on the left is that structure in a given snapshot tends to depend on structure in prior snapshots. So in the next bit, we'll be kind of looking at a model that proposes a way of generating these types of objects. So temporal partitions, so mesoscale structure in temporal networks. Okay. So when we worked on this, we kind of zoomed out for a moment and we thought, so what is the goal of having a generative model for mesoscale structure? So what is a generative model? Broadly speaking, I mean, if one is interested in the real world, you can think of them as synthetic networks that can look like the real world depending on how you constrain the parameters. Mesoscale structure is ubiquitous. So in a lot of empirical data, we know that we can find it very often, sometimes multiple at a time, but it's an ill-defined problem, right? There's so many different methods for finding any given type of mesoscale structure. There is no unique definition. And often that is dictated by the method and potentially the algorithm one uses to optimize set quality functions, say. And there's an abundance of generative models in the literature, and they've been used in different ways. Maybe 3 worth highlighting here are One way is to try and better understand methods for detecting mesoscale structures, so benchmarks. And there's a lot of examples of this in the literature. You can also use your model to develop a statistical inference pipeline to then infer structure from an empirical network, and investigating detectability thresholds. And there's examples of each one of these in abundance in the literature. So it's kind of arguably important, but it's also quite hard. If you think of a static network, there is a lot of different properties that you might want to capture, right? The real world can exhibit parallel or some other heavy tail distribution, heterogeneous community sizes. You could have spatial embeddedness, weights, directions, etc. And typically models that you come across can capture some of these at a time, but not all at once. So there's already kind of a lot of characteristics in single snapshots. In temporal networks, you inherit all of these, because in any snapshot, you've got a network, but you've also got this notion of dependency. And at the time, what we found was that many existing models, you either didn't have an explicit parameter for dependency, or if you did, it was restrictive in a way that you might not want when working with empirical data. So what we tried to do is to suggest a framework that could generate the richness of features and characteristics, that list between parentheses I had on the prior slide, directed, spatial embedded, etc., that you encounter at the level of edges, but also at the level of dependencies, where you might have non-Markovian dependencies, change points, if we reimagine that correlation network kind of pre-Lehman, post-Lehman. So how did we suggest to do this? So one first choice that we made in our modeling framework was that we modeled dependencies at the level of partitions, not edges. So what that means is if one specifies the type of temporal dependency one is interested in, and I'll be more specific about that later, the model generates a temporal partition. So that picture that I showed you when I contrasted a static partition to a temporal one. So this is the object that it generates, just to go back to it, the one on the right. And then for a given partition, so imagine those little circles and colors, for any individual snapshot, you can choose your favorite stochastic block model and generate edges. So all the models that exist that cater to different things, one can use. Okay. And then we specified a conditional model. So to achieve that, we specified a conditional model instead of a joint probability distribution on community assignments or mesoset assignments. And the model is governed by two parameters, one that we called a null distribution and a second that we called a dependency matrix. The first one allows you to capture certain features you might always want, like the sizes and the numbers of mesosets can change over time. And the second is kind of a key one because it allows you to encode what dependencies you're interested in. You know, is it a kind of uniformly gradually evolving structure? Do you want change points, etc.? And I'll give examples of P very soon. And then we defined an update process that iteratively updates the mesoset assignment of nodes. And it's kind of worth highlighting that while in temporal networks, you have the notion of a start and an end, so your iterative process can just go over the snapshots. This works for, I don't know how many of you are familiar with multi-layer networks and kind of their generality. And when we think of multiplex networks where there is no notion of order, this becomes kind of non-trivial. And this would work even on multiplex networks that change over time, but I'm not going to get into this, but we do discuss it in the paper. But here we're focused on temporal. So I'm not going to get into the mathematics too much, but I just want to flag what update equation we defined using these two parameters. It looks notationally rich, but it's actually quite simple what it's saying. This is where I would have used the pointer. So at the very top, it's basically saying, what is the probability that a node I in snapshot alpha has a label S, given the assignments of nodes in prior snapshots beta, where beta is strictly smaller than alpha. So we're respecting the temporal ordering. And there's two parts to this. So either a node I can copy the assignment from another node that has the same assignment in a different layer beta, So you either copy it from another layer or snapshot, or you get assigned the label S via the null distribution if you don't copy. And so here you can see that if the copying probability is 1, assignments are just going to stay the same in time. And if the copying probabilities are 0, they're going to get assigned via the null distribution independently for each snapshot. And this is just an example choice that one could make for the null distribution, a categorical distribution. But I'll show you examples of this, so don't kind of worry too much about this not becoming clearer, hopefully. So this is an example of what one could define as a temporal dependency matrix. So we said there's two main parameters, the null and the dependency matrix. So these copying probabilities on the first off diagonal, if they're all equal to some, let's take the extreme case, they're all equal to 1, then structure doesn't change at all through time. They're all equal to 0. Structure gets generated with the null distribution independently for every snapshot. If they're all equal, period, to some other value, then you just have a kind of uniformly, gradually evolving structure. You could introduce change points by taking kind of high values and then dropping to 0. You could have non-Markovian dependencies by populating further values on the upper triangular. So one could specify this in different ways. So this is just another toy example to show you what this could look like if we're imagining a simulation. So initially nodes are not assigned to any set. You assign nodes in the first snapshot via the null distribution in some way. With probability P, the label is copied. 1 minus P, you get that purple set, gets assigned by the null distribution, and you just reiterate this process. And this actually appeared in Gassemian et al. For uniform P on the first off diagonal in 2016, this particular model. And there are some nuances here. So for example, the support of a given snapshot has to intersect with at least one support of a prior snapshot for communities or mesosets to appear. Which is, no?
Give us another go at that one.
So the labels where the null distribution can kind of give you that label with a non-zero probability. So the support of a null distribution on a snapshot must intersect with one of the prior snapshots for a community to grow, because at any given step, it shrinks. Yeah, it doesn't. Yeah, it's not a key point. It's just a yeah.
There's a different null distribution for every time point.
There is a different. You can have the same one. You can have different ones. But you're right that the null distribution is snapshot specific. So there's a subscript S, I hope. Sorry, alpha. So this denotes that it's, yeah? Yeah, Shoaib.
Null distribution, I guess, provides the main expertise or random?
The way that it's been used, kind of a sensible choice, but if you have a good reason, you probably don't want to, if you choose something biased where you get assigned to the same set, so probability of 1 on label 1, like think of the impact that it could have on the resulting structures in a sense. But categorical null distribution is a common choice. So you have an upper bound n subscript C, I think I denoted, on the number of mesosets, and you assign a probability of being in each set. In the Gassemian et al., they had equal probability, but you could draw them from a Dirichlet distribution. Yeah.
Similar question, no ex ante how many distributions there might be, either by snapshot or how many mesosets you have?
You could set NC equal to big N, which is the maximum possible number of mesosets, or you could statistically infer that potentially from the data. So that's something we're hoping to have as follow-on work, kind of statistical inference, but yeah. Okay. Okay. So this is example on synthetic networks. So, and by examples, I mean examples of temporal partitions. So equivalent in terms of what they are to the little circles and the colors, except that here the colors are mushed together. So it's kind of a continuous representation. On the left, we've got P0, and I think we had, huh? Yeah, exactly. So everything assigned via the null. I think we had some kind of bound on NC and a categorical distribution. On the very right, we have P is 1. So this is kind of what you'd expect. Everything stays the same. If it didn't, we would have found a bug in our code. And then kind of values between them, things look a little bit the same, but yeah, not quite. And as you approach one, more and more so. How am I doing on time, actually?
Yeah.
So 0, okay.
Yeah.
Sorry. All right. And then in the bottom row, this is just a measure of similarity between the induced partition on every snapshot. So all reds, they're all the same. Low numbers, probably that's not 0, not. All right. So I'm not going to go through this in detail. It's just to say that one appealing feature, which doesn't quite hold for the multiplex case, but in the temporal case, it's quite tractable. So you can compute some probabilities explicitly, which is not always a given. So these are just some probabilities that could be of interest in a temporal network, like the probability that a mesoset appears, and they're not actually complicated. I could walk through them, but I'll skip it for now. If somebody's interested, I can come back to this slide. It's just a flag that there's a degree of tractability that might be appealing to some people. All right. So far we've talked about generating a partition. Like I said at the beginning, one of the key choices we made when designing this was that what we produce is a temporal partition. And then you could choose your favorite stochastic block model to generate edges. You could also consider adding edge level dependencies, but here we're just talking about dependencies at the level of a partition. So I'm going to show you some numerical examples before going into this. So I don't know if you remember on the slide where I kind of motivated what a generative model is. One of the first ways in which this is used is to benchmark techniques against each other. So I'll show you a numerical example where for different values for different dependency structures, we generated a partition. Using a specific SBM, we then populated edges within this partition. And we did it in a way where the structure would represent community structure, so denser connections within sets. And the two approaches, so the method that we use to detect these sets and the experiment I'm going to show you is known as multi-layer modularity, so an extension of modularity to temporal networks. You could use any method you want. And the algorithm is Louvain. So I'm just going to spend a bit of time on this slide to say something about a way to detect communities in this talk. But the point of this is just these are the tools we used in the experiment I'm going to show you. But instead of having that as a black box, I'll say a little bit about it. So how many of you are familiar with modularity? Oh, okay. So what this is saying, so L is the number of snapshots and N is the number of nodes in every snapshot. If we assume that there is just a single snapshot, so L is 1, this is going to reduce to the left-hand side term, which is standard modularity optimization, where you have an adjacency matrix, so observed data, that you're comparing against expected data in a null network. So A minus P, and you try to optimize over the set of partitions where you want to have as many edges with Aij bigger than Pij within sets and edges with Aij smaller than Pij between sets. Now, in this generalization, on the left-hand side, you have standard modularity for every snapshot. And on the right-hand side, there's, if you like, you can think of it as an incentive of assignments to kind of carry forward, so to remain the same across different snapshots. And this has been called persistence in the literature, kind of, I guess, rather intuitively. And omega, you can drop to, and it doesn't change the optimization problem, is an incentive for persistence. So what this is finding is an NL partition, a partition on NL nodes, such that you have a trade-off between what is optimal for every snapshot and what persists across. And so a solution here, so C in calligraphic C, is an NL partition. So that's just one way to find the object that we're generating. There are others, of course. And to optimize this, so you can represent this as actually just one big NL by NL matrix. And you can use Louvain algorithm, which is quite popular in the field. I made this bit red, so I won't go through Louvain, but I just want to make one comment on the bit that I highlighted in red. So Louvain in its original form is a greedy algorithm where you move a node to a set if it maximally increases your quality function. And you flip a coin if there's multiple such directions. In the case of a temporal network with this quality function, This introduces a bias where it overemphasizes persistence as of a point. I won't get into that, but I'm happy to discuss kind of offline. So in the experiments, you'll see we relaxed the greedy aspect of the algorithm and we moved to a node to accept chosen uniformly at random that increases the quality function. So we still have increase at every move, but uniformly at random. So I'm going to show you the experiments and I'll skip. So this is a slide where I basically just show in a toy example what multi-layer modularity might give. I'll go through it quickly. 3 snapshots. Node 13 has more connections to the clique on the left in the first snapshots, more connections to the clique on the right in the second snapshot, more connections to the clique on the bottom right in the third one. For low values of omega, it's going to put node 13 with each one of these cliques. For higher values of omega, you emphasize kind of persistence, and node 13, instead of staying with that clique where it has more connections, is going to move to the clique where it has fewer but persistent connections. So just to kind of plant the idea in a toy example. And you could think, I mean, yeah, in the real world, might have small circles of close friends that have persisted through time, and large groups or transactions in a financial network that tend to occur and reoccur and might be of interest. So going back to the main topic of this section, that was a bit of a parenthesis. So what we have here is a few things happening in the background. Yeah.
Is the fact that the actual label of the Mesoscale community, that's not really informative, right? It could be, you call them ABC, call them
correct. Yeah.
Is that a problem with your quality function at all? Is that a problem with your modification for the algorithm?
No, do you mean, is it dependent on?
Because you're checking if a community is persistent through time.
Yes.
But the actual value of the community is not really a meaningful quantity, right? So you're checking if the community label is the same in 2 time steps.
Which is basically saying, are you in the same community? Though you see, from the perspective of a quality function, it interprets it on a partition level. So are you in same indicator function value 1 if same community, with your community denoted by, A1, 3, ABC. Do you see what I mean?
So if for say 1 layer, for 1 time point.
Yeah, layer time points.
I commute the community labels.
Yeah.
That would be the same solution, but it would be a terrible.
But you have to think that a label. So if you change, imagine that you've got a community labeled 1 in snapshot 1, and you've got in snapshot N is a bad choice. In snapshot K, label 1 appears as well. If you change 1 to something else in snapshot 1, you need to make sure that you remap it in other snapshots. But if you do that, then it's exactly the same. Yeah. Okay. So there's a few. Yeah.
Now I'm a little curious about the sort of ship of Theseus problem with communities, where you're sort of changing one person at a time so that the label is the same, but it's completely different people by the way.
Say that again. I should have parentheses took us on a parentheses.
You're changing, you've got a community of whatever people, and one person drops out, another person joins in slowly over time, so that by the end, they're sort of the same community, but they consist of completely different sets of nodes of people. Different Theseus.
So when you say the same community, you mean like size?
I guess I'm not sure what I mean by same community. That circumstance. Same label.
So it could potentially have the same label
with continuity over time.
But are they the same nodes that belong? So we don't.
Each time step it has mostly the same nodes as the previous time.
But they just drop.
Drop, add. So over time, it's completely new people. With their
gradually.
Yeah, gradually.
Yeah. So it's kind of like, if you think of it with probability P, you've got one drop, like, if you've got, I don't know, big K members, K minus 1 copy, K minus 2 copy, K minus 3 copy, something like that is what you're imagining. Okay. So we can chat about that more later just to see what you have in mind. So what in relation to that were you curious about? Or we can.
I guess I was curious if you would call it the same community or how you would deal with that. Maybe
so how you link sets across snapshots.
Well,
I can.
Yeah, maybe it's an answer.
No, not at all. So you basically, this would be linked. So persistence basically looks at the sets that have the largest. We can get into this. I can show you, but there's definitely results on this. And there's an algorithm, I think called the Hungarian algorithm, that comes into play in terms of how induced partitions get linked, but I'll tell you more about this. Okay, how are we now on time?
13 minutes.
Okay, cool. Okay, so this is the last slide of this part. So this is just an experiment where here's how one might use this to gain insights into ways of finding sets in temporal networks. So there's a bunch of parameters and things going on in the background, but you've seen basically everything by now. So we have the generative model, and with it, we generate a partition, and with a stochastic block model, we generate edges. Here we use DCSBM. The quality function that we're using to find communities is the one that I showed you in the prior slide, and the algorithm is Louvain with maximally increases relaxed. P is the copying probability. At the top, we have the same P on the first off diagonal, so gradually evolving structure. And then on the bottom, we have change points. So a high value of P followed by 0, I think every 25th snapshot. And what this is, one thing that is kind of perhaps worth noting here is the structure can be detected. So the intercept with the y-axis is how well you detect the planted structure if you look at every snapshot independently. And whenever you have movement away, so above the value that intercepts with the y-axis, you're doing better than you would do if you're looking at every snapshot individually. So this was kind of informative to see that it happens for a certain regime. Unclear why it tends to be the same value. So that's an itch I've had that I kind of want to better understand. But by doing this for different algorithms, we kind of got some intuition into their quirks. And it was easier to see on those controlled experiments than when we just applied it directly to empirical data. So this is one use case, but it can be used in different ways and on not communities, which I'll briefly go through in this part. So here we'll talk a little bit, it's going to be a much shorter bit, on core periphery. So the second type of mesoscale structure. And this was introduced many years ago by Borgatti and Everett. And in its original form, you partition a network into two nodes, core and periphery. And what we did in some collaborators from Oxford and Turing at the time was we suggested an extension of traditional core periphery to directed networks. And as far as we knew, at least back then, the definitions of core and periphery didn't really exist in a direction-dependent way. One exception is bow tie structure, where you basically have a core, which is the largest strongly connected component, and a periphery in, periphery out, which have paths that respect the in and the out subscript. So Yueting is actually working on, my PhD student in the audience is working on bow tie structure in social networks. All right, so this is one generalization that we focused on in the paper, but there's obviously many other permutations of this that you could consider. And we have an appendix in the end that looks at them. Convincing you that this is meaningful is not the purpose here, but I'll just go through it quickly in terms of what it says. So we have core and periphery. We have a core in, core out, periphery in, periphery out. We assume that you can have dense connections within C out and C in, and connections between the peripheries and the core, but sparse connections within periphery and between periphery. And out and in means that the arrow has to respect that. But there's obviously other constructs that you could do, and we go through various in the appendix. And the particular one I focus on here is besides the point. But if you reorder them in this way, the idealized, if you like, stochastic block model will look like this. You'll get ones on that L and 0 outside of it. And you could just easily have a synthetic SBM that generates the structure with varying degrees of noise. And the point I'd like to make here is you could generate directed core periphery or standard core periphery using the temporal generative model, right? You could constrain the number of sets to be equal 2 or 4. And if we had the copying probability equal to 1, say, with a different SBM for every snapshot, your adjacency matrices would look like this. The sequence would look like this. So I just wanted to kind of make that point because I get asked often, can you use it to generate things other than communities? Yes, you can. You could use it for bow tie, you could use it for core periphery. And this is just an example of that. Okay. So some quick points. So we looked at a model for generating mesoscale structure. We saw different types of dependencies one could specify. It's possibly appealing that you could use any SBM to generate edges. There's many different models, even non-SBMs, to generate edges. And you could use it to model different kinds of mesoscale structure. We saw communities, we saw core periphery. Some work that is ongoing. So one is on inference, and this is also with Lucas, and we're kind of hoping to develop an inference pipeline for temporal networks. Other work on mesoscale structures, so early stages of Yuting's PhD on bow tie structure and social networks, where we look, the subject matter is kind of differing vaccination views, but you could apply it to other kinds as well. Graph embeddings, which you could also think of as a type of mesoscale structure. We move from a network, right, to a set of n vectors of k dimension. And this is some work we're doing with Turing and GCHQ. And yeah, interested in the application of online media, which I haven't worked in that much to date, but hopefully will soon. And Shuaib, who's also in the audience, I didn't know you were going to be here. Also working on recently mesoscale structure with trophic analysis tools. Good. Thank you very much.
Thank you very much for a fantastic talk. Can we take some questions from the audience?
Hi, thank you very much for your talk. One question about the case of community detection. You're using modularity, right? As you're using Louvain
Yeah,
in
so
the first
here,
part of the
multi-layer modular. So it's
yeah.
like a generalization of.
Right. Does it also suffer from the resolution limit? I would assume so. Like have you considered that as a problem? Like the resolution limit is here to modularity?
In all of the ways that it applies, it will apply.
Right.
If the term on the left is modularity, you could insert, that usual resolution parameter, but there's kind of other ways also to deal with that now. So the little, yeah. But there's other techniques that you could try to mitigate the resolution limit, and you also have some results that it's attenuated if you use a uniform null network. There's some work by Trag on that. We can talk about it more. But one point that you kind of reminded me that I didn't highlight is so long as the term here can be written with a matrix B, and B doesn't have to be modularity. It doesn't have to be A minus P. You could have stability, which is a dynamics-based quality function that was introduced by Lambiot and Delven and other researchers. You could have that there. So the kind of the shape of the maximization problem needs to look like this. You need to be able to rewrite it as a matrix. It might apply to other forms, but it definitely applies if you can write it as a matrix. And the B's can be anything. Yeah.
Thank you.
Actually,
Richard?
I am actually really
We actually
interested.
started looking at that method with semantic change.
Yeah, well, I mean, I accidentally, I'm embarrassed to say, wrote down this equation the other day. I didn't realize it was,
When we were collaborating,
I should have just read your paper more thoroughly.
This is an older paper. The modularity.
But yeah, I was interested. You said there was other ways than the resolution parameter of
So
fixing the issue.
there's one where you vary the edge on the self loop. This is an approach that Irina suggested a while back. I can point you to the paper.
Yeah,
and I suspect there's more going on around
love
there.
to hear about it.
Yeah.
Love to hear about it. So okay, so whenever you have time,
Yeah,
I'd love to
absolutely.
be educated on that one.
Absolutely. Okay. Good. Yeah. Thank you.
I was going to say, I might have a quick one. So when I first joined the Raphtory project, we were looking a little bit into this with the word semantic change. And one of the things, and one of the things I was curious about was if how the results might be different if you have the omega or the sort of interlayer strength, rather than being something that's uniform across the nodes, having something that's might be a function of node degree in one of the layers or something like this, and where you might get some.
We looked into that a little bit at the time, and what we did was, and when I say at the time, I mean probably like not a decade ago, but many years ago, and it was defined, you used how similar. So we started with omega 0. We looked at the induced partition on 2 consecutive snapshots. We computed the similarity in some way, and we made omega scale with that. And interestingly, when we reiterated, it converged very quickly to a given value. But there's one paper that came out more recently. I can point you to it. It's by Roxana Pampo and other collaborators, where they link this expression of modularity to stochastic block models. So they follow a paper that came out by Newman, where he linked static modularity to SVMs, and they extended that to temporal. And there you can show that there are choices for gamma, so the resolution parameter, and omega, that are best fits under certain assumptions. And I think that would be an interesting direction to go into. And I think it makes it heterogeneous across different pairs of snapshots.
Fantastic.
But I'd be curious to hear more about what you looked into later on having a different choice of omega.
Yeah, definitely.
That's not
That
an
would be
overly explored area of investigation.
Yeah, that'd be great. Thanks. Yeah, and yeah, I'd love to have a look at that paper.
I'll put admin too.
Yeah, thank you. If there are no more questions from the audience, let's thank Mario again.
Yeah. Something that, no? Doesn't say. See. I don't know. Where did the other people have it? Yeah? Yeah.
That sounds good. So for our final talk of the day, I'd like to introduce Andrea Barron-Kelly from the City University of London, who will be speaking to us about dynamic networks in blockchain ecosystems. So thanks, I'll hand over to you.
Thank you very much. It's been a great workshop so far, so I will ruin it and also take a huge time subtracting it to your weekend. No, so it's a lighter talk, less formal, and networks will come. But how do I advance? Like this. So let's start with the first part on dark web marketplaces. So my first task is to convince you that they are not something so weird. They are accessible with Tor. Many of you may be familiar with them. Those of you who are not familiar with them, they are basically very similar to the platforms we use to buy any goods on the normal internet. Tor is nowadays becoming more and more user-friendly, and their market is growing. The big difference is that they sell goods that include, that are no restrictions, and they use cryptocurrencies. Bitcoin is still very popular. In the latest years, more privacy-preserving currencies have started to grow, but for network effects, Bitcoin is still there. The first one was Silk Road in 2011. And you see already at the time, the interface was pretty friendly. You had, this guy was selling, I don't know, MDMA or something. And there are reviews. A good vendor would use again, 3 hits and 1. So today there are hundreds of markets. Okay, of course, the distribution, as you can imagine, is very heterogeneous. So only a few, as we will see, are significant, but the role of the others is not negligible. So the first thing is a very gentle introduction and see what happened during the COVID-19 epidemics. Okay, so how did they react? This is a way to bring you there. This is also the last talk, so let's see. So what we saw is that the offer is large and diversified, and the dark markets reacted very quickly to shortages in the economy. So they were very reactive in real time to what was happening outside of the dark web and to public attention. Okay, So this is our data set. We had a lot of listings from, so listings, here we are speaking of listings. A listing is when you go on, I don't know, say Amazon, and the page you are faced with for the product you want. Okay, so you can have multiple listings for the same good. You want running shoes, you have several different listings. The data set, this first data set, there are two studies before and after the vaccine. This is the before the vaccine, is until November 16. And we found 800 roughly COVID-19 specific listings. Okay, this means that they offer goods related to COVID-19. There are countless mentions, for example, related to delays in shipping due to COVID. Of course, they also suffered. And this is a typical listing. You have, as you can expect, the listing title. This is chloroquine. You have price, you have the vendor, you have text, and you have shipping information. This ships from United States and ships to all countries. Of course, there is no customer protection. This is what the vendor declares, and then you don't know. So these are the categories we found. There are PPEs, masks, if you remember at the beginning of the pandemic, nearly 3 years ago, a little bit less. PPEs, masks were not found outside. So immediately they started gathering with offerings of like hundreds of thousands of masks. Then you have medicines. We'll go more there, which include vaccines at this stage. Then we will focus on vaccines. You have guides on scamming. From a certain moment on, there were governments offering funding to businesses. And so you had guides, manuals you would buy to how to get those fundings. Web domains, medical frauds. Medical frauds are clearly frauds. So medicines, we don't know. Medical frauds is vaccines offered as early as March 2020. Tests, fake medical records. They cater, this is very important, they cater to everyone. So they cater, if you want the vaccine, they give you the vaccine. If you are a no-vaxxer, they give you a certificate of vaccination. And even ventilators, Okay, this is the average price. US, UK, and Germany are major players in terms of ships from. Again, this is self-declared. You may want to choose a vendor that ships from the country you are based in, but yeah. The interesting thing is that there are several markets that are involved. So there is no a market that is specialized on COVID-19 stuffs. Several markets offer different products. Again, this is a fast overview. The interesting thing is that vendors are are typically not specialized. So this is the number of products a vendor offers for non-COVID-19 related goods, and this is what they offer for COVID-19 related goods. And you see the mass is above the diagonal, meaning that they are most probably credible vendor. Remember, there is a very efficient, if you want, a system of referrals there. So a vendor can scam once or twice, but eventually that you don't survive. And this is a timeline with some important dates, which is the Wuhan. Italy was the first country in the West to shut down. Then there was the first reopening, wave 2. And you see, you have more than 100. Now, it doesn't seem like a large number, but if you want a vaccine and you have 37 listings, it means you have 37 options to buy your vaccine. So it is significant. As I said, PPEs were at the beginning, you see, and then they drop out because simply you could buy them in your local pharmacy. Facts and misinformation was something we were not expecting, and also characterize them as players also in the misinformation ecosphere, if you want. So Trump mentioned at a certain point that hydroxychloroquine was it. And immediately you have that the number of listings of hydroxychloroquine goes up on the markets. Of course, if you are lucky, you are buying hydroxychloroquine. However, you are unlucky because it was not effective. Otherwise, you don't know what you're buying. But this is really a place where misinformation can be translated in quite immediate threat to your health. And then this were just the mentions. What about the vaccines? I'm going very rapidly just to give you this idea of the fact that it's a live ecosystem. all my references will be cut. That's it. This talk is used. Let's go to the pub. Okay. We now focus on the second period until July 2021. We have 250 listings offering approved COVID vaccines and also fabricated proof of vaccinations. This is a listing, one of the very first. You see very minimal, $909.8. And this is the time series, you see. Pfizer was announced, then Johnson & Johnson's, and then you had the 1 billion doses moment. And this is a very nice listing of the first vaccine. You see, it of course feeds into the conspiracy vibe. So the WHO is trying to be selfish with human life, but we have the vaccine already. Buy it for $15,000, but it was March 2020. Again, these are the markets. So again, you see the offering is widespread across markets. These are, as you can imagine, the largest at the moment, at that moment. And this is where they ship from. And okay, this is a timeline. So the important thing is that there, for example, for COVID-19, but you can imagine for drugs is much more structured. You have a diversified offer. You have a reaction to public attention, which is very, it's a market. And you have this vaccine market, which has grown a lot. Okay, now let's come to something more quantitative if you want. So the question here was, this system is very resilient. Okay, it's been going on for 10 years. So the obvious thought you might have is, let's shut down the market. Why don't they shut down the market? Well, they did. In 2013, for example, they raided Silk Road. And you see, there was even like the IRS special agent saying this is like a sign that this has no future. But of course, immediately other markets popped up. And they are really in the hundreds over time. So they are absolutely unreliable. They are illegal. You can lose money because they scam you, especially at the beginning, meaning the first 5 years, because of seizures. If the police comes, it's difficult to say, but my money for cocaine were put there. And no customer protection, of course. Even if they scam you, you cannot go to the police. But they proliferate. So what I'm going to tell you is that they have a systemic resilience. So the single market is very fragile, but together they form an ecosystem which allow them to survive. And the reason why single market closures have little impact is because users migrate very swiftly and in a coordinated fashion. So I'm now showing you that they go together to a runner-up, recreating the experience of a big market where they can trade. We don't look anymore now at listings. We look at Bitcoin transactions. So we really have the transactions. Previous studies analyze user surveys and partial listings. There is a low number here. I don't remember, but and the Bitcoin transactions are public. So that's nice. You don't know the identity of the user, but you know that this user is making a transaction to this other user. Actually, you don't know this. You know that this wallet is making a transaction to this other wallet. And every time, and of course, you can imagine people try to cheat with these wallets. So we have a data set that was curated by Chainalysis, which is the leading company for this. And what you try to do is aggregating different wallets into what's likely to be an entity. Okay. Some of these are also labeled. So we have the identity, the node of the market, and then a series of nodes of entities transacting with the market. This is our data set. This is the operation of clustering. And at this point, we have a more meaningful data set, which is this entity transacted to this entity, this amount of US dollars at this time. And this is our data set. We have 350 million transactions from 23 markets. So we would have 69, but we curated. We wanted to make sure we knew the story of the market, etc. And interestingly, many of them were created and died during our time, observation time. Okay, for different reasons, including voluntarily giving up. At the time, we observed $4.2 billion in transaction. And the question is, what happens after a closure? If you take the time series of the number of markets, you see that after a closure doesn't happen much. So these dashed lines are closures. I mean, yeah, you can go a little bit down, but the system is resilient. And also in terms of volume of US dollars, it really doesn't happen much. If I remove this, you could probably guess that in a point like this, there is a closure. But I mean, this is logarithmic scale, and overall, the damage is not big. The thing is, as I anticipated, spoiling the surprise, that the volume goes to other markets. So this is the same plot, but this is logarithmic scale and this is linear scale. And the reason is that the closed market, of course, goes to 0. And you see that the alternative markets are sucking up this volume quite quickly. So this is the day of closure. And you see, in a week, you can say things are pretty much restored. How does this happen? And this is user behavior. And this is the phenomenon we detected. So you have a migration. So imagine you have two dark markets coexisting. These are Silk Road market users. I don't know, the PDF moved a little bit, I think. Sorry about that. And Silk Road is then shut down. And you have these users moving to the other, to Sheep marketplace. Now, these are migrant users. These are not users because one stops being active. The other one was already transacting also with Sheep. Makes sense? If doesn't, please interrupt me. But compared to previous talks, this is fresh water. And non-migrant because already a Sheep user. And you see, this is data. So you have to look at this figure as a clock, starting from here. And you have the fluxes of users that go from one market to the other every time a market is shut down. And so, I mean, this also had some kind of policy impact, if you want, reinforcing the idea that trying and shutting down market is not significant. You should try and target vendors, if anything, because markets are too easy. 85% of expected returning users are active within 5 days from closure. And meaning that this goes up above 90 if you give yourself a little bit more time. And as you can expect, migrants are also the more active, both in terms of interactions, than in terms of transactions, than in terms of amount of transactions. So you really lose users that probably you would have lost in any case. That is the single purchaser of things. Now, where are they going to? They have, at any point, a series of alternatives. There is always, especially in the window until 2019, a dominating market and many small ones. So they have, you could say, but they disperse, doesn't work. Again, as anticipated, no, they tend to move together significantly. For example, in this case, this is an actual figure. When Alphabet market was shut down, if you're familiar, I mean, Alphabet was a major player. They went to ANSA, who became another major player. And in fact, this is the same figure as before, but I now disentangle the top destination and the second destination. And you see that that sagging up of the volume is concentrated mostly on a top destination. The average, on average, is 66% of the volume goes there, and users migrating, this is very important, to more than one market is only 4%. So they tend to stay one. Where do they go? In this case, there is a barrier of language. For example, the Russian anonymous marketplace was systematically very large, but is not the preferred destination. And And okay. And the preferred destination is instead Hansa. Now you can imagine different reasons, different indicators that allow you to predict. For example, is the second largest market, or is the market where there are already more common users? And it turns out, not surprisingly perhaps, that is the runner-up. Basically, the police tend to shut down the biggest guy, and users tend to go on the runner-up. And this is very important, however, because these small markets guarantee the resilience of the system.
Are there any currently active markets that are operating? If so, which?
Okay, I refuse to endorse, but if you Google this question, you can find that. Why was my analysis was done just on Bitcoin? I would love to try analyzing other currencies, but I don't have the data. Particularly Monero is quite difficult by design, but you could do this. Monero is growing in importance recently. So in that time stamp, probably was not.
How do you match the wallet market?
We didn't do that. There is a huge there is a significant literature in that. We partnered with Chainalysis, and they gave us the thing. You can have several heuristics on time. Is of course you don't have ground truth.
But they do provide
by definition, you don't have ground truth, so you don't know. But yes, but let's say now years and years of operations in the ground seem to suggest that it's meaningful. Actually, we should go into the into the details of how it works. For example, one typical thing is that you want to disguise your traces, especially at the beginning. A typical thing is you divide your pot of money across different things. So when you have a transaction from one wallet, synchronous transaction, to several other wallets, you tend to assume that these several other wallets are the same. This is really the most trivial one.
If Richard buys, I don't know, toilet rolls,
well, I'm leading to glamorous like that, then.
We all did it. Do you buy from is it sort of like a shop, or is it like an eBay where you have lots of traders?
It's more the latter, more eBay. No, this is a very important question. No, so especially at the beginning, the market would act as a gatekeeper. So you would pay the market would pay the vendor. In this interval, the market was keeping a pot of money, and some scams were due to the market disappearing at a certain point.
So the question is your data all sale? Do you sort of purchases as well?
No, I have only transactions. I don't know which good they are buying. No.
No, I mean, you don't know. It's not the marketplace who's paying their suppliers. It's Richard buying the toilet paper rather than the marketplace.
Yes, but especially at the beginning, Richard was paying the marketplace, and the marketplace would pay the vendor.
So is that in your data as well?
No, that's not an idea. No, I don't know who's, but we are going towards something in that direction with the next slides. Mm-hmm.
The market support inside information that it was going to close because it seems to go to zero a couple of days before closure. Right? Is that just a graph anomaly, or?
It's both. It's a sort of course, I mean, the point of the graph, but also it is how the market dies. The market is a series of addresses. So some may have been active for a little longer, some start dying, and then at a certain point we used official dates of closures, but it's never a sharp moment in time. No, sorry, no. I have so my data set is a network where I have the node that is the market. And I have these nodes which are not wallets anymore, are users, if you want, entities. And so then I see whether a users that used to interact with market A is moving to market B. Or maybe I don't get your question. So these users will likely change wallets identity, but I have it as a user. So this is incorporated into the creation of the data. That's the thing, exactly. Mixers start to become relevant at the end of the spectrum and are much more relevant recently. Mixers are things that are used to, very, very simply, also because I have a lot of things, but your beers, don't blame me. But basically to mask your traces. So you send money, the idea is you send, the basic idea, you send money to a mixer, the mixer will pay them. Reshuffling the technicalities so that the reconstruction of the flux is difficult. Delaying the payment, for example, etc. As you can imagine, companies like Chainalysis put a lot of effort in trying to back engineer mixers. But yeah, that's a problem. As I said, there is no ground truth. So surely this data set contains also fake positives. So. Yeah.
I'm curious, the comment you made earlier, you said people move in a coordinated fashion. Is that some coordination between them, or is that coordination because they're all responding to a shared signal, which is observing the next largest thing in itself?
I would love to know this. Of course, there are plenty of channels they can use, and I'm not familiar with. So yeah, probably there is a core that decides beforehand. No, the FBI uses the data Chainalysis gives them. At least so it's not so easy. Okay, so resilience is this systemic property thanks to migration. But to go to that question about whether they transact to the market, then we followed up this year, last year. And what we found, and we didn't expect, and also people at Chainalysis didn't expect, is that there is a large decentralized trade networks around markets. So users around markets also transact with one another without going to the market. So dark markets help create these networks, acting like, if you want, a piazza. So you go in the market, you meet your vendor, and then you start transacting outside of the market. From this point of view, especially today, a dark market is closer to Tinder than to eBay. So you go there, you find your match, and then you chat on WhatsApp. So this was our initial mental picture and what we did in the first study. Then we started noticing that these arrows existed. And what's even more interesting, I think, is that then what happens is that when the market is shut down, this network is quite resilient. So they stay. So there is also this extra layer. So for these user-to-user networks, there were 2 studies based on interviews suggesting that the network would exist. We had the luxury of millions of data and transactions and 40 markets, and 50% of the users also trade on the user-to-user network. So, and this is something I find very fascinating from a perspective of complex systems. So you have this system, nobody knows anybody else. So you have these aggregating structures, which are the markets. You start going there. At this point, you find yourself there. And there is a decentralized, there is a push again back to decentralization, because you have used them as meeting points. And then you don't need them, strictly speaking, anymore. And they also form stable relationships. In all cases, in our dataset, the trading volume in the decentralized network is larger than the one of the star network. And a decent fraction of users, at least 20% of those in the network, meet while active on the same dark market. So pairs are formed with one of the users transacting with the market. They have never transacted with one another. Then the other user transacts on the market too. And only then they create this. They pay the market or receive for the market. This is undirected. This individual, this entity. Then this entity does the same. And then we observe a transaction that does not involve the market anymore. At the beginning, we were only focusing on the star network, but then we have also this data. And you see these stable pairs, which we did a temporal backbone, but you can think about everything is exactly the same if you take those who have interacted more than 3 times. Yeah, but you see they are stable. So this is rescaling with 0 as the day of closure, and they tend to stay stable. So, okay, this is a recap that comes only after 3 slides, but there is this decentralized trade network, which is important both in terms of user numbers and trading volume. And of course, this creates further resilience if you want to dismantle something like that. I think we are doing now is that in everything, with Elohim sitting at the back, is everything I have told you so far is users. So now we are trying to devising methods to label them as vendors or buyers and see if they behave differently. Of course, the first indication is that vendors contribute to the resilience in significant ways. Last bit, very last bit, but it's very short. Also, you asked a lot of questions. This is a result I don't understand. So if you have an intuition, let me know. I have suspicions. So we now look at the coding of cryptocurrencies, and we look at the temporal network even more now. So resilience was a systemic property. Now it's transparency, which is a systemic property. The thing that is largely, if not fully ignored, is that crypto developers are not independent. And the traditional open code answer to transparency neglects the network completely. So it's not sufficient. So what is the problem? Code is law is a mantra that you hear from in the digital realm in general. Cryptos is just code. Okay, the code defines everything about a crypto. It only doesn't define the price in the market. Now, the problem for all code-based system is that, well, these developers then have an overwhelming power. Plus, we don't know what's in there. The traditional solution is, well, let's open the code so everyone can have a look, and we are sure there is nothing nasty going on. We analyzed 300 cryptos, 298 cryptos, we code in GitHub, and that are active on the market, okay? Because you have a lot of clones that are. This includes 63 of the top 100 cryptos. We have 6,300 developers who would do a lot of edits. And this is the different cryptocurrencies. Of course, Bitcoin and Ethereum dominate the landscape. What we find is that 4% of the developers contribute to more than one cryptocurrency. Okay, and as you can imagine, they are also the most active. So you have a network. So these crypto codes are not isolated silos. There is this activity of developers. And this is the absolute implicit assumption of open code. Because open code tells you, if you know the code, you know everything. What you don't know is why that code is there. So we built the network of co-coded cryptocurrencies. So you have developers and cryptocurrencies, and then you project it into cryptocurrencies. This is a small network. And we look at a very easy temporal property. That is, the first time, the first link, so it's unweighted. Okay. We are not interested in how many developers edit a pair of cryptocurrency. We only look at the time of creation of the link, the time at which the first coder codes it. Okay, this is a little bit heterogeneous, and you see the number of couples increases. Most developers that contribute to this network make only one link. One of them made a lot. But does this matter? Okay, it's a concern for transparency. Now we have a luxury. Cryptocurrencies are one of the few, maybe the only digital object which, besides a genotype, which is the code, has also a phenotype, which is how they behave in the market. Okay, so let's look at the market and at the process of network formation. So this is what we did. We have a developer that edits a first crypto and then edits a second crypto. This is the connection time because she's the very first developer to ever connect these two codes. Then we check price returns. This is just return of investment. The price today minus the price yesterday normalized of the two cryptocurrencies. And we say, does the correlation increase? It does, otherwise I wouldn't be telling you. The negative result stuff, nobody believes in it. So we rescale time so that 0 is the time at which all cryptocurrencies are connected. And this is linked pairs, and this is random pairs, randomized in several ways. So we have a longest line. Okay. And you see that you have this increase in correlation. The reason why it's above 0 even before is because Bitcoin basically correlates with all of them. In fact, then I will show you a figure where there is no Bitcoin or Ethereum, the big guys. Correlation increased for 65% of the linked pairs, because you could also think, okay, there is one dominating couple that is bringing the average up. So let's see instead in terms of linked pairs. And no, you see that it's the whole distribution that is tilted toward positive correlation after that time. And then we did this check in several ways. For example, removing the big guys. So you remove Bitcoin and you remove Ethereum. The network is sparser, but the phenomenon is still there. So it's not just that they. You can look at linked pairs. You have typically a large difference in volume between the two. The second edited crypto is younger and therefore also smaller. With few exceptions, they grow. We observed a mature phase of the cryptos. Why? Now, of course, the question is why. Now, we do not know. We have not. But there are two possibilities. The naive one is the market story. So code is open. Everyone can do the analysis we have done. So this is a signal to the market. The market reacts to this signal. The other one is that developers trade large amount of cryptos too. And there is always in open source projects the problem of incentives for developers. Here, one incentive could be that you become a serious stakeholder of the smaller crypto, and then you start trading it, maybe unconsciously or consciously, in a way that correlates with the other crypto you hold. What is sure is that there are hidden correlations. If you want to do portfolio diversification, this is a signal you might want to consider, and you don't consider. And this I anticipated this. And the other one is that correlation comes from the network. So as I said, transparency is a systemic property, and open code is not enough. And we think that this is a message that goes well beyond cryptocurrencies. So the network of co-coded objects. Okay, this is the paper is 2 years old, and this is again a recap. And now I'm done, and so beer time.
Thank you, Andre. Can I take any more questions from the audience?
Yeah. I'm not sure if it was covered. I'm intrigued by this result where the code development synchronized currencies. I'm not sure it was covered by the possibilities listed. is it possible that people who work on them are also influential in the success? Like I edit it because I'm a big shot in that, and now I've moved on to editing that, and that's linked my success with cryptocurrency A and cryptocurrency B.
Absolutely.
So it's driven by the devs.
Typically, when you act on a younger one, you are influential also because you acquire a lot of tokens. So you can, if you're rich, you can be influential in that sense. It can be that you bring your influence, but this is assuming that the market knows this for every time that there is one link that is being created. It is possible. We would like to know more. Of course, we haven't looked at the semantic. We consider pushed and pull accepted. We didn't look at the semantic of the exchange. We didn't look at successive editing. So there is a lot to look at. But the signal is there, and at the zero level is interesting for portfolio distribution.
Can I see what two hands or
Thank you very much. Had you had the chance, so you said that you didn't look at the weighted, the effect of the weights and the number of coders who co-edit. Is this data open source? I mean, I know the GitHub repos are open source, but do you know if anyone else has tried to look at this at the weighted effect?
Not that I'm aware, but we could and should. But yeah, resources are perfect. But yeah.
Thank you.
But the data, these data are outside, and in general, they are all public data because both daily price time series and code is open.
And when you said you had not analyzed the semantics, what did you mean by that? Do you mean like the communities, the community discussions around those cryptocurrencies, or
no? But also what the significance, if you want, of the edit of the second cryptocurrency.
Okay.
But in any case, was as in open source projects, it needed to be accepted by the community. So it is somehow significant, but we didn't check whether it correlates with writing a lot of code or not.
Gotcha.
Thank you.
Thanks. I think there's possibly a comment from Haroon in the chat about how some of the issues with are to do with the complexity of the code, and they like few people who can actually understand it. And
I see.
If I've understood it correctly.
Yeah, sorry, I see why open coding is enough. It's because of the code complexity. Well, it is because of code complexity, but also because of networks. I mean, the idea that everyone would read the code is a bit naive, of course. Even the formulation, the official formulation is that at least someone will. However, again, you miss this kind of information.
Sorry, I'm still half formulating this in my head. Apologies if it doesn't come out quite right. So I guess I'm trying to think of a situation where there's some sort of open source code development, say, and there aren't the like direct financial incentives to anyone could profit off it from someone paying you, etc. And I'm wondering whether you can compare what you see in the crypto repositories against, say, like regular open source development and adoption of libraries or techniques, or people editing across different currencies, sorry, not currencies, either like code bases, or even like things like an individual starts editing a new Wikipedia page, and whether correlations between pages they previously edited and the pages they newly edited are starting to like correlate with each other more, where there isn't like a sorry, do you know what I'm trying to get at here?
No, absolutely. Yeah. The cryptocurrencies have the luxury of, as I said, having this obvious, clear phenotype, which is the price. With Wikipedia, one could say, yeah, maybe it's someone who does amazing pages, and this will attract more public. But in theory,
or that like there's a current event which suddenly means that Donald Trump and some other person are now correlated in page views, and that the correlation page views happening because of, or correlation edits page is happening because of that is to do with some external signal rather than paid editing dynamics.
But in theory, this could be possible also here. The thing is, we have so many pairs that in the end,
and the point is to test between them, maybe.
Yeah, exactly. No, it's an interesting question. How and we thought about a little bit how to extend it to something that is not cryptos. We haven't been able to identify at the time a clear equivalent of the market, which is so transparent in a sense. The market has this nice feature of being very clear.
Yeah. Thank you, anyway.
Thank you.
So if there are no more questions, then I might thank Andrea again first.
Thank you. Thank you to the organizer.
Sorry, just one last question.
No, we haven't looked at motives, but the network is small.
Okay,
Small.
yeah.
But in any case, we haven't.
Yeah. We'll wrap up both the session and the rest of the day. So just wanted to say a few thank yous first. Without going on too much, I think the idea for this event was when we'd gone to one of the conferences like CCS or complex networks in Palma, and when we were chatting to people, realized that actually there's so many people doing something temporal networks, network dynamics, who are just a few miles away. Like, why are we just meeting at in somewhere in exotic location? So I thought it'd be nice to set this up, and really pleased with both all of the talks in the session and everyone who's come both online and in person. So thanks first to the speakers of the sessions who've given great talks. Thanks also to fellow organisers, Richard, Matt, Ben and Nicola, who unfortunately couldn't make it today. And thanks to Pometry for sponsoring, and Idea London, who can let us use the space and do all of the coffee breaks and everything. So I think without further ado, let's head to the pub.